Great. Well, first of all, thank you very much for all coming, and thank you for having me. It's a great pleasure to be able to be with you here. I'll be talking on an observational overview of active galactic nuclei. That's the sort of summary for all of the lectures that I'll be giving. And I want to stress the observational aspect of it. I'm going to stress observations of active galaxies, what we can measure about them reliably, what we're still trying to measure but can't do reliably. And of course, equally important will be the theoretical overview of active galaxies, which we'll hear about from the speaker in the afternoons. So I'll start just with a summary of the lectures that I'm going to give. There's going to be sort of four main chapters. Here's the fourth. Today I'll start in giving a general introduction, talking about some of the historical findings about active galaxies and so on. I'll then give a sort of basic summary of the basic observational facts about active galaxies. What are the most essential things that any model of active galaxies has to be able to explain? I'll then talk about how we find active galaxies out in the universe. There's a tremendous industry of people trying to find active galaxies using optical surveys, using surveys in the radio or the infrared or the X-ray. And a lot of our ability to go and study active galaxies really well depends just upon our ability to find them in the first place. And so I'll talk quite a bit about finding active galaxies, and then I'll say something about the terminology of active galaxies. So that's going to be sort of the first chapter. We're then going to move to talking about sort of breaking down the basic structure of an active galaxy. And we'll start by talking about observations on small scales, talking about the region in the immediate vicinity of the supermassive black hole, which we think is the main engine for what's going on. We can now actually make quite sophisticated measurements of what's going on in the immediate vicinity of the black hole. And I'll talk about those types of observations. We'll then talk about one of the main sources of optical and ultraviolet emission lines, the so-called Broadline region. And then we'll talk about winds, which we know are expelled outward from many active galaxies, and which may have a role in making the black holes that power these active galaxies interact with the galaxy that it's embedded in. So we'll talk about these winds some. And then we'll move on to larger scales. That'll be the sort of the third chapter. We'll talk about the narrow line region, another critical emission line region in these active galaxies. We'll talk about the so-called Torus. This has been a very important discovery whereby people now realize that a lot of the diversity that we previously had seen from one active galaxy to the next can be quite simply explained in the context of a unified model, which invokes this Torus. So we'll talk about that. And we'll then move on and talk about jets. Many of you have probably seen these beautiful images of relativistic jets being fired out from active galaxies. And we'll talk about these jets and what we've been able to learn about them. And then we'll end, sort of the final chapter, will be a more focused lecture. And this is going to draw upon the work that my group at Penn State and many other groups around the world have been doing on extragalactic X-ray surveys. And we'll talk about what X-ray surveys have taught us about the demographics and the physical processes going on, and the ecology. That is how the black hole interacts with its environment. We'll talk about those aspects as revealed by the X-ray surveys. So that's the overall layout for what I'm going to be covering this whole week. Okay? And before I sort of launch into the details, I have a few more just general things to say. So even with the 5 lectures that are allotted here, we're only going to be able, just considering just the observations, we're only going to be able to scratch the surface of a truly massive field. There's a very large number of people that have been working now for decades making observations of these active galaxies. And so we're just going to be covering just the surface here. There literally are thousands of papers in the literature now, okay, on the subject. And so what I'm going to aim to do is to give the main ideas that are relevant. But unfortunately, I won't be able to note every special particular case or every technical exception or anything like that. I'm going to aim to get you the main essential ideas. And even with that, there's a tremendous amount to sort of learn and explore there. And I do want to mention that there are a number of good books that have been published, and these books have been enormous efforts for people to prepare on active galaxies. Here are two of them. Here's another two, and I'll just say a few words about these. So if you have interest after hearing what I've said and you want to go further and see more, these are some good books to sort of study. There's a quite recently published book, The Physics and Evolution of Active Galactic Nuclei by Haggai Netzer, who's an expert researcher in the field. And I would say that overall, if I could only buy one book, if I only had limited money, or in fact I had limited luggage allowance on my flights to China, so I could only bring one book, and that's the one I chose to bring. Okay, and that's just because of the fact that it happens to have been very recently published, so it's very up to date in this fast-moving field, and it's a quite comprehensive, readable overview summary of active galactic nuclei. So that's a very good one to start with, I would say. There's also another excellent book by Brad Peterson, who's an expert at studying the emission line properties of active galaxies. This one is also very good. It's getting a little bit out of date now. It's I don't know, a decade or so old. Okay, and then there's a book, a quite massive volume, in fact, by Julian Krolik on active galactic nuclei. This is a very high level, sort of high graduate level summary of active galactic nuclei, prepared from a more sort of theoretical point of view. I would say that these first two books, well, this one is both sort of observational and theory. This one is fairly observationally driven. This one is more theoretically driven, and I'm sure there are others as well, but that's a quite good theoretical book if you're interested in those topics. And then there's a sort of a classic book on the astrophysics of gaseous nebulae and active galactic nuclei that talks a lot about the emission line formation processes in active galaxies, for example. So those are some examples of books that you might find valuable if you want to go beyond what I'm able to cover. And I just want to say something about questions. First of all, questions are very strongly encouraged at any time. So feel free, just if I'm saying something and it's not clear, stop me and ask me a question by all means, because quite likely other people aren't understanding or either. And so by all means, I'm very happy to do it. Or if you're really interested in something I'm saying and want to hear a little bit more, please direct me, because I very much want to go in the directions that's most useful to you. So please give me help in this way so I'm able to do the best possible job for you. And I will say that sometimes I may defer a question until I've had time to develop the relevant underlying context. In other words, if you ask a question and it's something that I'm going to be covering like 5 slides ahead, I may just ask to defer it a little bit until I'm able to give the relevant sort of underlying context to answer the question well. And if somehow I forget your question and I've said that, please remind me. And I'm also, of course, certainly happy to talk with people outside the lectures as well if you have any questions. So by all means, questions are very, very encouraged. OK, so now let's launch into this first chapter. Any questions before we start? OK, so let's launch into the first chapter then, which is on, again, an introduction on the basics of active galaxies, on finding active galaxies, and on the terminology that we use to describe them. So I'm going to start with just some early history of AGN studies. How did this field develop in the early days? How did we get to where we are now? Okay. Well, there's actually quite a long history. In fact, it goes all the way back to as early as sort of 1908, in at least what I'm aware of, where back in 1908 there was a man named Edward Pfaff. Here's a picture of Professor Pfaff there. And he noted back in 1908 strong emission lines from hydrogen, oxygen, and neon in the nuclear spectrum of NGC 1068, an object that we know today is a bright, nearby active galaxy. Okay? And you have to remember that this was before we had general relativity. It was before people had come up with the Schwarzschild metric. And it was also before people even realized, it took until the 1920s, until people even realized that galaxies were truly extragalactic objects, their own galaxies into themselves. And so long ago, okay, people knew that, hey, there's this remarkable object out there, NGC 1068. It has these remarkable emission lines. This is a very curious thing. Pfaff commented on it extensively. And people knew there was something suspicious going on here, even if they didn't have even the underlying framework to understand what they were seeing. They knew that things remarkable were going on. Then people later on, a man named Vesto Slipher, obtained a higher quality spectrum of NGC 1068. And this was a tremendous amount of work. Slipher would have to go and, with his telescope, would have to point it at NGC 1068 and expose all night, okay, to get a high quality spectrum. And then the night would be coming to an end, so he would, and this was with photographic film. And so he didn't want the film to get developed. And so he would then put a lid on the box where the film was and take it off and put it in a drawer. And then he would come back the next night, put it back in the telescope and observe again all night, and then put it in a box and put it in the drawer, and then come back the next night. Because he had a limited telescope, and to get a high quality spectrum in those early days, that's what you had to do. So he would literally expose for many nights in a row to get these spectra. And he noted that the emission lines of NGC 1068 were unusually broad in that high quality spectrum, a hint that there was high velocity gas present in this active galaxy. And of course, he didn't know what to make of it entirely, because again, people hadn't realized that galaxies were even extragalactic yet. But he knew there was something remarkable going on. Another remarkable early discovery was a man named Heber Curtis, noted in another nearby active galaxy, M87, what he called a curious straight ray connected with the nucleus by a thin line of matter. That was back in 1918. And here is Heber Curtis, and here is a more modern observation of M87. And the curious straight ray that he was talking about is that, which is a relativistic jet sticking out of M87. And so back in 1917, he saw this jet sticking out of M87. You know, that's very strange. Why is there this thing sticking out of this galaxy? Well, we now know today that it's because there's a relativistic particle jet being fired out of the center of that active galaxy by the black hole. Of course, Curtis didn't have the context to understand what he was seeing back then, but that's what he was seeing. And then a few more words then. Again, then we had the general realization that galaxies are truly extragalactic. Edwin Hubble noted, also around in a similar time frame, noted the nuclear emission line spectra of of NGC 1068 and two other active galaxies, NGC 4051 and NGC 4151. And again, he just noted that this is rather peculiar, that these galaxies stand out from other typical galaxies in having these strong nuclear emission line spectra. And again, he didn't know what to make of it at the time, but that's what people found. So then further progress came, well, in a number of directions. First of all, came from radio astronomy. So around sort of the 1930s and 1940s was when radio astronomy was being developed for the first time. I believe that an amateur astronomer, Grote Reber, discovered a bright radio source, which we know today is Cygnus A, a powerful radio galaxy. Another man named Carl Seyfert showed in a definitive study in 1943 that a fraction of galaxies have strong, broad emission lines, and that these galaxies, the ones that have the strong, broad emission lines, are especially luminous, particularly in their nuclear regions. They had very bright nuclear regions. And today we, in fact, named after, based on Seyfert's work, we refer to these galaxies as Seyfert galaxies. So sometimes in this lecture, you'll hear me talking about this Seyfert galaxy or that Seyfert galaxy. Well, that goes back to this work that Carl Seyfert had done. Here is Carl Seyfert. And, well, and unfortunately, this didn't come out very well, but here are some emission line spectra from his original paper. Okay? And here, by the way, here is Cygnus A, which I mentioned previously, which is a powerful radio source. These are big lobes of relativistic particles, and that's the relativistic jet being fired out of Cygnus A. A huge advance came in 1963 when Martin Schmidt, drawing upon observations made by a number of people, discovered an object which people had known about, 3C273, which was the 273rd object in a radio catalog made by radio astronomers at Cambridge University. That's what the C stands for. He discovered this object to have a redshift of 0.158. This was a very important discovery. It was the first time people had identified a quasar. Okay? And here is Martin Schmidt on the cover of Time magazine based upon this work. And at the time, he found this object had a redshift of 0.158. And that was at the time, that was an astonishing redshift. I mean, redshift 0.158, oh my gosh. Now, of course, today we're regularly finding objects at redshift 6 and 7 and so on, but back then that was a tremendous enlargement of our ability to study the distant universe. Then things took off very rapidly. This discovery caught astronomers' attention very, very greatly. And Schmidt went on shortly thereafter to find many more such quasars and to study the evolution of such quasars, and he's still at it today, in fact. Then in 1964, Zeldovich and Novikov and Saltpeter speculated about what could be the driver of these quasars, these incredibly luminous objects out in the universe. And they speculated that black holes may be powering them. Now, this was before, in fact, the term black hole had come into general use. That actually didn't come into general use until about 1967 or so. And then in a very important paper, a man, Donald Lyndon Bell, who again is still active today, noted that many galactic nuclei may contain what he referred to as collapsed old quasars. And so the idea here is that when you see a distant quasar out in the universe, that represents a growing supermassive black hole. And Lyndon Bell made estimates about how many supermassive black holes should have grown given our studies of quasars in the distant universe, and compared that to the density of galaxies in the local universe, and reasoned that it's quite likely to expect that we should see what he referred to as a collapsed old quasar in the center of many galaxies in the local universe. And indeed, studies today have shown that's the case, that in fact most massive galaxies have, ones that have at least a decently defined nucleus to them, appear to have a supermassive black hole in the middle. Okay. And then after this time, the subject took off. AGNs became a topic of widespread study, and that's how we sort of ended up with where we are today. Is then there was a huge influx of people working in the field, all sorts of exciting discoveries, and that's how we made progress since then. So anyway, that's a brief history. Is that clear? So that's sort of roughly how we ended up with where we are. And again, you can see that, if you sort of step back, you can see that, like many things, the progress here, the observational progress, was not just a straight linear improvement over time. I mean, people were finding things and sort of writing down and saying, this is very remarkable. And then people would just forget about it. People forgot about Fath's work until someone dug it up in an archive much later. And similarly, Heber Curtis noted this curious straight ray. And we know today that's a relativistic jet. But no one really jumped on it back then and really followed it up very effectively to sort of study it further, even though perhaps they could have. And similarly, like Edwin Hubble's work here, noting the nuclear emission line spectra back in 1926, was sort of dropped until 1943, until people made further progress on that. And so you can see that somehow, oftentimes, progress in science is much more haphazard than one would like, where people sort of find things and they don't know what to make of them, and then they forget about them, and it's only much later on that you actually start picking these things up. Okay, so that's a quick historical overview. Now let's start talking about the basic observed properties of these active galaxies. First of all, when we observe typical galaxies out in the universe, non-active galaxies to start with, we typically see, like these two here, we typically see the light from them is just the summed light from all the stars in that galaxy. You're just seeing the co-added emission from all the stars in that galaxy, plus any gas clouds that those stars irradiate and so on. And that's what makes the light that you're seeing. Okay. However, there is a subset of galaxies, the so-called active galaxies, where something remarkably different is going on, where they have this very bright point-like nuclear source. Here, for the case of 3C273, and there, for the case of this other luminous active galaxy. And in both cases, you can see there is a host galaxy around these things. You can see the host galaxy there. It's disturbed and so on, but there definitely is a host galaxy there. And so one thing just to ask to start with, just in very basic round numbers, is how common are these types of galaxies, these active galaxies? Well, people have done extensive studies of that And again, in very round numbers, if you consider luminous quasars, things like 3C273, it's about 1 in a million mass of galaxy will contain a luminous quasar like that. And that's in the local universe. That's around us today. If you go back to earlier cosmic times, that answer is quite different. And we'll come to what happens at earlier cosmic times in a later lecture. So, but just around us today in the universe, it's like 1 in a million mass of galaxies will contain a luminous quasar. If you go to these sort of moderately luminous objects, the objects that were studied by Seyfert, if you ask how common are these so-called Seyfert galaxies, well, it's about 5%. About 5% of massive galaxies contain these moderately luminous active nuclei in them. Okay. And then if you push down to even more sensitive levels to look for any sign of nuclear activity, okay, by looking for weak emission lines or by looking for a very faint X-ray source in the nuclear regions. There's 2 examples of how you can do this, or a very faint radio source. Then you find that about 30%, okay, of 30% of massive galaxies will show some sign of low-level nuclear activity, and that's a pretty significant number. Okay, 30%. That's you know, a good fraction of galaxies have something going on, notable, you know, associated with this black hole. Okay. Although, typically though, as you go to higher and higher luminosities, the activity gets rarer and rarer. Okay. So what are? Yeah, sure. Yeah, sure.
How reliable is 30% number is? Because I guess it depends on the sensitivity of the.
Oh, yes, certainly. Yes. In fact, I'll come to that a little bit more later on. So well, certainly when you get down to this very low very low levels, and I'll say more about this in a minute, it almost becomes semantic, what you call an active galaxy and what you call a normal galaxy. Indeed, if you're willing to go down to very faint levels at the center of our own galaxy, you know, we see, in fact, I was involved in seeing the X-ray flares from the center of our galaxy for the first time. And, you know, so even our galaxy, I mean, it depends at some level what you're going to call an active galaxy. And so at these very faint levels, it almost becomes semantic, because as far as I'm aware, there isn't any property that's clearly bimodal that separates a group of active galaxies over here and a group of normal galaxies over here. It's a continuous distribution, and what we call active and what we call normal can become somewhat semantic in the end. Yeah, that's right. Any other questions on that? Okay, it's a good point. Okay, so now let's go on and talk about the basic observed properties of active galaxies. So here are 5 main, if I had to sort of sum up what I think are sort of the 5 main observed properties of AGNs in a very broad sense. And we'll go into a lot more technical detail on all these things later on. But for today, we'll just speak very broadly. First of all, we observe that these active galaxies have a broad range of luminosities, in some cases reaching very large values indeed. Okay? Secondly, they show strong and broad emission lines in the optical and the ultraviolet, sometimes in the infrared as well. The emission we see from these active galaxies comes out over a very broad band. It's a very broadband emission, very unlike that of a star. Okay? We also observe variability to be a common property of active galaxies. These things aren't steady over time. They're changing over time. And then finally, we often observe particle jets being fired out from these active galaxies. And I've alluded to all these things already, but I want to say some more about them. So those, in a very broad sense, are the basic observed properties of these things. So let's talk about them. Let's talk about the broad range of luminosities to start with. Well, this is a technical plot. The details aren't so important. It's basically, this plot is measuring the relative amounts of optical versus X-ray power versus luminosity. Don't worry about the y-axis so much. Worry about the x-axis. And look at the range of the x-axis. So each one of those is 2 orders of magnitude. So you've got 2, 4, 6, 8, 10 orders of magnitude, almost. Really, it's only about 9 if you consider the low populations at the end. It's about 9 orders of magnitude being covered in luminosity in things that we call active galaxies. So that's what I mean when I mean this broad range of luminosity. I mean a factor of 1 billion, okay, range at least, okay, in luminosity, in things that we call active galactic nuclei. Okay. And these range from at the very most luminous end, things that we refer to as quasars. Those are the most powerful examples of active galaxies. Down to more moderate luminosity objects that we refer to as the Seyfert galaxies, for example. And I'll say more about this nomenclature later on. And then down to much more lower luminosity, the so-called low luminosity active galaxies down there. And so there's a tremendous range of power among these things that we call active galaxies. Okay, and I'll say some more about that. So I referred to the 9 orders of magnitude already. And then to go back to the question that was asked, as was mentioned already, there is really no strict lower limit on the luminosity. Again, even the black hole at the center of our galaxy shows some intermittent activity at very low levels. Okay? And if you wanted to include that on a diagram like this, you'd have to go down substantially further still. You'd go down, in fact, to about, well, that unit would really apply. But in comparable units, it'd be down at like 10 to the 34, okay, or 10 to the 33 for our own galaxy. Okay, so it would go down even further if you were to include that. And so then, as was mentioned already, at very low luminosities, this distinction between what we call active and what we call normal is sort of largely semantic. There's no clear bimodal separation of properties. There is, however, sort of a maximum observed luminosity. That is, we believe we've surveyed the universe well enough now that we have found examples of the most luminous active galaxies that exist in the universe, period. Okay? In other words, we don't think that in 10 years, if we go do a better survey, we'll find new examples of active galaxies that are 100 times more luminous still. We think that these things out here, sorry, go back here. We think that these things over here that we're studying are the most powerful that they come. And just to sort of give you a little bit of perspective, up here at the very highest luminosity end, you're seeing objects that are outshining the galaxy in which they live by a factor of 10,000 to 100,000. Okay, so these are extraordinarily luminous things, okay, at the high luminosity end. Some of the quasars are really quite remarkable. And these are so luminous that even if you put them out at very high redshift 4, 5, 6, they're still quite bright, okay? And so we believe that we found examples of the most luminous things that exist out there. We're not going to find even more luminous things in 10 years or something like that. Yeah. Yeah, sure.
Do we have any theories that can predict the upper limit of the most luminous quasars?
Well,
I mean, they could be really, really rare, so we just haven't got them.
we haven't. Well, okay, we have. Well, I mean, if you look at the sky surveys that we've done now, like for example, Sloan. For Sloan, we've surveyed quite well about 10,000 square degrees. That's a quarter of the sky. We've surveyed it well enough that we think we've found all the really luminous things there. So at some level, it's sort of a statistical question. I mean, if you've surveyed a quarter of the sky and you haven't found any that are much more luminous than that, then what's the chance that if you survey the rest, you're suddenly going to find one way up there? Not so likely. That's the first one. Secondly, then, if you work out, and this is something that hasn't been covered yet, but if you work out according to the Eddington limit and so on, that the black hole masses that are inferred for the objects up there, you get like 10 to the 10 solar mass black holes up there. And if you look in the local universe, what we know about black holes in the local universe, that's like at the high end of the most massive they come. If you look at, for example, the black hole at the center of M87, it's like 6 times 10 to the 9 solar masses. And that's about as massive as black holes come. It's somewhat higher than that. They've found evidence for a few in massive cluster galaxies, the massive galaxies in the center of clusters that are up around 10 to the 10. And we aren't finding black holes. So actually, it sort of lines up quite nicely in that the most massive black holes that we can find in the local universe have Eddington limits comparable to the power that we see from the most powerful quasars. So that's the best theoretical argument that I can give. Yeah. Other questions on that? Yeah. I don't mind. Go ahead. Sure.
What's the coefficient for alpha?
Oh, yeah. Okay. Yeah. Okay. Yeah. Alpha again. Don't get hung up over it for now. I'll say a lot more about it later. Alpha in this case is measuring an effective slope between the optical and the X-ray band. It's measuring an effective spectral slope such that, and again, that's not the point of this diagram in this context. But I will just say that the way what it's showing, what it's showing is that the objects that are over here, further down towards large negative values, have relatively weak X-ray emission compared to their optical emission. Okay, and objects over here have relatively strong, okay, X-ray emission compared to their optical emission. So there are interesting things that correlate with luminosity as well, and I'll say a lot more about them later on. That's not where I'm going to go right now, but we'll say a lot more about that later on. For now, I just am trying to get you to focus on this axis, which is very impressive just by itself, the fact that you've got 10 orders of magnitude on that axis. Yeah. Thought there was another question. Yeah. Does the luminosity, no, okay, okay, so his question is the luminosity that's being quoted here including the luminosity of the galaxy? And I can say, well, up here, yes, but it hardly matters because the quasars are so outshining the galaxy, it doesn't matter. Down here, it's safer luminosity. I can tell you because I was involved in this work. We, in fact, used Hubble Space Telescope imaging to cut out the nuclear region and just get the nuclear light. Now, whether you can do that perfectly or not, it's not an easy thing to do, but we think we've effectively cut out most of the starlight from the galaxy there. And then down here again, that's very difficult indeed. And you might wonder, why are there these funny lines where it's over here, but then they draw a line going over to there? Well, that's because that's where you get it if you just do a measurement straight, and that's where you get it if you do your best to get out the starlight. And so people are doing their best in this diagram just to show the black hole related light and not the starlight from the host galaxy. But it's not always an easy thing to do. It does help when you're working at 2,500 angstroms, but it's not so easy. Yeah. Sorry. Other questions? Okay, great. So, right, so we already talked about all this stuff. So again, so that's what we know about just about the luminosity range. It's very impressive just considering the luminosity range alone. Okay, so now let's go on to the next observed point. Again, we're just working our way through this list that I gave here. We just did the broad range of luminosities. Now let's talk about the strong and broad optical UV emission lines. So here is a plot that people made using large numbers of spectra from the Sloan Digital Sky Survey to get a very high quality spectrum, okay, of in this case, a typical active galaxy. This is like a composite spectrum of many quasars added together to show you a typical spectrum. So the point here is that in addition to the continuum emission, which the first order is approximated by this dashed line here, okay, you also have sitting on top of that these strong and broad optical UV emission lines. Here they are, Lyman alpha, carbon 4, carbon 3, magnesium 2, oxygen 3, H alpha, for example. And both the strong and the broad part of that statement deserve note. Okay, the lines are strong in that they have large equivalent widths. That tells you there's quite a bit of line-emitting gas, nebular gas, in the central regions that is making the line. And the widths, well, I'll say more about that momentarily. Here's another plot that sort of shows this in more detail. Again, if you want to see all the details, you can go to the paper by Vandenberg et al. Is one nice example. And this plot is showing panel by panel connected up the whole spectrum. And you can see if you really go in and look very carefully at a high quality spectrum, you can see tons of little emission lines. Each one of these things labeled here is an emission line, okay, from this composite spectrum. So there's a whole forest of emission lines that are there. Okay. And so, again, I already mentioned that the strong part of the statement indicates that there's a large amount of ionized nebular gas producing line emission. And the idea to first order is you have gas in the central region that's being photoionized by the brilliant central source. Okay? I mean, you have this brilliant central source to work with. We've talked about that already back here. Okay? All you need to do is put gas close to that thing, nebular gas close to that thing, and it's going to make large amounts of line emission. Okay? And so that's the idea to first order. And we'll say a lot more about that later on. But that's the idea. You have photoionized gas doing that. Now let's talk about the sort of broad part of it. These lines have significant intrinsic widths to them, okay, in many cases. You can go back here. You can see that they have significant width to them. Many of the lines do. And these indicate, the idea here is that you're seeing not thermal motions. You aren't just seeing the gas is really hot, so you aren't seeing thermal broadening of the lines. This is thought to be Doppler broadening. The gas in there is moving around, has some bulk motions within it, and that's what broadens the line. Some of the gas moving toward you, some of the gas is moving away, and all that, when co-added together, is what produces the broad profiles of the lines. And here you can see it even further. Here you can see this nice broad profile here, of, in this case, the H-beta line. Some of the lines are considerably narrower, however. Okay? Here, for example, is forbidden oxygen 3, which is much narrower, okay, than, for example, H-beta. And that's something that is quite important to note. And in fact, this leads to the idea of the broadline region and the narrow line region being distinct regions within an active galactic nucleus. And we'll say much more about that in a later lecture. Okay. But you can see that just from looking at that. So the line widths indicate high-speed motions with a wide range of velocities, up to, in the most impressive cases, up to something like 25,000 kilometers per second. So very high speeds indeed. And people have also done detailed modeling of the spectra to try to get basic estimates of what the abundances are. This is a very difficult thing to do. You can't do it to extremely high precision or anything like that. But typically, we estimate that the abundances are roughly solar or perhaps slightly supersolar, okay, in these emitting regions. So that's the second point. Okay. In addition to these emission lines, I also want to mention that sometimes, not always, sometimes we see blue shifted absorption lines as well. Okay, and here's some nice. Here's one particularly nice example of a quasar. In addition to the nice emission lines, which are still there, here you can see the emission lines. You can see that there are these big gashes being cut out of the spectrum there, 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 and there. Those are absorption lines, what are called broad absorption lines, okay, in this object. So in addition to there being nebula gas that's emitting, and that the idea is here you have some gas along our line of sight that's absorbing radiation and preventing it from getting out, okay? And we see that these absorption lines have a broad range of widths. In the most impressive cases, like the one that I've chosen to show here, you see the widths of the lines being very broad, okay? Thousands of kilometers per second broad, indicating that you have gas moving outward, presumably spanning a broad range of velocities to cause the width of the absorption trough. Okay. Sometimes the absorption features are much narrower, but sometimes we see absorption lines as well. And we'll say much more about them when we talk about the winds in active galaxies. Okay. A few more things. Now let's move on to talk about the emission we see from these active galaxies over a very broad band. Okay, so we observe that the emission from these active galaxies comes out over an extremely broad bandpass. This is basically showing, in this case, effective sort of luminosity or effective flux, okay, versus rest frame wavelength, running all the way from, let's see, down here in the radio, okay, up through the infrared and the sort of optical and ultraviolet, and then up here in the X-ray band. And the point here is that both, well, essentially for all types of active galaxies, you see a very broad band emission. Sometimes some objects have very strong radio emission, sometimes they don't. But even leaving aside the radio emission, the broadband spectrum that you're seeing covers many orders of magnitude in frequency with substantial amounts of power coming out in all those frequencies. This is totally unlike a star, okay? You know, a star will typically peak in the optical, or if it's a hot star in the UV, if it's a cool star, it's in the infrared, but it'll span a relatively narrow range of wavelengths. And you know, while our sun does produce some X-ray emission from the solar corona, it's at a much lower level compared to the overall power. It's about a millionth or less of the total power from the sun comes out in the X-ray band. Okay. Here, you can see that the X-rays make up like 10% of the power coming out at low luminosities, at least. And you have substantial amounts of power coming out at all these wavelengths, or all these frequencies. So there's no single frequency that you can sort of ignore and say it's not very important. These things are genuinely powerful broadband emitters. Okay. Yeah?
Why don't we have data in between 11 and 13? There are no data.
Well, it's because historically it's been difficult to obtain data in that range. That is changing now with good millimeter and sub-millimeter observations. It's becoming possible to fill that in. Yeah, it's just observational. It's from the sample that they were working with here, the data that they had available. You probably know that, for example, we have excellent all-sky survey data, for example, from Sloan in the optical. We also have that now, you know, in the infrared, for example, from WISE. But we don't have an excellent all-sky survey down in the sub-millimeter. So that's why that region is not filled in as well as the others. Yes, but it's very important to study that region, and people are filling it in. And I do want to mention that in some cases, the emission is much broader still. You can see here, just remember the sort of frequency that we're going up to here. This is sort of 10 keV X-rays up here that we're getting up to there. In some active galaxies, you go to much broader still. In the so-called blazars, which we'll talk about later on, okay, and so just to put that in context, you know, where is 10 keV on here? What is this? Here's, yeah, they did it all in MeV for me here to make it difficult. So that's an MeV. So that would be, that's like a keV. So that'll be like 100 keV there, okay? And for these two objects on the top, you can see that they don't stop even in the X-ray band. They go all the way up to very high energy gamma rays, okay? And so they go up orders of magnitude. What is this? This is 2, 4, 6 orders of magnitude further still. In fact, of a million up further still, up to the very high energy gamma rays. Some active galaxies will be powerful emitters there. This is typically emission that's thought to be associated with jets being fired out. But that shows that in some cases, the emissions even are spanning a broader band than what we typically talk about. Okay, so that's the broadband nature of these things. These things are genuinely broadband emitters. Let's talk about the variability. Yeah, sure.
So going back to the last year, how many fractions of the AGN show such high frequency?
Show this very high. It's a tiny fraction, less than 1 in 100, probably less than 1 in 1,000. Of all AGN, that's right. I mean, the majority of active galaxies, and I'll talk about this more later on for those who are following, but so going back to this plot, you probably know that this plot is separated out into radio quiet and radio loud active galaxies. In round numbers, at least up at fairly high luminosity, very high total AGN luminosities, the radio quiet objects make up about 90% of active galaxies. The radio louds make up about 10%. And then the blazars are a subset of these, a very specialized subset of these. And they're the ones where the relativistic jet happens to be pointed right at you. And that's an even smaller fraction. So
most AGN, roughly several hundred.
Yeah, most AGNs have cutoffs at a couple hundred keV. That's right. And I know it does. Well, and these AGNs, okay. What I'm trying to say is the power that we can measure from them, where a substantial fraction of the power coming out cuts off at a couple hundred keV. For all I know, if we could study these AGNs, if we could study, say, NGC 4151 at the same sensitivity level that we could study Sag star, maybe we would see some luminosity there. But it's going to be down greatly in terms of overall bolometric importance. Yeah, right. OK. Yeah. So any other questions? OK, great. So then now let's talk about the variability. And so another sort of basic defining property of these active galaxies is that they're variable. OK? And this has been noted for a long time. In fact, it was noted as early as the 19th century. People had seen things up in the sky that were varying up and down, okay? But they misclassified them as variable stars back then. Okay, we now know today that some of the measurements they were making back then are quite useful, in fact, for studying the active galaxies. And in fact, variability could have allowed the discovery of active galaxies even earlier than they were discovered. But this is one of these cases where people just didn't follow up on it. Science is not as organized as you might think sometimes. And here's a nice example. This is 3C273. This is about 100 years light curve data on 3C273. And generally, among active galaxies overall, the variability that we see from them is generally chaotic. Okay, there's no clear periodicity to it. like a binary star, nothing like that. No clear even sort of quasi-period to it, although quasi-periods have been found in a few cases. Generally, you're just seeing this erratic variability up and down. I'll say much more about the measurement of that variability later on. And this variability, in this case, well, this is a measurement here in the B band, okay? But this is a multi-wavelength phenomenon. Here are measurements here in the radio. Okay, these three are all, I think these three are in the radio. Then here, yeah, here we're going out to, what is this? That's sort of pretty long wavelength infrared. Then here we're moving through the optical, and there's X-ray bands. You can see that there is substantial variability from this thing, okay, at all these wavelengths. In fact, there's significant correlation from one to the next. You can see that that relates to that, relates to that. And I'll say much more about this later on, about the properties of this variability. Variability in different bands is often correlated, and that there's a great deal to be learned by studying that correlated variability from one band to the next. Okay? I do want to highlight some of the more extreme examples of variability, for example, in the X-ray band. One thing that we see, broadly speaking, is that variability generally becomes stronger in terms of being of larger amplitude and being more rapid, okay, as one moves to higher frequencies. X-rays are a particularly good way to study them if you want to see a lot of variability. Here's a nice example. This is a measurement, in this case, of a nearby active galaxy. That's a telephone number if you want to give it a call. Okay? And it's basically measuring the counts per second coming in, okay, versus time from this active galaxy. And you can see that this thing is varying by large factors, by factors of 2 or 3 from there to there, okay, on time scales of like an hour or less, okay. And this is commonly seen. Here's another. Here are some long-term monitoring of the X-ray variability of these things, and you can see these things are jumping up and down like crazy from one day to the next, okay, as they vary up and down, okay. And so this is important because it tells us something about the physical size of the region producing the X-ray emission, specifically that it has to be quite small. Okay, if you're seeing these things varying by factors of 2 or more, by large amplitudes on these sorts of short time scales, that implies that the emission region size, at least the emission region where the X-rays are coming from, is small. It's like, you know, of order light hours or less. Okay, and that has some important implications that we'll talk about later on. Another point just to make quickly is that the emission lines of these active galaxies are also variable. If you study just the emission lines, here for example, here is showing a nearby active galaxy NGC 5548. This is the mean of 34 spectra people took of 5548. And here they look at the RMS, okay, the RMS of those 34 spectra. And you see that the emission line is variable, okay? And in fact, people have noted that. They've noted that the broad emission lines vary. And in fact, they then make light curves showing the light curve of the continuum and the light curve of the line. And they find that these two things behave in a similar way, but in the sense that the emission lines vary, but they vary in a way that generally follows the variability of the continuum with a lag. Okay, so the emission lines are varying, but they vary in a way that sort of lags the continuum a little bit. And this leads to the idea that maybe we're seeing a time delay, the time it would take for the continuum emission to reach the line emission region. Okay, and this leads to the whole idea of reverberation mapping of active galaxies that we'll talk about later on. But the lines vary as well. And so what does this tell us, this variability? Well, the first thing overall is that the observed variability implies that the main emission regions have sizes of light hours to light days or less. Okay, so we're talking about compact regions here producing this power. And even for close active galaxies, this implies angular sizes that are very tiny, something like 10 to the minus 6 to 10 to the minus 5 arc seconds. And that's in the best case of nearby active galaxies. Okay? And that's too small, at least presently, for us to image directly. Okay? And for comparison, when people take all radio telescopes spread all across the Earth and combine them together with aperture synthesis techniques to get the very highest angular resolution they can get, you can get their typical resolutions of about 0.0002 arc seconds. that still is far short of getting to where we can actually image directly nearby active galaxies, which are substantially smaller angular sizes still. And the point here, to sort of take away from that, is it's very common. You'll see me do it because I love showing these beautiful pictures that artists draw of these active galaxies because they look really neat and things to talk about. But keep in mind, whenever you see pictures like these, they're only artists' impressions of what's going on. We have not yet succeeded in making direct images of the black hole region of these active galaxies. We do hope to do that in the future, and people are working to make direct images of the emission region of the black hole in the center of our galaxy, which happens to be a very promising candidate for such work, but that has not really been achieved fully so far. But that's something for the future. And so just keep in mind that pictures like these will always be artist impressions constructed based upon measurements we make of variability or measurements of spectra and so on, but we can't make such images directly. Okay, so generally, when we study the variability of active galaxies, generally you don't see periodicity. Generally, they vary in a fairly chaotic manner up and down. There are a couple of cases where people have claimed to have detected typically it's not a proper periodicity, but they talk about measuring some kind of quasi-period behavior. And that's been found in a few cases. The best established cases I'm aware of generally talk about quite short quasi-periods. I know people have claimed in some long-term light curves to see quasi-periodic behavior. Even if you see that type of behavior, that doesn't prove that the emission region is that large. It could still be smaller than that. So, I mean, I would not be optimistic about our ability to go in and spatially resolve these emission line regions anytime in the near future. I think that's going to be in general a ways off, although we may be able to do it for isolated specific cases like M87 or the center of our galaxy within the next decade or so. But in general, that's going to be a very difficult thing to try to do in the long term. Yeah. Any other questions at this point? No. Okay. So we did the variability. We talked about that. And then now I believe, I just want to finish with talking about the particle jets. And so another point to make is that a significant minority of active galaxies, about 10% emit powerful particle jets. Here are two nice examples here. These are radio galaxies. These are nice radio images made with a very large array. And you can see these jets that stick out of the active galactic nucleus down there, come out to where they strike, in this case, the intergalactic medium and interact with it. And we find that in general, that the fraction of active galaxies, as I mentioned previously, in fact, that show these powerful jets, is about 10%. Yeah.
Is this 10% only for local universe?
That's a local universe number. That's a local universe number. And furthermore, that's a number for fairly luminous active galaxies. Exactly what happens with the radio loudness behavior when you go down to very low luminosities may change. In the LLAG, low luminosity AGN regime, it's a little more complicated. But yeah, that's a local universe number. And there are claims that, in fact, it may evolve with redshift. And people have actually claimed that it increases and decreases as you go to high redshift. And I think they're still just trying to sort out exactly what happens, because there's very difficult selection effects you have to be quite careful about there. That's right. And then, and again, so these objects, the ones with the jets, with the powerful particle jets, well, these jets produce strong radio emission, typically via the synchrotron process, although there's a variety of processes going on. And these are the ones that are referred to as being radio loud. So back here, when I was talking back here, just go back a little bit, when I was talking about radio loud active galaxies or radio loud quasars back here, these are the ones that have these powerful jets, like the ones that I was speaking of, like things like that. Although these aren't powerful radio loud quasars, but they have jets like those. And these jets can be extremely impressive. In this case, in fact, this is a combined optical and radio view, of one of these systems with powerful jets. And you can see here the optical image is shown in the sort of bluish here. And so the whole host galaxy that contains the black hole is only about this size in this image. The jets are sticking far outside of the host galaxy, well out into the intergalactic medium, and are interacting with gas out in the intergalactic medium there. I'll show you one other nice example of these particle jets. This is in the nearby case of M87. Okay, this again, you've heard me mention this galaxy several times already. It's a very nearby, well-studied example of an active galactic nucleus. It happens to be the one that Heber Curtis saw this curious straight ray sticking out of back in 1918. Okay, this is what we can do today with that same object. Okay, and so here it is on large scales, imaged with the VLA. Okay, the jets are coming out. They're interacting with gas in the cluster of galaxies surrounding M87. Okay, and producing all of this sort of turbulent behavior. If you zoom in just on that part, here it is. You see the jet sticking out. Now you just pick up that little part, zoom in on that. There's the jet. Now you just cut out that little part, zoom in. There it is. Now you just cut out that little part, zoom in, there's the jet. Now you just cut out that little part, zoom in, there's the jet. Okay? And so people have managed to study the jet in M87 in great detail using advanced techniques that combine the data from many radio telescopes all together. And you can see here, well, several things. First, you can trace the jet down to very small scales. In this case, I believe you're tracing the jet down to several hundred times the event horizon size of the black hole. So the jet's being made on quite small scales. Let me just finish this. And I'll get to it. And then another point to make is that you can see that the jet on very small scales is pointing in the same direction as it is when you go out to much larger scales. Okay, and that's a remarkable thing, because if you look at the size of the jet in M87 or in objects, especially like these, okay, these things are huge. Okay, such that, you know, even if these jets were setting themselves up at a good fraction of the speed of light, it would take them 1 million years or more to get to that size that they're at, just based on causality, if nothing else. And so what that's telling you is there's something inside these active galaxies that says, I want you to shoot out a jet, and I want it to go in that direction, and I want you to keep it going in that direction for the next 1 million years. I mean, if I told you to point your arm in that direction for the next 1 million years, I think you would say no. Okay, because it's just not going to work. But something inside of an active galaxy knows, stay in that direction and keep shooting out in that direction for the next 1 million years, okay, or longer. And that's the point. There's something very stable inside of these active galaxies, some kind of gyroscope that keeps the pointing fixed in a favored direction for a very long period of time. Okay, and so that's the what I was going to say about the sort of basic observed aspects of them. And I know you had a question, so go ahead.
How will we know the velocity of these jets?
The jets.
Specifically, are most of them relativistic?
Yes. Okay. Well, there certainly are some well-studied cases like M87, where we know the jet is moving, you know, relativistically. You can see individual blobs of plasma over the years moving in M87. You can just watch them move and do it that way. Then in general for jets, we see, of course, a number of pieces of evidence, and I'll say a little bit about these later on, you know, strongly supporting the idea that they are relativistic. You see strong brightness asymmetries from one side of the jet to the other, or you see apparent superluminal motions. Those types of things also support the very high speeds.
Most of the jets we observe are relativistic?
We have pretty good evidence that in many cases the jets are, I don't know about most, yeah, we have pretty good evidence that in most cases, yeah, they're going to be relativistic, I believe. Because, I mean, even leaving aside cases where you can measure individual blobs moving along, you certainly see strong brightness asymmetries from one side of the jet to the other being a common property of jets. And that relies upon, you know, relativistic beaming. Yeah.
Even for M87, close to the black hole, the velocity is only about 0.3 or 0.4.
Okay, I guess I would call that relativistic. At some level, you can decide what you decide to call relativistic or not. Yeah, yeah, that's right. Yeah. Okay. Yeah, go ahead. You've got a question. Yeah, absolutely. Previous slide, sure. This one, yeah. Two yellow. You mean over here? I mean, why are those yellow? Okay, it's a color. What they're doing is here they're using the colors to denote intensity, And it's a color scaling. And basically where it turns yellow, that's the regions where there happens to be the very highest level of intensity. They're using color here to mark intensity. It's not a true spectral color or anything like that. And so what's happening here, to be a little more specific, and I'll say more about this later on, is these particle jets are flying outward through regions where they have previously evacuated all the matter that was there. And ultimately, they get to a region where they have yet to clear it out. And that's where the jets strike the gas that's there. And that's where you get these very bright emission hotspots. That's right, yeah. OK, so that's oh, yeah, go ahead. This one? That one? Or even before?
I mean, the emission, the broad emission.
Uh-huh. I'll go back to that. Like here, yeah. You want that one? OK. Oh, you want this? Oh, the broadband. OK. Yes, we do see radio emission from radio quiet AGN. Yeah, so his question is, so yeah, radio quiet AGN are not radio silent. They do produce some jet power. And in fact, if you go and study some radio quiet quasars in great detail in their nuclear regions, you actually can see little jets. Little jets. In some cases, there's even been a case of a radio quiet quasar where people have seen relativistic motions of that jet over time. And so even the radio, at least, let me be careful, at least many of the radio quiet quasars do produce little jets. But somehow these jets are vastly smaller than the dramatic cases like those. Yeah.
For all AGN, even they are real quiet, I mean, how many fractions they can produce radio emission?
What fraction of radio quiet quasars produce some radio emission? Yeah. Well, it's very difficult to know because, it's very difficult to know because when you get down, typically these types of diagrams are constructed using data from wide field sky surveys. And the problem is for objects that are very radio weak, getting an exact limit on how many of them have some radio emission, well, you stop detecting them. And so you can say, I can put an upper limit upon the radio luminosity as this, but that doesn't prove there isn't some radio luminosity there. And so what one could do, if one really wanted to answer that well, is you could take a large, well-defined sample of objects, and you could go back and do targeted radio observations of all the ones that weren't detected, to try to detect them all, and then you could firm that up. But I know it's a substantial fraction of even the radio quiet objects show decent radio emission. Yeah, that's right. So is this a good place to take a break? Because I think this is a natural place to take. You normally break it in two, right? So I think this is a natural. You've heard me go on for an hour now. So how about I'm happy to answer any more questions. And then let me just say what we'll then, after the break, we'll come back and we'll talk more about how do all these observed properties that I've been talking about, how do they fit in a general sense, to the black hole plus accretion disk model, and we'll then talk about finding active galaxies and about the terminology for active galaxies. Okay, thanks. Should we start? Okay, I think we're going to start up again. And so we're now going to continue, and we're going to talk about the basics of the black hole plus accretion disk model. And this will be in a very basic general sense. And you'll hear a lot more of the technical details about accretion disks and so on from the theoretical talk this afternoon, as well as from some of my future talks. So we've just covered these basic observed properties of active galaxies that need explanation. We talked about how they have a very broad range of luminosities, reaching very large values. We talked about how you see strong and broad optical UV emission lines. We talked about emission over a very broad band. We talked about the variability. And we talked about the particle jets. Does anybody have any further questions about those from your just your discussions during the break about those basic observed properties, or do you all feel pretty good about those? Seems like everyone's good. Okay, so now we're going to try to put these in the context of the black hole plus accretion disk model. So let me just say a few general words about what do I mean when I talk about this black hole plus accretion disk model. Well, the basic idea is that we believe that these active galactic nuclei are representing accreting supermassive black holes, okay? And we're talking here in general about black holes that are range between maybe down to like 10 to the 5 solar masses on the low mass end, and on the high mass end extending up to like 10 to the 10 solar masses, okay? And these are radiating tremendous amounts of power, ranging from, again, at the low luminosity end, maybe 1,000,000 times the luminosity of our sun, and at the high luminosity end, going up to like 10 to the 15 times the luminosity of our sun. Okay, so that's sort of what we're talking about when we think about this model. And that black hole is, again, it's accreting, and the idea is it's accreting from a disk of material. Now, why exactly is material in the form of a disk? Well, you're going to hear about that from the lecture this afternoon. Okay, it basically boils down to angular momentum effects, okay, holding the disk in one direction and it can flatten in the other. Okay, and we believe that this accretion disk, first of all, is a multi-temperature structure, having higher temperatures in its central regions, lower temperatures as you move outward, and that alone can partly account for the broadband emission that we see from many of these active galaxies. Certainly not entirely, but partly that can help. Instead of being, like our sun, which you can characterize pretty well with the first order with a single temperature, these disks are inherently multi-temperature structures. And then the optical UV emission lines we've talked about, well, it's believed those come from, high-speed photoionized gas. Again, if you have this brilliant source of radiation, it will shine out upon whatever gases it is there and cause it to produce emission lines, if it's nebular gas at least. And you could have irradiation of the outer parts of the disk, and many people think that some of the emission lines we see from active galaxies are coming partly at least from the disk. And you could also have emission formed for if you have a wind flowing outward. That's what this sort of stripy stuff here is representing as an outflowing wind. If you irradiate that, you could produce absorption lines in that, and also, of course, emission lines in that same structure. Okay, and you may have emission lines coming from that, and you also have made emission lines from whatever clouds happen to be present in the central regions. So that's where we believe the emission lines come from. A few more relevant points. One thing I want to just stress is that black hole accretion is very efficient. Okay, in terms of if you have a certain amount of matter and you have to turn it into energy, luminous energy, black hole accretion is a good way to go. Okay, and this plot here sort of illustrates that. So this is just, again, looking at the sort of the fraction of E equals mc squared that you can extract from matter. Well, one way you can extract energy from matter is you can burn it, or you can use chemical processes upon it. You can burn some coal, you can burn some wood, or alternatively, you can eat some food and metabolize it inside yourself to derive energy. Those types of processes produce power, but they're not very efficient. They're about sort of 10 to the minus 8% in terms of efficiency, turning the rest mass energy into power. Alternatively, another way you can extract energy from matter is you can fusion burn it. Nuclear fusion can give you of order sort of 0.7% in very round numbers of the rest mass energy liberated as power. Accretion disk emission can give you considerably more power, depending upon the details of the accretion, depending upon whether the black hole is spinning or not. You can get something like 5 to 30% of the rest mass energy liberated as power. And that's a really good thing, going back to the tremendous luminosities, reaching the very large values. For powering things like luminous quasars, there's a real challenge just to get enough energy to power them. If you wanted to propose, for example, that let's say you wanted to propose that you think that the luminous quasars are powered by big coal furnaces in the centers of galaxies. Well, you can quickly work out how much coal it would take, and you would need to burn many galaxies worth of coal to keep the thing going for any appreciable amount of time, just because it's not an efficient enough process to do it. So the point is, if you want to generate a sufficient amount of energy to keep one of these things going, you need a very efficient process, and black hole accretion gives you that. Again, just in a very broad sense, without lots of technical details. Now, going back to the broadband emission, we believe that for the case of a supermassive black hole, you can do pretty well explaining the emission ranging from the infrared up to about the ultraviolet from the accretion disk itself. Going beyond that, however, going to the X-rays or going to the radio requires additional things to be going on. Okay? The X-rays are not made to very efficiently, at least in your sort of standard textbook idea of an accretion disk. Other things have to be operating. And in fact, the X-ray emission, we believe a lot of that comes from a coronal structure associated with the accretion disk, kind of like how the sun has a corona. You all know the sun has a corona. Here's a beautiful X-ray image of the solar corona from the Yoko satellite. And these are coronal loops of several million Kelvin plasma sitting up above the surface of the sun that's producing the X-rays. Here are some beautiful solar coronal loops you can see there. Okay? We believe that accretion disks have coronal structures as well. The exact details of this corona are not well understood. I'll say more about that later on. But the idea is you have a magnetic field threading the disk. That magnetic field gets twisted up owing to the disk's high-speed rotation. Perhaps some of the magnetic field lines pop up out of the surface of the disk, release energy up there, and lead to the formation of a coronal structure. We believe such a structure, something like that, is what's responsible for making the X-ray emission we see from these active galaxies. The disk itself is too cool, so you need this additional component doing it, the so-called corona. And we believe that this corona is very hot. It has a temperature of like 150 keV. Okay, that's of order like 1 billion Kelvin in very round numbers. So it's extremely hot. Much hotter than the solar corona, which is like 1 million Kelvin. Okay, so this is a much more extreme coronal structure than the solar corona, but it is broadly similar to first order. And the idea is the X-rays are then made by Compton upscattering in that structure. So whatever photons come from the disk, come up from the disk, they get Compton scattered by gas in the corona. And that boosts the photons, which may have started as optical photons or ultraviolet photons, boosts them up to X-ray energies, and that's what leads to the X-ray emission. You may get some very low energy X-ray emission from the disk component as well, or may not, depending upon the system being studied. But that's the basic idea for the X-ray emission. And if you put those things together, the emission that you expect to get from an accretion disk, and again, you're going to hear a lot more about that from the theoretical lectures, and you put that, which is shown here, this is sort of the emission you expect from a standard thin accretion disk, and you combine that with the emission from a corona, you can get emission spanning a very broad range of wavelengths or frequency or energy, as shown here. Okay? And we believe that those basic structures do a pretty good job explaining the emission, at least running from sort of the optical UV up to the X-ray. Now, how do you go further down to lower energies? Okay, well, there's a couple things there. First of all, we believe that there are many gas components present in these active galaxies. We've already talked about the disk. We believe there's other things that are there also. And this is hardly surprising. If you look at the center of our own galaxy, here's a beautiful mosaic of the center of our own galaxy, combining data from Chandra, Hubble, and Spitzer. And you can see there's all sorts of complex filamentary structures in here. And there's, I don't know if they're labeled here, but there's large molecular clouds forming stars in the central regions and so on. There's a lot of other gas components present there. And these often contain dust as well. Okay? And so when you have radiation being formed from the accreting black hole, some of that radiation will shine out upon whatever matter is out there, okay, irradiate it, okay, heat it up, okay, and will then cause it to produce, ultimately, thermal infrared emission. And as I had already alluded to, we believe oftentimes that this material may be in the form of a sort of a toroidal structure that does does a great deal of obscuration of the direct emission that would otherwise be able to get out from the active nucleus. And so the idea is whatever obscuring material is there, whether it's in a torus or in some other form, radiation from the central region shines out upon this gas and dust, heats it up, and it emits out in the thermal infrared. Okay? And that material likely produces much of the infrared emission, essentially as reprocessed waste heat. You took the original sort of short wavelength radiation and re-radiated as longer wavelength waste heat from dust. And we believe that component produces a lot of the dust emission. And so here's sort of a broadband schematic. Up at the very highest X-ray energies, you have coronal emission. Then in sort of the ultraviolet and the optical, you have the accretion disk. Going further down into the infrared, you have dust emission from whatever obscuring material is present in the central regions. And then down, as you go down to radio emission, well, in radio loud quasars, you'll have powerful emission from a strong jet, okay? And in radio quiet objects, as I mentioned already, sometimes they have little weak jets. You may also get radio emission from a corona. Some people have proposed that. You may get also radio emission from the host galaxy. So that's what may produce the radio emission here. And those are the basic ideas that explain the very broadband emission that we see from these active galaxies. Okay, any questions about that? There's a range of components there, but that's how we explain this very broadband emission. It's totally unlike what you see from stars. Okay, now to say a few more words about the variability. First of all, the variability still remains not that well understood. So let's just admit that up front. Okay, but we do have some useful points there. First of all, the black hole plus accretion disk model has the favorable aspect, in fact, that the accretion disk is expected to have about the correct size to explain the observed variability timescales. In other words, we can work out, given the black hole masses I was talking about, how big the black hole will be, how big the accretion disk will be, okay? And we find that the variability timescales actually agree pretty well with the sort of predicted size. And moreover, in fact, people have studied how the variability depends upon luminosity. And you find, speaking in very broad terms, that in general, more luminous objects, in many cases likely corresponding to more massive black holes, have less variability than low mass objects, corresponding with the idea that the black hole gets bigger with mass, exactly as expected. Okay. And furthermore, as you probably recall, I also had mentioned that the variability gets stronger as you go to higher and higher frequencies. And that also makes sense in the context of a multi-temperature accretion disk model, for example, because, of course, like the ultraviolet is being made on a smaller physical scale than, say, is the optical, and on an even larger scale will be the infrared. And so you get the correct scaling with wavelength of variability, such that you should expect stronger variability from higher frequencies. So that fits together quite nicely also. Okay, however, all those positive things being said, at a fundamental level, the physical origin of the variations remains poorly understood and is still the subject of very active study. People are now performing, and I'll allude to these a little bit more later on, are performing large supercomputer computations where they put in all the equations of magnetohydrodynamics, and they try to simulate accretion disks, the emission from accretion disks, and how that should change over time. And those simulations indicate several possible causes of the variability. You may have local random variations in the amount of dissipation. That is, how much of the gravitational potential energy being lost gets turned into radiation. That may vary locally, and that may cause some variability there. You may get non-axisymmetric structures developing in disks. Disks may have hotter regions and somewhat cooler regions. And when you move those around at high speeds, you may get variability in that way. You may also get global precession of tilted accretion flows in some cases. And things like that are thought to be responsible for explaining a lot of the variability. However, a deeper understanding of that is going to require further simulation work, I believe, both that models the dynamics of the accretion flow, and people are making really good progress with the dynamics right now, as well as the full thermodynamics that goes on in the disk. And that's much harder, and people are making slower progress in that regard. So that's something to say about the variability in general. I will also note that, of course, there are other natural causes possible causes of variability. In some cases, over, again, fairly long time scales, you may get modulation of the accretion rate. That may change over time. In some cases, we actually see also variable obscuration. Matter may pass in front of the direct line of sight to the black hole and then move out of that line of sight. That can cause variability. Or in some cases, you could also have microlensing going on, where the accretion disk itself gets microlensed by intervening stars. And so those could be other possible causes of variability. But the variability is a complex thing. The black hole model has a lot of positive aspects to it, but there still needs to be further work to understand the variability. And then the particle jets, they were in sort of a similar situation. I can say a few positive things, again, about the black hole model in the context of particle jets. First of all, we believe that many supermassive black holes are rotating, are spinning. And you'll recall that I told you we need this very stable gyroscope to keep the jet pointed in the same direction for millions of years. Well, a black hole that, say, weighs 1 billion times the mass of our sun, that's spinning at a good fraction of the speed of light, gives you a really excellent gyroscope to keep a jet pointed in the same direction for a long time. Furthermore, we do expect relativistic motions close to the black hole, and we furthermore believe that there are magnetic fields. You remember I was already alluding to magnetic fields in the disk back here when I was talking about this coronal structure. We believe there are magnetic fields playing an integral role in even allowing the accretion itself to proceed. And so we believe that magnetic fields play a role also, and somehow via magnetic processes, some of the inward flowing matter gets diverted outward again in the form of these jets. And exactly how that works, well, that still is still not that well understood. I'll talk more about that later on when I say some more things about jets. But you have the positive aspects in the black hole model of relativistic motions. You have this relativistically deep potential well. You expect there to be magnetic fields and plasma linked to those magnetic fields, and you have the stable gyroscopic action of a spinning black hole. All those things are positive aspects for the black hole model, at least in having a chance to explain jets. Okay, so now I want to move on and say a few words about finding active galaxies. How do we actually find these things, okay, out in the universe? Well, there's a number of ways to go about that. In fact, there's a real need to use multiple methods to do it. In fact, so there are many methods for finding these active galaxies. Some are as old as the subject itself, okay? And all the methods we've come up with for finding active galaxies out of the universe have positive aspects as well as negative aspects. They can have real limitations in some cases and real selection effects, okay? Some, I would argue personally, I think that some are likely better than others. Some are more effective than others and give purer samples of active galaxies than others. I personally like the X-ray method pretty well myself, but even that's not perfect. And so for a complete census, you really want to apply as many methods as possible so you can cross-check the methods against each other and ultimately get a complete census of all the black hole accretion that's going on out in the universe. Okay. And we believe right now that our current census of black holes, accreting black holes out of the distant universe is, while not perfect, certainly is sufficient to answer many of the key questions about AGN populations. How common are they in general? How much black hole growth has occurred in the universe? We think we can answer those things pretty reliably from the surveys that we've done so far. Okay, and so now I'm going to talk about the methods that are typically used to find these active galaxies, because this is a really important aspect of the subject. Well, one of the ways that we find active galaxies, one of the first ones that was pioneered, was via the use of optical and ultraviolet colors. And here, what you do is you exploit the fact that the emission from the accretion disk that I was just talking about back here generally has higher temperature overall than that from a star. Okay? You get a lot more emission, for example, in the blue and in the ultraviolet than you get from a typical star. Now, there are exceptions. Things like white dwarfs can be very strong emitters in the ultraviolet if they're very young. But in general, that's true. And so you can do a pretty good job separating quasars or active galaxies from stars using ultraviolet excess emission. And so one thing that people do is they look for point sources, point-like sources that are brighter in the ultraviolet than normal stars. And that's what's in fact being shown here. Here is a quasar spectrum here going out toward the ultraviolet compared to stars. And you can see quasars show this ultraviolet excess emission compared to a typical star. And so that can let you home in on the active galaxies. And that works pretty well out to a redshift of about 2 to 2.5. Okay. Out at higher redshifts, things are a little more challenging because you start getting a lot of absorption by the intergalactic medium. Okay. And that makes quasars, well, that absorbs away, okay, a lot of the typical emission you'd be trying to see. And in fact, then quasars get very red in the blue part of the spectrum, but they can still be separated out because they have these very distinct colors due to the imprint of the intergalactic medium absorbing their light, and it still makes them stand out from stars. And so people typically make diagrams like this, where they make a plot of one color, in this case the G minus R color, versus another color, the U minus G color, okay? Or here are other ones. Here's G minus R versus R minus I. Here's R minus I versus I minus Z. And you can see plots here where the stellar locus, where all the stars live, are shown in black. And you can see that quasars, especially as you go out to the higher redshifts, separate themselves out from where the stars typically live. And so you could home in on objects in that part of color space, and when you go and investigate those objects, you find out they're typically quasars, in this case at high redshift. And this continues as you go out to high redshift. So by using all these colors together, this one, that one, you can do a quite good job homing in on which objects are the quasars and which ones are the stars. So that's one way that people find these things. And this works pretty well, at least for many quasars. In fact, most of the quasars that we found have still been found with this method, with optical UV color selection. Okay. This method works the best for unobscured quasars. When you have a bunch of reddening, if you have a bunch of dust, for example, obscuring the quasar at some level, that will redden its spectrum, will absorb a lot of the ultraviolet light, okay, and that will mess up the method to some degree. So that's one way that this method will fall down. Okay, so you have reddened quasars, you're going to have more trouble finding them with the optical technique. Furthermore, well, this method, you can see right from the start, you're looking for point-like sources in general. So furthermore, at lower AGN luminosities, you're going to have the host galaxy producing light. They'll no longer appear point-like, and it will also affect their colors. Okay? And so that will cause a problem for optical UV AGN selection down at low AGN luminosity. So this works best in the regime where the light associated with the active nucleus is much more powerful than the light from the host galaxy. When you go down to lower luminosities, it becomes more problematic. And people have also come up with other methods in the optical UV using things like objective prism surveys, where they get low-resolution spectra of many, many objects. Is another technique for finding them. But that's how we find things in the optical UV. Okay, so that's one technique for finding them. And again, this has been very successful, as I mentioned. Here's a nice plot that in this case shows for a large number of Sloan quasars, their luminosity, in this case in the I band, versus their redshift. And you can see that they've done pretty well getting large numbers of quasars, okay, with this technique. In fact, Sloan has now identified with the optical UV technique more than 200,000 active galaxies, which is quite impressive, okay, to have such large samples. They certainly didn't exist back when I was a graduate student, but the growth there has been tremendous over the past decade or so. And as you can see, these 200,000 objects, they span a broad range of luminosity and of redshift. Okay? And another point just to note for now, and this is something that will be relevant for all the surveys I'm talking about, is you almost always get this strong correlation between luminosity and redshift in your sample. And that's just because objects that are low luminosity and high redshift are very faint. And so it becomes hard to find them just practically. And so that you always have to be careful when you're seeing correlations, for example, in a survey that you've done. You know, let's say that you see some property appears to be changing with redshift in a sample of quasars. Well, how do you know it's really redshift that's doing it and not luminosity, given that luminosity and redshift are so strongly correlated? So this is an inherent problem you always have to be careful with in this survey's work. And it's imposed by just this basic fact here. Okay, so that's optical UV surveys. Now let's talk about X-ray surveys for active galaxies. So we know that X-ray emission is nearly universal from active galaxies. I'll say more about that later on, but just take it as a fact for now, that X-ray emission appears to be nearly universal from active galaxies. And so we've used this fact quite successfully to go and find active galaxies in the X-ray band. Here, for example, is a very deep observation made with the Chandra X-ray Observatory. This is a 4 million second observation with Chandra, okay? And you can see all these point-like sources, okay, in here. And these are all active galaxies. The vast majority of them, not all, but the majority of them are active galaxies, okay? So this is another good way to find active galaxies. And of course, this one is, all this work was led by our conference organizer here, so he can tell you more about it if you like. And the X-ray studies have a number of positive aspects. First of all, X-rays are a very penetrating form of radiation. So for the same reason that your doctor uses them to study your bones, we use them here to find obscured active galaxies in the distant universe. In other words, if you have an obscured system, well, X-rays, being very penetrating, can often get out, whereas the optical UV emission can't get out. That's what I was talking about back here when I talked about the reddening causing trouble for optical UV selection. And you can often get X-rays out when you can't get the optical UV out, and so that lets you home in on active galaxies. And then furthermore, X-rays tend to maximize the contrast between light associated with the black hole and light associated with the host galaxy, okay? And X-rays let you home in on the black hole light preferentially and reduce the host galaxy light. And so that gives you another way to home in, even on low luminosity active galaxies, where otherwise the host galaxy would be troublesome. Okay? And we can now find, with these surveys, we can find obscured active galaxies and low luminosity AGNs quite reliably, okay, even out into the distant universe with these X-ray surveys. Okay? And we now, as a result of these basic positive aspects of X-ray surveys, we now have a wide variety of X-ray surveys that have been done, ranging from shallow surveys over the entire sky. For example, the ROSAT Observatory, which many of you have probably heard of, did a very sensitive all-sky survey. And there's a mission coming up called eRosita that some of you have heard about that's going to do a much more sensitive all-sky survey of X-ray emission. And that's one extreme, is a wide all-sky survey. And then this plot here is showing the other extreme, where you do an extremely deep, small area of sky survey, a so-called pencil beam survey, to find active galaxies. And using all those surveys together, ranging from the very wide all-sky ones to the very deep, narrow field ones, is how you get a full understanding of all the black holes out there from an X-ray perspective. We also have done gamma ray surveys for active galaxies. Here's a nice plot. Many of you have heard of the Fermi Gamma Ray Observatory. Fermi is still operating, continuing to do a very sensitive survey of the whole sky in the gamma rays, and it has found quite a few point-like sources up at high galactic latitudes that, when followed up, are found to be active galaxies. Now, Fermi finds a very specialized subset of the active galaxies. It finds these ones called blazars that I mentioned previously. Do you remember how I told you how you can have these radio jets in active galaxies, and these radio jets will sometimes be pointed in the plane of the sky, or sometimes maybe pointed exactly along our line of sight. The ones where you have the jet pointed almost exactly along our line of sight, those are the ones that are referred to as blazars, and those are the ones that you will most effectively detect up in the gamma rays, for example, with Fermi. So Fermi has done a wonderful job finding large numbers of new blazar-type objects, which are rare objects. They're not demographically that important in terms of absolute numbers, but they're physically very important because they let you study jets from, literally from a new angle, that along your line of sight, okay? And so here's a little histogram here that shows what Fermi has found. And you can see the majority of the objects being found by Fermi, something like 60% of them, are blazars. And we suspect that a good fraction of these unknown objects are furthermore going to turn out to be blazars as well. So that's what you can do in the gamma ray. Now let's go to the infrared. Infrared selection has also been very effective for finding active galaxies. People have developed now several methods for the effective selection of active galaxies in infrared data. And these typically rely upon making these color-color diagrams, similar to what I showed you already in the optical. So here's a color-color diagram comparing emission at 3.6 microns versus 4.5 microns versus 5.8 minus 8.0 microns. And active galaxies often stand out quite distinctly in certain parts of this diagram, such as over here. Okay. And so several methods have now been developed for finding active galaxies with infrared. And here, again, what you're often homing in on is you're homing on seeing that waste heat coming out in the infrared from whatever obscuring material is present in the central regions, getting heated up and re-emitting it, okay, via dust emission. And so that's what you're homing in on there. And the infrared is not perfect, but it's relatively resistant against obscuration effects, similar to the X-rays. And so the infrared and the X-rays often go very well together in letting you home in on the population of obscured active galaxies that you can't find from optical surveys, okay? And in fact, the infrared techniques claim, and sometimes I believe them and sometimes I don't. As an X-ray astronomer, I stand up for the X-rays pretty hard. But they claim that sometimes they can even find AGNs that are missed in the X-ray surveys. And if so, that's very important. And it's telling us new things about the AGN population, okay? And the one challenge for the infrared, however, of course, is as you go down to low AGN luminosities, there you get into real troubles because you get a lot of contamination from star-forming galaxies and so on that prevents you from homing in on the AGNs effectively. So that's infrared selection, another major technique. And then radio surveys is another critical technique. In fact, as you probably recall, I mentioned, many of the first quasars were found via radio selection in the 3C catalog of radio sources made by astronomers at Cambridge University when they were first doing radio surveys of the sky. And here is just a typical image from the first survey, and you can see that typically these surveys are pretty bland, not a whole lot in there, but there are these point-like sources, and you go and follow those up, and you find that the majority of those are radio-emitting active galaxies, okay? And again, we find that when you do such surveys, about 10% in very round numbers of active galaxies are radio-loud sources, and that sensitive radio surveys are now able to detect not only the radio-loud AGNs, but at least many radio-quiet AGNs also. And because stars are usually very weak radio sources, you have little stellar contamination, so you really home in quite effectively at least on the 10% of objects that are radio loud and some of the radio quiet ones with these radio surveys. Furthermore, because you get excellent positions generally in the radio band, you're able to do efficient follow-up studies to match the radio source to its corresponding optical source and get a spectrum of it so you can identify it reliably. And so those are the positive aspects of the radio survey. The sort of downside of radio surveys is they're often quite incomplete, again, owing to the radio quietness of many AGNs. And so certainly the radio quiet population is discriminated against by radio surveys unless you get to very good sensitivity. And in that case, you can home in on those as well. And I think I'm going to wrap up today then just by saying a few words about terminology. Okay? And so active galaxies, as you've noted already, have quite colorful names, quasar and blazar and things like this. And in fact, people have noticed this, and in fact, they've made comic books with some character named Quasar who can fly around and do things. And here's a card that was named after the quasar, and they put something here in the background. That's not really a quasar, but they thought it looked neat, and so they figured they could sell cars that way. And so anyway, these names have caught on in popular culture, and there's a lot of names flying around. And here are a bunch of them, and you've heard me say some of these names already, okay? You've heard me talking about a safer galaxy or a quasar. Where's have quasars in here? They're radio loud quasar or radio quiet quasar. And you've heard me talk about a blazar. You've heard me mention a radio galaxy. And there's all sorts of names running around out there. And unfortunately, AGN terminology is somewhat of a mess, okay? And I'm sorry for that. If we could start over now, we could do a much better job. But again, remember how I sort of mentioned at the start how science often doesn't proceed in a nice, orderly, organized, linear way. But people go off in a direction and realize they were wrong, and they go back and go in some new direction, and they forget about somebody who found something earlier. This is how things often work. And because of that history that I told you about in the first part of the talk today, this has led to AGN terminology being somewhat messy. Because it was developed as people were first coming to understand AGNs, they didn't have a complete understanding of the whole phenomenon when AGN terminology was being set. And so as a result, a lot of names have been come up with that have stuck, and it's too late to go and fix it now. And so you just have to learn the terminology for what it is. Okay. And I will say, however, that via subsequent unifications of ideas, and I'll talk about these in much more detail later on, some of this terminology has been seen not to reflect real internal physical differences, but rather for other things, such as the degree of obscuration of a given source. Okay? So a lot of this terminology, in fact, these things, when you see, for example, a Seyfert 2 galaxy, okay, as opposed to a Seyfert 1 galaxy, or if you see a Type 2 quasar as opposed to a Type 1 quasar, a lot of that just reflecting obscuration. And I'll say much more about that later on. Okay. Anyway, so there's a lot of historical baggage, and that doesn't have a lot of physical importance. And I would say even given that, even today, there's fairly sloppy usage, unfortunately, of AGN name types in many cases. For example, people came up with this definition for Type 2 objects originally, which hinged upon details of the optical emission line properties. But today people use this Type 2 terminology in all sorts of inconsistent and irregular ways that make it a real mess. Okay? And similarly, blazars. I mean, people use this term blazar in all sorts of inconsistent ways. And in fact, it's sort of interesting that the original name blazar was come up with by some guy in an during conferences. They often have like an after-dinner speaker. And this after-dinner speaker had drunk a lot of wine already during the conference dinner and was up there kind of woozy, and he started just saying all sorts of crazy things and said, why don't we rename these things blazars? And people loved it and started applauding, and so that's where the name blazar came from originally. You can read about the story in Krolik's book if you're interested. And unfortunately, but the name caught on, and there we are. Okay? And so again, it's too late to redo the terminology in a more sensible way, so unfortunately you'll just need to learn it. And so there are a few key classification sort of variables that we use when we try to classify these AGNs. One key classification variable is the strength of the radio emission. And I've already mentioned that. You've heard me talking about radio loud quasars versus radio quiet quasars. People have come up with a more formal way of distinguishing that. They typically look at the ratio of the relative amounts of radio power to optical power, and they use that to separate out objects into being radio quiet and radio loud. Okay, that's one key way that we do it. Another big classification variable is the optical and UV emission line properties. That's another way that we classify these AGNs. And this leads, for example, to the Seyfert 1 galaxies versus the Seyfert 2 galaxies. Seyfert 1 galaxies are ones that show these very broad lines that I talked about, as well as the narrower lines, whereas the Seyfert 2 galaxies only show the narrower lines. Okay? And type 1 quasar versus type 2 quasar. Well, that's the same thing. The type 1 quasar show both the broad and the narrow lines. These ones show only the narrow lines. I'll say much more about that later on. Similarly, people talk about broad line versus narrow line radio galaxies, again, relying upon the optical UV emission line properties. And then in addition, people realize that, well, this simple approach of breaking everything down into type 1 and type 2 doesn't really fully explain the diversity of the phenomena. The same way that, for people, for supernovae, I mean, astronomers can only count to 2, right? You have to remember that. They only count to 2. And so when they find supernovae, they first say there's a type 1 supernova and a type 2 supernova, right? But then they realize, oh, actually, supernovae are more complicated. So now we have type 1a and type 1b and type 1c and type 2 this and that. And they start breaking it down into these subgroups. It's the same thing for active galaxies. We've realized that active galaxies are more complicated, and you can't always break them down simply into a type 1 and a type 2. And in fact, we now have intermediate Seyfert types, where they talk about a type 1.5 Seyfert galaxy, or a type 1.8 or a 1.9 Seyfert galaxy. And these have very specific meanings that you can look up in the books that I referred to. Okay? There are other things as well. There are so-called narrow line Seyfert 1 galaxies, which is another classification that comes from optical UV emission lines. There's things called BL-lax. Those are objects that don't show any obvious emission lines, but we're still convinced are AGNs. Okay, I'll say more about them later on. That's another example of optical UV emission line classification. People also use other classification variables, things like variability, and things like ultraviolet absorption line properties. Those are other ways that we classify things. For example, you heard me earlier on refer to a broad absorption line quasar. Remember that quasar that had those huge absorption troughs being cut out of its spectrum? That's an example of classification based on ultraviolet absorption line properties. And then luminosity is also often used in classifications, largely for historical reasons. That is, when people were first found these objects, some people, Carl Seyfert and colleagues, had found Seyfert galaxies. And then later on, Martin Schmidt and collaborators found quasars, right? And then there was this question as to, well, are Seyfert galaxies fundamentally different from quasars or not? And they didn't know at the start, and so they kept the names different. Okay? Today we know that, for example, this distinction by luminosity, in that particular case at least, is largely historical. That is, we believe that Seyfert galaxies are just low luminosity versions of quasars, but essentially all the same physical processes are operating in Seyfert galaxies that are operating in quasars. You see the idea there? It's really a continuum of properties. There's not two distinct groups, Seyfert galaxies versus quasars. It's just quasars are more powerful than Seyfert galaxies, but otherwise they're fundamentally the same things. Okay. And so people have broken all this down. Here's a classification table if you're interested. If you ever need to go look it up, you can look in Krolik's book, which has this nice table that breaks things down. And here are the various classification variables. Here are the various types. And you use this table. And if you follow this table strictly, you can assign a given object to a given type. Okay? And you can, again, I'm not going to go through all the details here. And in fact, people also make these little diagrams trying to separate out AGNs. And here, this one works pretty well. If you just consider this three-dimensional plot of radio power versus emission line width versus variability, you can do a pretty good job separating out AGNs reliably. And you can see here such that objects that are really powerful in the radio band are things like radio galaxies, narrow line radio galaxies, broad line radio galaxies, radio loud quasars. Okay? And if you go down to objects that have low radioluminosity, then depending upon emission line width, they break down into the objects that only have the narrow lines, the Seyfert 2s, and the objects that have the broad lines and the narrow lines, the Seyfert 1s and the radio quiet quasars. And then if you go over to objects that have extreme variability and are highly radio loud, you end up with things like BL-lax and optically violently variable quasars. And those two together are what that drunk conference speaker proposed to call blazars, and that's what caught on. Okay, so those are called the blazars. So anyway, that's the idea. And again, a lot of this terminology is historical baggage. And we've also come to realize that a lot of it is just due to the level of obscuration. And here's a plot that illustrates that. I'm not going to go through all the details now. I'll say much more about such plots later on. But basically, we know now that there's a lot of obscuring stuff in the centers of active galaxies. And we know, at least in some cases, this obscuring stuff is roughly equatorial in nature. And so people often describe it as being a so-called torus. And this plot is sort of showing a cut-through diagram of that torus. Here is the torus here, okay? And the black hole is down in here. Here are emission line clouds and so on there. There's a jet. And so first of all, let's focus on the bottom part of this diagram, which is specific to the radio-quiet active galaxies. There, we have objects that show broad lines and narrow lines. And those are the so-called type 1 objects, such as Seyfert 1 galaxies, where you can look down into the emission line regions quite directly and see all the emission lines, including the very broad ones. And other objects, the so-called type 2 objects, where your line of sight is obscured by that material, so you can't see a lot of the broad line emission. That is an example of classification by just the level of obscuration that's there. In other words, we don't think, at least in many cases, that Seyfert 1 galaxies and Seyfert 2 galaxies are fundamentally different things. We just think that they have different levels of obscuration. It's fundamentally the same thing. It's just obscured to a different degree in one object versus the other. Okay? So that's an example of orientation-based unification. And we have a similar type of thing. It's a little more complicated going on in radio loud objects, shown in the top part of this diagram, where you have narrow line radio galaxies, where you only see the narrow lines because the broad lines are obscured by the torus. You can have broad line objects where you can look down here. And then you can have objects where you're looking right into the jet, and those are the blazars, and so on. And again, there's a number of complications there, but that will do for now in terms of describing this, that you can have these orientation-driven effects. And so then just to end, I'm going to just go through a nice set of plots that I'm going to use throughout the rest of the lectures on the so-called AGN powers of 10. And so some of you have probably seen the famous Powers of 10 movie. If not, I encourage you to go Google it. It's a very nice movie where they sort of show, well, two people at a picnic, it starts with, and then they zoom outward and outward and outward, showing, going out to show the whole Earth, and then to show the whole solar system, and then moving out to show the whole galaxy. And then they zoom all the way back in, zooming down in upon the man's hand at the picnic, and they zoom in upon the atoms in the man's hand. And well, first they start with the molecules and the atoms going all the way down to the quark level. It's a nice movie to watch, and it sort of shows a wide range of scales and how your perspective can change with scale. And one of my colleagues, a collaborator named Pat Hall, has made a very nice set of these powers of 10 diagrams for active galaxies. And so I'll just flip through these here quickly, because they sort of put a lot of information together quite compactly. And so this is a plot showing just the black hole region. And here it shows radius in units of gravitational radii, which are defined like that for a black hole. Okay. Here's the inner part of the accretion disk here. And up here, it puts it in context. It puts it for a billion solar mass black hole. It puts it in comparison to the solar system. So here's Jupiter, Saturn, Uranus, Neptune, Pluto. Eris is out there, and so it puts it to scale. Okay, and so you can see that even for a very very massive black hole, you're talking about the inner part of the accretion disk just being somewhat larger than the size of our solar system. Okay. So that's the smallest scale, and you can step out a little bit, and here's the next plot here, and here's the next one still. And this one here now shows radius in units of AU along there. Here's radius in units of gravitational radii. And here's the black hole in here, and here this is the X-ray emission region where that coronal structure would live that I talked about. You can then zoom out further still. Here's the region where we believe the jet is being launched. Here is the region where the disk is emitting the ultraviolet and optical continuum emission. You can zoom out further still. And now here's the jet launching region. The X-ray emitting region is down here on very small scales now. Here's the region where we think a lot of the emission lines are being formed from the so-called broad emission line region. Here's where we think this obscuring toroidal material, whatever it may be, is located. If you zoom out to larger scales still, here is where you think you may have some of these these clouds in an outflowing wind being present. Here's the inner part of the so-called narrow line region, okay, and so on. And so the idea here is you're taking this AGN structure, which is a very complicated thing, and you're breaking it down into all its component pieces. And much of what I'm going to be doing for the other presentations I'm going to give is I'm going to be giving you sort of a guided tour through the black hole emitting region, the black hole region, or the broadline region, or the narrow line region. I'll take you through a tour of each one of these parts of the AGN and tell you about it in considerably more detail, again, from an observational point of view. And there are perhaps analogies there. Here's a historical, perhaps, analogy. Have you ever read Dante's Inferno, where Dante took the vision of hell that they had at the time back in the 1300s and broke it down into all its component pieces? And here it is. And so I'll be giving you sort of a guided tour of an active galaxy, kind of like the poet Virgil gave Dante a tour of hell during his visions. And it's interesting that there may be some analogy there in the way that people tend to take something that's very complex and try to break it down into all of its component structures and so on. And if you do very well, you can then get out of hell, and you can go up through purgatory and then ultimately get to paradise, which is hopefully where we'll end up at. So anyway, that's everything for today. Thank you. Okay. Happy to answer any questions if there are any. Otherwise, we can talk later. Yeah, sure. The Fermi telescope. Yeah, I'll go back. Yeah, I'll go back to the plot about Fermi here. Yeah. Yeah. Ultimately, it's because it's very hard to focus gamma rays. Gamma rays are so penetrating that bringing them to a focus is a very challenging thing. In fact, the way Fermi detects these gamma rays is via electron-positron pair production. So a gamma ray will come into the Fermi observatory. It will strike a set of metallic foils, and that will convert the energy. That will convert the energy of the gamma ray into an electron-positron pair. And you then measure the motions of those electron-positron pair in the detector to determine, and then you work backwards to try to determine where the gamma ray came from. And the point is that you can only measure the position fairly roughly, and that makes it very hard to find a counterpart and to identify all of them. Now, Fermi is an enormous advance, however, over the previous one. The previous high-energy gamma ray telescope we had was something called EGRET, which was on the Compton Gamma Ray Observatory. And it would typically say, well, there's a source over there within about a degree or so. And it's very hard to identify it when you're given an error circle of a degree. Okay? And so ultimately that's why. They're not identified because it's very hard to get highly precise gamma ray positions because gamma rays are so penetrating it's hard to bring them to any sort of a focus. Yeah, that's right. Yep. Yes? Yeah. Ah, right. Yeah, good. Yeah, sorry, I should have mentioned that. Okay, so the Chandra Observatory, which was used to take this image here, has imaging capability that degrades as you go off axis. The imaging is sharpest on axis, and it gets worse and worse as you go off axis. And so if you go way off axis like this, these sources appear very bright, but they're not. The sources in here are just as bright, or brighter in some cases than the sources out here. It's just there's more digital ink being spent out there just because the imaging's poor. But if you actually look in Professor Jouet's paper, he actually shows a nice image of the central region. And so if you dig up this paper and look there, you can actually show a nice focused image of just the central region. You can see the source density there is very high, and there's a lot of bright sources in there. Yeah, so that's purely due to the imaging of the telescope. There's no real physical effect there. There are, however, some truly extended sources. I believe this is one example there, of truly extended sources. So not only did you detect black holes in these images, sometimes you will detect the hot gas that's bound within groups and clusters of galaxies as well. And so you'll get things like that. Yeah. Right. Anything else? Okay, well, thank you very much. Thanks. Okay, I told we should get started. Before I launch into the next presentation, are there any questions from yesterday? Anything anybody thought about overnight and realized, oh, that wasn't so clear, or I don't believe it, or whatever, that we can go through? Or are people feeling pretty good? Okay. Well, it seems like everything's okay then. So we're going to continue with our observational overview of active galactic nuclei. And you'll remember that yesterday we did pretty well. We got through the entire first chapter that I mentioned, where we had this very broad overview of active galactic nuclei. What are their basic properties in a very general sense? And then we talked about how we find them, and we talked about some of the terminology. For this lecture today, this chapter, and likely for the one tomorrow and even going into the next day, we're going to talk in much more detail about specific regions of the active galactic nucleus. And we're going to go through them in some depth to try to learn all the basic essential ideas about them. In particular, we're going to start today focusing on observations on the smallest possible scales, the regions very close to the supermassive black hole. We're going to talk about what we can measure in that region. Well, we're going to start by talking about the black hole region. Again, that's a region within 50 or 100 Schwarzschild radii of the black hole itself. What can we measure about that region? We'll then talk about the broadline region. That's the region where the broad lines seen in the optical and ultraviolet spectra are created. And we'll talk about what we know about that region and what that region's good for. That region turns out to be very useful, for example, for measuring the masses of supermassive black holes and active galactic nuclei. That's one of the key things we get out of the studies of the broadline region, our black hole masses. And we'll talk about how we do that. And then this will likely run into tomorrow. Maybe we'll get started on it today. We'll see how we do. We'll also be talking about outflowing winds. So that's what we're going to do for now. And then we'll move on again to larger scales. And we'll then have this focused lecture on X-ray surveys and what they tell us about active galaxies. So that's, in a very general sense, where we are and where we're going. So let's focus in on observations on small scales, okay? Focusing, again, on the black hole region, the broadline region, and winds. So a few general points. I've already said that we're going to be focusing on the innermost regions close to the black hole. And for purposes of sort of clarity, I'm going to start off by focusing on objects where we have a clear view of the innermost regions, because that's what we're trying to focus on today. We're not so interested today in obscuration and so on, although that's very important and interesting. That typically occurs on larger scales. Okay? And so you remember that I showed you yesterday this picture of a simple orientation-based unification model for active galaxies. And I told you how in type 1 objects, as shown here, we have a clear view from where we are down into the central regions. Whereas in type 2 objects, you have a lot of obscuring material that blocks our clean view into the central regions. And so if you want to study the central regions in the clearest possible way, you focus on the type 1 objects where you don't have a lot of obscuration, making things more complicated and complex. Okay, that's the first point. Now, however, we think that what we learn by studying those unobscured objects is broadly applicable, in the sense that if you believe those orientation-based unification models, the same physical processes should be happening in the obscured objects as well. It's just they're harder to study because there's some obscuring matter there. And so what we're going to be talking about today should be broadly applicable to all active galaxies, although it's most cleanly studied in the unobscured ones. And for simplicity, for now, we're also going to focus on the majority population of objects which are the radio quiet. You'll recall yesterday that at least among luminous active galaxies, something like 90% of them are radio quiet. Okay? We're going to focus on that majority population for now. And we will then see in the next chapter what happens when you add in a jet to that picture. It's a pretty good approximation. We believe that a radio quiet active galaxy, which is sort of denoted by the bottom part of this diagram, okay, is the simpler of the two, and that a radio loud active galaxy can be understood, at least to quite good approximation, as a radio quiet AGN plus adding a jet. Okay? And so we'll see what happens when you add that jet, and that makes things even more complicated at some level. But we're going to focus on the majority population and the sort of the simpler population today. And again, I'll say much more about jets later on. Okay. So let's go back to these powers of 10, okay, schematic diagrams that I showed you in the last presentation, where again, in each one of these, you're sort of stepping outward by about an order of magnitude in size. Okay? And so this is the black hole region that we'll be talking about, the region very close to the black hole, where you have the innermost part of the accretion disk, and where you may also, where you also have the region where X-ray emission is being formed. Okay? And then if you step outward even further, you come out to the region where the jet is likely being formed, and you then come out to the broadline region, where those broad optical and ultraviolet emission lines are being created. And we'll talk about measurements of those when we talk about the broadline region. And then on just somewhat larger scales still, you have the outflowing wind, okay, that I've alluded to a couple of times already. And so that's what we're going to be focusing on. So putting it in context, we're going to start in on the black hole region. We're then going to step outward to a somewhat larger scale, talk about the broadline region, and then we'll step out to a somewhat larger scale still and talk about this outflowing wind. So that's what we're going to be covering today. So let's start in on the black hole region, which again, by those words, I will typically mean the region within 50 or 100 Schwarzschild radii of the black hole itself, the region very close to the supermassive black hole. First of all, this is a region where we expect strong gravity effects to be present, and we expect relativistic motions to be present. And what you're seeing here is a diagram that shows the results from a detailed computer calculation that predicts what an accretion disk should look like very close to a supermassive black hole. And it has this rather strange shape. It doesn't look like a simple accretion disk like I had shown you, for example, back in this picture, back here, this one. And that's because on these very small scales, very close to the black hole, significant relativistic effects come into play that modify the emission. And for example, you can see that the accretion disk is brighter on this side than it is on that side. And that's due to the orbital motion of the gas very close to the black hole. Because the gas is moving at a good fraction of the speed of light, in its such radii, you have beaming of the radiation, the same beaming that occurs in jets and that you learned about in your physics classes is occurring here. So this disk is clearly going around this way. And so the matter over here is coming toward us. The matter over there is going away. And so the matter that's coming toward us beams its radiation in the direction of motion. And that's why it's brighter over here and dimmer over there. That's the first thing that you'll note in a diagram like this. Furthermore, you can see there's this bright emission over here. That's actually due to gravitational lensing by the black hole, which takes light paths that would have normally never reached us, and it takes that light and bends it around to where it actually reaches us. And so what this image is showing is a detailed computation where people have worked out the proper light trajectories for motions in the space-time close to a supermassive black hole. And those are some of the effects that you get. This is for the case of a perfectly smooth accretion disk. We have good reasons to suspect accretion disks are probably not perfectly smooth. And so this is actually a somewhat more realistic one where it's showing the same type of thing at a variety of different inclination angles. At inclination angles of 5 degrees there, 30 degrees there, 55 degrees there, and 80 degrees there. And you see the same basic effects are occurring, but here it's also showing the fact that the accretion disk is likely to have somewhat of a non-uniform emissivity pattern, and so you can see you get this sort of stripy behavior there. Okay? So that's, first of all, we're talking about a region where things like general relativity really matter. Okay? Now this plot here shows the schematic. This is a schematic diagram, not actual data. I'll show you actual data in a moment. This is a schematic diagram that shows the broadband spectral energy distribution that we observe from active galaxies in the X-rays. Okay? And this is covering a very broad bandpass running from about 0.1 keV down there to 1 keV to 10 keV to 100 keV or so up there. Okay, so you can see that's 3 orders of magnitude or so in energy or in frequency. Okay? And to put this into context, you're all familiar with medical X-rays for the doctor's office or the dentist's office. Medical X-rays typically have energies of sort of 50 to 100 keV or more. And so medical X-rays are up there. Okay? And we're talking about an emission band that includes the medical X-rays but also goes to considerably lower energies also. Okay? And you can see that the broadband spectrum that we see from active galaxies is, I mean, even in this sort of simplified schematic diagram, has some significant complexity to it. You have this broadband continuum emission, again, spanning something like 3 orders of magnitude in energy. Okay? You also have, down at low energies, extra emission called the soft X-ray excess. And then over here, you can see you have a fluorescent line, in this case produced from iron atoms. Okay? And we'll talk about these iron lines in quite a bit of detail in a little bit. And then there's a high energy cutoff up here where the continuum drops off. And we'll talk about each one of these components that are labeled here one by one shortly. Okay? But just to sort of put it in context, that's what we're talking about. That's what we see to first order when you observe an active galaxy in the X-ray band. And to put that into context, again, over here is the spectrum of medical X-rays, in this case where people have taken a beam of electrons and fired it into a piece of tungsten, okay, to make medical X-rays. And you can see the medical X-rays, again, are up at like 50 to 100 keV or so. Okay? But to 0th order, the spectrum is not radically different, that you have this broadband continuum emission, and you have characteristic line emission being imprinted on top of that. The same kind of thing you're seeing here, a broadband continuum with an emission line here superimposed upon it. And this emission that we see in the X-ray band is proved to be a very powerful probe of the black hole region. So we'll be mostly talking about X-ray observations of this region right now. And again, to put this into an even broader context, this plot here shows the sort of connection between the multi-temperature emission that you expect to get from the accretion disk, which for a supermassive black hole, as you heard yesterday from the theoretical talk, is primarily in the ultraviolet and extreme ultraviolet, okay, and the X-ray band, which is primarily up here. Okay. So this is what we're talking about here, this part of the broadband continuum. Okay. So to first off, let's talk about why do we think the X-ray emission is coming from a very small physical region? Well, as we talked about yesterday, one of the big clues in this regard is X-ray variability. Okay, we commonly see the X-ray emission from these active galaxies varying by large amplitudes on short time scales. And here again are just a couple of plots showing that. These are the count rate, counts per second coming into an X-ray detector, okay, versus time. And you can see that this thing is varying up and down by large amplitudes, factors of 2 or more on time scales of an hour or less. Here are 2 other examples that I didn't show yesterday. Here's another one this is a nearby famous bright Seyfert galaxy. In fact, this is one of the original Seyfert galaxies studied by Carl Seyfert back in 1943, okay, NGC 4051, observed here in the X-ray band. And you can see it's varying up and down like crazy on very rapid time scales. Here's another example, another nearby bright active galaxy, and you see it varying up and down. And this rapid variability, as shown by these 3 examples here, is common among active galaxies. It's been seen now in hundreds of cases. And so this is a well-established common property of these active galaxies. And the most important point coming from this variability is it implies an emission region size of light hours or less. Okay, and so to put that into context, you know, that's pretty good evidence right there. Just the variability alone is pretty good evidence you're dealing with a very compact emission region. And we can sort of put that in context by going back to these orders of magnitude diagram. Okay, and you recall, so up here is showing the size of the solar system. Okay, and you'll recall that light travels from the sun to the Earth in about 8 minutes. Okay, and if I recall correctly, it travels from the sun to Jupiter. I believe it takes something like 43 minutes or so to get to Jupiter. So there you're talking about a good fraction of an hour. And to get out even further, you're talking about, again, you know, a couple of hours or something like that to get out to, you know, to travel through the solar system. You're talking about hours or sort of time scales, okay, light travel time. And so the point is that we're seeing variability of this extremely luminous X-ray emission. I mean, this is the power here involved is billions of solar luminosities all coming out in the X-ray band, okay? And you're seeing this thing varying on a time scale that implies that it's of order the size of the solar system, okay, in size. And then as I mentioned yesterday, you also see nice evidence that sort of links the physical size of the system, okay, to how fast it varies, in the sense that when you see objects where you've been able to measure the black hole mass, or if you don't have that, you just measure its luminosity and assume that that's some first-order approximation of the black hole's mass, you generally see stronger variability for objects with the smaller masses and the smaller luminosities, exactly as you would expect, okay, in the sense that a black hole of higher mass is bigger, and so it should vary more slowly. Okay, so now let's talk about the observations of these various X-ray spectral components, the ones that I had labeled on that previous diagram. We'll talk about the continuum components first. We'll talk about this broadband power law emission. We'll talk about the soft X-ray excess, what is its nature, and we're going to talk about this broadband hump you see up here called the Compton reflection hump. Okay, and we'll talk about those three components, and then we'll talk about some discrete atomic features as well that we see from the black hole region. In particular, we'll focus on this iron K line and how it's proved to be a very powerful diagnostic of the black hole region, and we'll talk about other line emission as well. Okay, so that's what we're going to be focusing on for a while. And I've shown you now this pretty schematic a couple of times, this one. Okay, I first of all want to show it to you in real data. I always am very uncomfortable, just as an observer, looking at various cute schematics like this, because while they look great, it's not real data. Okay, I like to see real data. And so here's a plot that actually shows real data of those various components. So this is a measurement, in this case, from the Suzaku satellite, which is a Japanese US mission. And it's of a nearby active galaxy. That's its name. And what's being shown here is the measured X-ray spectrum in a couple of different detectors. That's why these things have the different colors here. Up here. And then down here, this is showing the ratio of a fit between a power law model to the X-ray emission and what you actually measure the data to be. And so you can see a power law gives you a decent approximation over some decent part of the spectrum of the actual measured data, but at some places there are clear deviations. Down here, there's this clear excess emission compared to the power law. That's the soft X-ray excess that I'm talking about there in actual data. That's the soft X-ray excess. Okay? Up here, you can see there's this broadband excess compared to the power law fit. Okay? That's the Compton reflection hump. And here you can see this spiky line jutting up. That's the iron K alpha line in actual data shown there. Okay? So that's actual data putting all this into context. This is one particularly nice example where just due to this particular object's nature and due to the very high quality data over a broadband that were obtained, you can see all these components at once very nicely. Okay. Okay, so that's sort of the broadband schematic. Now let's go into some of the details. First of all, let's talk about that X-ray power law. Okay? So we observed to first order the X-ray emission from many of these active galaxies showing a basic power law shape. Okay? And so what that means is just if you're measuring the number of photons, okay, coming in as a function of energy, okay, it's proportional to the energy to some power, which is typically written as minus gamma, like that. That's what's meant by a power law form, okay, of the X-ray emission. Okay? And people have gone out for large samples of these active galaxies, and first thing they do is they fit power laws to them, and they measure that parameter gamma. Okay? And we find that active galaxies have some diversity of that value, but they typically, the measured values of the power law photon index cluster in a range between about 1.7 and 2.2. Okay, we can measure that quite well. And that turns out to be important in terms of constraining physical models, measuring what the slope of that power law is, as we'll talk about in a little bit. So where does this power law come from? How is it being made? Well, the idea is that power law is the observable manifestation of the accretion disk corona that we were talking about. You have this accretion disk corona, and it takes photons from the accretion disk that may come out in the extreme ultraviolet or the ultraviolet or in the optical, and being filled with very high energy electrons in that corona, again with a temperature of like 1 billion Kelvin, okay, it Compton upscatters those photons, okay, to create the power law. So a photon comes up out of the disk. As it's trying to traverse this corona, it gets smacked by a very high energy electron or perhaps a positron, gets boosted up into energy, and that Compton scattering process naturally produces a power law form of radiation. Okay? If you're interested in the details of how that occurs, you can look in the famous book by Rybicki and Lightman, where they actually show how Compton scattering very naturally produces a power law spectrum. Okay. And so this corona, well, what is it? Well, this is somewhat mysterious still. Okay? The corona, we're trying to determine its nature from the measurements that we're making. One standard idea that's been well developed is that it sort of is like what I'm showing here, that it's some sort of coronal structure that's being heated by magnetic flares when magnetic fields erupt out of the surface of the accretion disk, are rapidly sheared apart, and dump their energy up into this coronal structure. That's one idea for what we think may be going on. One thing we can do is we can measure the temperature of the corona. Okay? How can we do that? Well, we look at many of these active galaxies, and you typically see the power law runs along for a good while, and we'll talk about this Compton reflection hub in a minute, but at some point there's a cutoff in the spectrum, and that high energy cutoff is coming about because the corona has some finite temperature to it. Okay? And let's say the corona has a temperature of, as I believe I mentioned over here, about 150 keV or so, about 150 keV. Well then, for photons significantly above that, you're not going to be able to produce them very effectively. You're going to get this exponential cutoff in the flux. And that's what's believed to be going on there. So the reason why there's this cutoff here in the spectrum is because the corona has this finite temperature, and it just can't produce photons of energies much higher than the temperature of the corona. Makes sense? That's pretty reasonable. Okay? So that's the origin of this cutoff. And this cutoff turns out to be very useful because it gives you a method of measuring what the temperature of the corona is. If you see this cutoff at 150 keV, that's a pretty good hint that's about the temperature of the corona. If you see it at an energy of 50 keV, that tells you have a lower temperature corona in that case, more like 50 keV. And so one thing that people are doing quite actively with various missions is they're trying to measure the energy cutoffs, okay, to learn something about the temperature of the corona. Okay. Now, the great challenge with understanding this corona is that its properties cannot yet be computed from first principles. So unlike an accretion disk, where there is this well-established solution to first approximation, the sort of Shakura-Sunyaev accretion disk solution that you heard about yesterday, okay? We don't have such a thing for the corona. We can't compute from first principles the nature of the corona, unfortunately. Okay? People are making progress trying to understand it with large-scale supercomputer computations, where they actually put in all the basic physics of an accretion disk, they put in the magnetic fields, and they try to see if they can produce something sort of like the corona. And they're making progress in that direction, those types of computations, but they're not all the way there yet. So we can't work out from yet. I think we will be able to do it probably within the next decade, but yet we can't compute the corona's properties in detail from first principles. So its nature remains somewhat uncertain. It may, one favorite idea is, as I show here, that again you have this coronal structure that somehow is sandwiching the disk, in the sense that the corona is sort of occurring on this side of the disk, almost fully covering it, and on that side of the disk. And so it's like a sandwich, where the pieces of bread are the corona, and the disk in the middle is the filling of the sandwich. Okay, so that's why that terminology is used. That's one thing that people talk about in terms of the coronal structure. Other people, based on various measurements, prefer to think of the corona perhaps as being the base of a jet, the base of a small jet. And this plasma in here may be able to Compton upscatter and produce such radiation, okay, to create the power law. So maybe that's the case. We're trying to sort that out with measurements as well as with better computations. But that's what we know so far. What we can say empirically is, even though it's very hard to work out the properties of the corona from first principles, we know empirically that whatever the structure is, it's very robust among active galaxies. And we know that because we observe X-ray emission with this basic power law form very commonly from active galaxies. Okay? In fact, it's hard to find. It's possible, but hard, okay, to find active galaxies that don't show this X-ray emission. And this plot here is one illustration of that. In this case, what we've done in this case is we've gone out to a sample of active galaxies, selected optically, selected based upon their optical emission. And we've looked in detail at their X-ray properties. And this is a sample where we have essentially complete sensitive X-ray coverage of all the objects. Okay? And what this plot is showing is it's showing the strength of the X-ray emission compared to the nominal value. The nominal value, in the way I've made this plot, would be here at 1. Okay? And so you can look for objects, for example, where the corona doesn't exist, where it's very weak. Those would correspond to objects that are very weak because you don't produce the X-ray emission. And they're rare. What this is showing is it's showing the 90% confidence limit on the fraction of quasars that are X-ray weak by a given amount. And if you want to look at quasars that are, say, X-ray weak by a factor of 10, they're rare. They make up less than sort of 2%, that's 2 or 3% of quasars. And so the point here is that this coronal structure that produces the X-rays, whatever it is, it's a very robust thing. It's not like it's only there half of the time or something like that. It's almost always there. And we know that because we observe X-ray emission to be so common from active galaxies. Does that make sense? So that's the basics about the corona. We know there's this coronal structure. Its exact geometry is somewhat uncertain. But it essentially it serves the role of Compton upscattering photons from the disk to produce this X-ray power law emission that I've been talking about there. Is that good? Any questions about the corona? There are many questions about the corona, but any that I'm able to answer. Yeah.
You mentioned that the corona was hit by the magnetic flare.
That's one idea.
By the magnetic flares. Reconnection?
Yeah, magnetic reconnection. Kind of like what happens in the solar corona, but much more extreme. So if you go back to this little schematic I drew here, one idea that people have is that you have the accretion disk, which has magnetic fields in it. And we have pretty good evidence that magnetic fields play an essential role in making accretion disks work. You heard yesterday about the bulbous Hawley instability, for example. Okay? Those magnetic fields get amplified owing to the rotation of the plasma in the accretion disk. They sometimes erupt upward out of the disk. And when they do that, they're anchoring, frequently, 2 different radii. And of course, this radius in here, closer to the black hole, is rotating significantly faster than the radius further out. And you have to remember that the motions in here close to the black hole are a good fraction of the speed of light. And so this magnetic field will be very rapidly sheared apart, and will dump its energy out into the corona, heating it via magnetic flaring of that type. Kind of like what happens in the solar corona, but much more extreme, happening much more rapidly, and because of that, ultimately producing much higher temperatures. Again, you remember the temperature of this corona is like 1 billion Kelvin, where the temperature of the solar corona is like 1 million Kelvin. So this is something like the solar corona, but much more extreme and happening much faster. Yeah, that's the idea.
Can you explain more about the Compton flexibility?
Yeah, I'm going to come to that. Yeah, just so you see where we're going, I have now slides on the soft X-ray excess, the Compton reflection hump, the iron K alpha line. So we're going to do all that in great detail. Yeah, I'm just getting the power law down for now, and we'll come back to the Compton reflection hump. You had a question, yeah?
Does the corona seem like the solar corona?
That's one way to think of it. That's how people, when they originally came up with the corona in an attempt to explain the X-ray emission that we see from active galaxies, they had a picture of the solar corona in their minds to first approximation when they were thinking about it. If it is like the solar corona, it's a much more extreme version of what happens for the solar corona, but that's the one way to think about it. Again, other people prefer to think of it as something like the base of a jet, in which case then it could be very different from the solar corona. We're still trying to figure that out. Yeah. Yeah.
The corona, you need it only just for producing relativistic electrons.
Yeah, that's right, to do the Compton upscattering. That's right.
Basically, you should also have synchrotron.
Yes, and people have talked about, I can tell you about that. If you're interested in that, there's a paper by Leor and Behar where they have talked about perhaps synchrotron producing some of the radio emission that we see from even radio-quiet active galaxies. Yeah, so people have thought about that in some detail. Yeah. Other questions? Yeah, go ahead.
So you mentioned the range of the photon stack.
Yeah.
So does it affect in the restricted information or intrinsic absorption?
Does it?
Does it affect in the restricted information or intrinsic absorption? Are these the intrinsic photon index?
Yes. Oh, right. Okay. So, yeah, so this measurement here, when we measure these photon indices, these are for unobscured systems. So let me step back. When I said at the start, today I'm going to be focusing on the objects here. We're going to focus on the objects where we have a clear view of the innermost regions. So that when we measure those photon indices, those are thought to be the true value being created in the immediate vicinity of the black hole, unaffected by absorption. That's right. If you add absorption on it, that can make things more complex, and it can take the effective photon index you might measure and corrupt it away from the real value. But this is those measurements of 1.7 to 2.2. Those are the real measured values for clean systems where we think we're seeing it directly. That's right. Yeah. There was another question up here, I thought. Yeah, go ahead.
Is there differences between type 1 and type 2 intrinsic power index?
Okay, it's a very difficult question to answer to begin with. And I can come back. I will talk more about that later on. It's a very difficult question. His question is there a difference between the real intrinsic photon index for type 1 and type 2 objects? Okay, and it's a hard thing to answer because, just again, going back to this plot I showed, the type 2 objects, are often very strongly affected by this absorbing material. And so it will take whatever the real value is, and it will imprint an absorption signature on it, often a very strong absorption signature. And unless you can measure that absorption signature very carefully and disentangle it from the overall signal that you're measuring, it's very hard to reliably get this back. But there have been attempts to do it. And the attempts to do it, if you're interested, there's a paper by Vasudevan et al. That considers such things. The attempts to do it, which often utilize high energy data, for example, from the Swift-Bat survey and so on, using very penetrating X-rays that can get through the absorbing material, do indicate that, yeah, essentially the gamma values for type 2 objects are pretty consistent with those from type 1 objects, although with a significant systematic uncertainty on it associated with our ability to unwind all this absorption back out of the spectrum. Yeah. So it's a tricky thing to get at, but that's what we find. Yes?
Shock acceleration can also produce the polar with photon index typically 2.
Yeah, many things can produce a power law with a photon index of 2. Yeah.
Is such kind of possibility ruled out?
we can say some basic things about the nature of the corona, and I'll come to some of those things when I talk about the formation of the iron line and reflection and things like that. Can we strictly rule out something like shocks? Well, if it is shocks, it has to be shocks occurring on very small size scales, very close to the black hole. So I mean, if you wanted to propose somehow that there's, for example, some kind of a shock in a jet, perhaps down in here near the base of the jet, some kind of a shock there, maybe that could do it. Can we rule that out? Probably not. That's right. Yeah. Yeah.
You just show us that the beaming development of the spin.
Yeah, yeah. I'll go back to that picture, like that. Yeah.
Yeah, but the popular idea that the beaming effect is most coming from the jet.
The
beaming effect is coming from the jet.
No. Okay. So yeah, the beaming effect I'm speaking of here is associated with the accretion disk. This is the sort of just the standard relativistic effect that when you have a relativistic particle moving in a certain direction, it tends to beam its radiation in its direction of motion preferentially. This will occur for relativistic particles no matter what form they're in, whether they're in an accretion disk or whether they're in a jet. So here I'm talking about particles in the accretion disk that are moving at a good fraction of the speed of light, and the ones over here are coming out of the screen, and the ones over here are going into the screen. And so the ones coming out here are preferentially beaming their radiation toward the observer, and the ones on the other side are beaming them away. So it's just the motions in the disk itself, not the jet. Yeah. Is that good? Yeah, sure.
When modeling the corona, I wonder whether we assume the thermal equilibrium.
Right. People have thought about that. So his question is, do we assume thermal equilibrium of the particles in the corona? It's a good question, and people have wondered about that for a long time. And there's an interesting history behind that, which I can tell you. Maybe I'll mention that in a minute. First of all, I'll just say that we observe these cutoffs from many coronae. Okay, we're able to go and observe them pretty well. Now, for example, with measurements from the New Star mission, or earlier with measurements from the Compton Gamma Ray Observatory, we can measure these power law cutoffs. Okay, that is thought to be associated with the temperature of the corona. So inherently, you're talking about a thermalized system. Okay, a non-thermal corona could have a power law that could extend out to much higher energy still. And in fact, early measurements with an early gamma ray satellite, in fact, suggested that many safer galaxies were detected up in the high energy gamma rays. And so people came up, there was a whole generation of papers, if you look back in the 80s and the early 90s, of non-thermal, exactly as you're talking about, non-thermal corona models. And then the Compton Gamma Ray Observatory was launched, and it re-observed all those safer galaxies, and all the previous claimed gamma ray detections went away. And all those papers were thrown out. So the best evidence we have right now is that at least the majority of the particles in the corona are thermal at some level. And that's how you get this cutoff here. There's one other thing I can mention, by the way, that reminds me of one other thing I should mention. One thing you might wonder is, why is the corona, why does it have a temperature of 150 keV? Okay, why is it that hot? Why doesn't it have a temperature of 800 keV? Does anybody have a guess as to why? There's a reason for it. Does anybody, you know about the limit of how hot you can make a plasma in nature? So let's say you have a plasma. Let's say you have a plasma, and you're trying to make it hotter by adding energy to it. Okay? And so you add some energy to it, and it gets hotter. You add some energy to it, and it gets hotter. And you keep doing this, but there's a limit to how hot you can make that plasma. Okay, if you start producing a plasma with temperatures up to like 150 keV or 200 keV or so, then some of the particles, the high energy particles, okay, on the Maxwellian distribution, will have energies that are up at 300, 400, 500 keV. What happens at 500 keV, or specifically at 511 keV? Anybody know what's special about 511 keV? Pair production. Electron-positron pairs can be made. Okay, and so let's say that you heat up a plasma up to temperatures of 150, 200 keV. Let's say you add some more energy to it now to try to make it hotter. So you dump some more energy into it. What you find out is that, okay, so you add some energy to it, but the plasma just stops becoming hotter. Because what happens is you start producing pairs in the plasma. Okay? Electrons may scatter off protons and produce electron-positron pairs in the process. Okay? And now you have extra particles you've created that now have to be heated up. So so the energy that you've added in goes into producing more electron-positron pairs, creating more particles, instead of making the velocities of the particles hotter. You see that? There's a natural upper limit to how hot you can make a plasma, and it's about that hot. And so the reason why we think these coronae have temperatures of about 150 keV or so is because that's how hot you can make a plasma in nature. You just can't make them much hotter than that, because you try to make them hotter than that, and you start producing pairs copiously. And your energy just goes into making more particles instead of making more temperature. Does that make sense? OK, so that's the corona. It was a good question. So keep the questions going. That's very good. Yeah?
Why does corona have the wavy structure?
Why does it have this structure? I just drew it here arbitrarily. I don't know the detailed structure of the corona. I drew it here. You're talking about why does it have these. What I'm trying, I drew that picture myself just by hand. Okay? And it's not a detailed computation or anything. But the idea there is that you have magnetic field loops erupting up out of the accretion disk, similar to the way that there are magnetic field loops that erupt up out of the surface of the sun. That's all I meant by that. I didn't mean anything particular about a wavy structure or anything. Yeah. And again, there's substantial uncertainty. And as was noted here, the corona could be like this, or perhaps it could even be like that. Yeah. OK. There can be a variety of processes that are important. Thermal conduction, to my recollection, is not incredibly important. What can be very important, however, is irradiation. Because again, this corona, and this is about, actually, this is a good thing. This is about what I'm about to talk about, in fact. This corona is producing lots of photons, high-energy photons, via this Compton upscattering process. Some of these will fly away to the observer, and we'll measure them as high-energy X-rays in this power law. But many of the X-rays are going to get scattered back down onto the accretion disk. And they could heat the accretion disk and make it hotter than you would expect. Sakura-Sunyaev solution. And I'm going to talk about exactly what happens when you do that in just right about now. So yeah, I'll come to that. So that's a big effect, is a radiation of the corona's emission down onto the disk. Yeah. OK. Great. OK, so I'm going to move on then, and we'll talk a little bit. I just want to talk a little bit about the soft X-ray. Well, actually, let's just go ahead and do the Compton reflection hump in the iron line. Remind me to come back and do the soft X-ray excess, because this continues on nicely from what we were talking about. So as was just mentioned, this corona is producing lots of high-energy radiation. Some of that high-energy radiation will shine back down upon the surface of the accretion disk. What happens then? Well, there's a variety of things that can happen. One of the main manifestations of what happens when that occurs is the creation of something called a Compton reflection hump. And this doesn't follow the laws of reflection. It doesn't follow Snell's law or anything like that. It's not that kind of reflection. But that's the common word that's used to describe it. Okay? And what we observe from many active galaxies is this broadband hump sort of peaking between something like 20 and 40 keV up there. That's the Compton reflection hump. There it is, shown just from the reflection process, and there it is shown in the total spectrum. And going back to real data, here it is in real data. That's the Compton reflection hump up there. Where does that come from? That's what we're going to talk about. Where does that hump made? OK, so the idea here is that this Compton reflection hump is produced when X-rays shine down upon the accretion disk or any other material that's present and irradiate it. Okay, so what can happen to a photon that shines down upon the surface of the accretion disk? I'll just I'll draw a sketch here on the board. So this will be, this will be the surface of the accretion disk. The accretion disk material will be down here. Okay, and we have a photon that's been created, an X-ray photon created that comes down from the corona and shines down upon the disk. What can happen to that photon? A couple possibilities here. What? It can reflect. It can reflect. Good guess, given what's written there. Yeah, absolutely. One possibility is it can be reflected back. It can be Compton scattered back out. One possibility is this photon can get Compton scattered back out, okay? And we can see it. Another possibility is that this photon can penetrate down far enough into the disk that it gets absorbed. It's absorbed by the photoelectric absorption process in this case. The edges, the atomic edges of atoms down in the disk can absorb that photon, okay? And so what happens is you have this competition that's set up between Compton scattering, which can bounce the photons back out, and photoelectric absorption, which can absorb the photon and essentially destroy it, okay? And you have to then determine, as a function of energy, which one of those things wins. Okay. Well, if you do that computation, what you find is that the photoelectric absorption is dominant below about 10 or 15 keV. Okay? If you shine low energy photons down upon this disk, most of the time the low energy photons below about 10 keV or so get absorbed in the disk material. Photoelectric absorption is very important at those lower energies. But as you go up to progressively higher energies, okay, your chance of getting Compton scattered back out goes up and up and up. Okay? And so that competition between photoelectric absorption and Compton scattering starts to win, okay, up above 15 keV or so. And you get this broadband hump coming from Compton reflection that peaks up at about 20 or 40 keV. There it is. Now you might say, why does it stop there? Okay. Well, there's a couple of things that come into play. Remember, at high energies, other effects can come into play. The reason why this thing doesn't just keep rising and rising but drops off at high energies, well, there's a couple of effects. First of all, when the photon comes down and strikes the disk, let's say this is now, let's talk about a photon that has an energy of, say, 60 keV. Okay, well, when it shines down upon the disk, it will strike an electron, and of course, the nature of Compton scattering, the reason why Compton got the Nobel Prize, is that electron recoils, okay? And in the process of recoiling, it steals some of the energy from the photon coming in. And so this 60 keV X-ray may only come out with an energy of 30 keV, depending upon the exact details of the scattering process. You see that? And so the electron starts to steal more and more energy from the incoming X-ray, and that's what migrates it down in energy. That's one thing that can occur. Another relevant factor is something called the Klein-Nishina cross-section effect, where you probably know that the cross-section for Compton scattering drops at high energies, okay? And the people who computed exactly how it drops at high energies were two scientists, Klein and Nishina. So the cross-section drops off, and also the power law itself is cutting off. And so what you get overall, when you model all this out carefully, is you get this broadband bump peaking between 20 and 40 keV, and that's the Compton reflection hump. And it's a manifestation of X-rays from the corona shining down upon the disk and irradiating it, and it gives you a direct signature, okay, of the fact that there's a disk there and it's being irradiated by this coronal structure, and that's how it's made. And so that's what was making this hump here, seen in actual data. It's that competition between photoelectric absorption and Compton scattering at low energies, and it's Compton recoil causing it to drop off up here at the high energies. Okay, so that's the Compton reflection hump. And then there's one other effect very closely related to this one that also comes into play, and that's the creation of an iron K line. Okay, so let's talk about them. Sorry this doesn't come through super clearly, but another thing can occur when an X-ray photon shines down upon the disk, and that is it can interact with an iron atom, and it can knock the n=1 level electron out of an iron atom, and then of course the other electrons in the iron atom will fall down to fill the hole, and that can lead to the production of a fluorescent line photon. Yeah.
If we move on, so this reflection then, what is the X-ray line? Will that produce polarization?
Will it produce polarization? Yes, it can produce polarization.
So then you observe them?
Well, people have never, I mean, making an X-ray polarimetry mission is a very challenging thing to do. You probably know there was a mission in the US called GEMS, put forward by Goddard Space Flight Center. And it was an X-ray polarimetry mission that had a desire to measure polarization from things like this. Unfortunately, you probably know they were overspent their budget and were canceled by NASA. But there certainly is a desire to build X-ray polarimetry missions to measure things such as this. But it has not been achieved yet. That's right. Yeah. So there is a desire to do that. OK, so let's go back to this iron K line. So another thing that can occur when you have these photons shining down upon the disk is they can interact with an iron atom. So let's just quickly sketch out the energy levels of an iron atom. So here we are. We have 2 electrons down here in the n equals 1 level. Let's say we have some more electrons up here in the n equals 2 level, and so on. You have the various energy levels. Okay, and what will happen is an X-ray photon will come in. Okay, and it will knock the electron out of that level, out of the n equals 1 level. You suddenly have a vacancy there. The n equals 2 level electron will fall down, will fill that vacancy, and then the process will produce a line. Okay? And that line, for the case of neutral iron, has a very well-defined energy. It's 6.4 keV. Okay? And that process of an X-ray coming in, knocking out the n equals 1 level electron, another one falling down and filling the hole, and that's called fluorescence. That's the name that's referred to as. That's X-ray fluorescence. That's a fluorescent iron line being produced. Okay? And so that's what I mean here when I speak of iron fluorescence. When you have the disk being irradiated by X-rays, that process can occur commonly, and it produces line emission. And this will work, of course, for any atom. You might say, why are you only talking about iron? Why aren't you talking about oxygen or neon? Well, it occurs for those as well. But it turns out iron is by far the best producer of line photons for a couple of reasons. First of all, iron has a very good high abundance. And secondly, iron has a very high fluorescent yield. That is, the fraction of the time this photon gets out of the atom, instead of getting destroyed by the Auger process inside the atom, is very high for iron. Okay, much higher than it is for something like oxygen. So iron, if you consider the product of the abundance and the fluorescent yield, iron wins by far. Okay? So now we have an iron line. We have a line being made. And this line is being made in a very special place. It's being made in this relativistic region close to a black hole. We're saying there's a line being made in here. Okay? So that line should show manifestations of the environment in which it's being formed. It should show Doppler shifts to start with, very large Doppler shifts due to the very high speeds. It should perhaps show relativistic effects. And the iron line indeed appears to show those types of things. And I'll show you a plot here of an iron line. Okay. So here's an example here of an iron line that was measured in a nearby active galaxy. That's its name, MCG -6, -30, -15. And let's look at this line in some detail. First of all, let's consider the energies here. That's the observed energy. I've just told you the line rest frame energy is 6.4 keV. Okay? And so if you find 6.4 keV on this plot, it's right over there. So the line is indeed peaking right around 6.4 keV. But the line's pretty broad, isn't it? Okay? This is keV. This is 4 keV, 5 keV, 6 keV, 7 keV, and so on. So how fast is the matter going that's producing that line, given its width? Just a first approximation. How much? Higher than that. How broad is it? I mean, roughly. I mean, that's a keV, that's 2 keV. So it's roughly, let's say very roughly, it's 2 keV broad. Right? It has a rest energy of 6.4 keV. So how fast is it moving? Yeah. Okay, it's moving at 1/3 the speed of light, or 100,000 kilometers a second. Okay? And so that's the implication of that width, is you're seeing matter in the inner part of the disk moving at 1/3 the speed of light. Okay? So that's one effect that comes into play, is just Doppler effect. There's a number of other ones as well. So what this is showing here is it's showing the various effects that go into shaping that line profile. To first order, as we just worked out, you have the Newtonian Doppler effect that broadens the line. But then, you know, the prediction there from a disk, from at least a non-relativistic disk, is you should have a bright peak over here, okay, in the blue, and another bright peak over here in the red. But you don't see that in the actual data. You only see the line being strong on one side. Why is that? Well, that's because if you go back to this picture, which side is bright and which side is faint? Is the blue shifted side bright or faint? Blue shifted side is bright, the red shifted side is faint. Okay? So that's going to suppress the red side of the line and make the blue side of the line strong. And that's why the line doesn't show that double horned profile, but shows it being very bright over in the blue side and not so bright over on the red side. That's how this side gets enhanced compared to that side. Okay? Then there also can be the general relativistic gravitational redshifting effect coming into play that can modify the shape further. And if you add all those things together, there's been many extensive computations of such line, you end up with a line profile that has this peak over here on the blue side and then drops off and is very broad, very similar to what's actually measured. Okay? So the idea here is you're actually seeing a line made in the immediate vicinity of the supermassive black hole, and you can actually trace out the motions of the accretion disk and things like what is the accretion disk's inclination, what is the accretion disk's emissivity. And some very brave people, and I don't know if I believe them, some very brave people claim they can even measure the black hole spin, okay, with these types of measurements. And so that's, you know, whether I believe all the technical details or not, the essential idea seems to work very well, and it's a, you know, a promising way of learning about the motions very close to black holes. Okay, so that's the iron line. Okay, and I'll just say also that we observe other line emission as well. Here's a plot that shows a broadband X-ray spectrum. Here is the iron K line from this particular active galaxy. That's the iron K line. There's also additional line emission that's been claimed to be found from this object, in this case from iron L. Okay, so this is the iron L shell emission instead of the K shell emission. This is the iron L line here, which also appears to be broad. Okay, and that's another broad line that people have claimed to have now found from an active galaxy. So that's pretty neat. You can see the lines made very close to the black hole. So we've now covered, I went a little bit out of order, but we've now talked about the power law, we've talked about the Compton reflection hump, and we've talked about the iron K line. I also want to talk a little bit about the soft X-ray excess. So let's talk about that now. So at low energies, going back to my little schematic here, we often see excess emission above the power law, also at low X-ray energies down here. Okay? And that's called the soft X-ray excess because it's emission in excess of the power law that we see. Here is a little slide talking a little bit about the soft X-ray excess. Here's a particularly nice example my research group worked on of an object that has a very strong soft X-ray excess. In this case, you can see the ratio of the power law model prediction to what we actually measure in the data is such that the data are something like 2.5 times, almost 2.5 times brighter than you expect from the power law due to the soft X-ray excess emissions. There's a very strong low energy component here. And this emission can often be fit pretty well with roughly a black body spectral shape, okay, which is what you might expect from an accretion disk, but it's very hard to interpret it directly as just being from a simple accretion disk because it's much hotter than you would expect from even the very innermost parts of an accretion disk. And it also actually shows often very strong variability, much stronger than you would expect from any sort of direct emission from a standard accretion disk. And so this emission we see in the soft X-ray excess is likely a combination, perhaps, of some emission from the disk plus some additional Compton scattered component. There may be some cooler part of the corona that has that exerts just a small amount of mild amount of Compton scattering that can produce the soft X-ray excess. And in fact, here is an object that people have modeled in considerable detail showing a modeling of the soft X-ray excess component seen there, okay, as being from some direct black body emission from the disk at the very lowest energies, plus some additional sort of cool Compton scattered component producing much of the emission. And then here is the hot Compton scattering component there that produces the power law. So that's the soft excess, and that's another component that we see from these active galaxies. Okay, so that's what we see when we study these things spectrally. I also want to say a few words about what we find when we study their variability. I've talked about variability already, and I've said that variability is useful because it tells you the stuff comes from a very tiny region. But what else can you get from the variability? Well, people study AGN variability in the X-ray band in great detail, okay? As I mentioned yesterday, when you look at the variability, you usually, and by that I mean almost always, you don't see any clear periodicity to the signal, or even any quasi-periodicity. Although there is one interesting counterexample where you do see a quasi-period. But in general, you just see essentially random variation up and down. And here are some examples of active galaxies that were monitored in detail, okay, over a long period of time. You can see here, this is over periods of years. And then they have intensive monitoring to give measurements on shorter time scales as well. And what they do is they take a Fourier transform of that light curve, essentially. And you can derive a variability power spectrum that tells you how much variability do you see as a function of time scale from the active galaxy. And what you generally find is you observe a red noise power spectrum, okay, from the variability. And that's what you would expect, okay? And what does that mean? Well, are you familiar with red noise power? Are you familiar with the various types of power spectral noise? White noise versus red noise versus blue noise? Anybody, or not so much? So red noise has the characteristic that you have more variability power at low frequencies, hence the use of the term red, okay, for it. You know, just like a red spectrum has more energy down at low frequencies. It's the same thing here. What does that mean? Well, what that means is that AGNs, when you observe them, appear to vary more on long time scales than short time scales. And that makes sense, right? If you observe an active galaxy for just 1 second, it's probably not going to vary a whole lot. Whereas if you observe it for a day, it might vary considerably more. And that's what the red noise power spectrum is characterizing, the fact that they tend to vary more on long time scales than short time scales. Okay? But when you measure those red noise power spectra, you do see that the power spectrum is actually somewhat more complex than just a simple red noise spectrum. You actually see a bend or a break in the power spectrum. And that you can see that in these various spectra here. Here's a nice example where you can see that the source has one spectral shape up here and a different one down there. And there's a break right about there between the two behaviors. And that also makes sense. There has to be a break out at some long time scales because, you know, otherwise the variability power would be divergent. Let's say this thing just continued as a simple power law all the way down to 0 frequency. Well, what that would imply is one day you would wake up and you would look at, you know, NGC 5548. It would be as bright as the sun. Okay, and clearly that can't be true. Okay, because you can't have a divergent power spectrum. And so the thing has to have a break. And so people go when they measure these breaks. There has to be a break out at some long time scales because, you know, otherwise the variability power would be divergent. Let's say this thing just continued as a simple power law all the way down to 0 frequency. Well, what that would imply is one day you would wake up and you would look at, you know, NGC 5548. It would be as bright as the sun. Okay, and clearly that can't be true. Okay, because you can't have a divergent power spectrum. And so the thing has to have a break. And so people go when they measure these breaks in detail. And you can then go and compare the power spectra we see from these active galaxies with those from other black holes. For example, black holes in our galaxy. Okay? And you can actually correlate the time scale you measure for this bend or break in the power spectrum with other AGN physical properties. And you find some very remarkable things when you do that. First of all, you find that the bend or the break actually correlates with the black hole mass. So this is showing the measured break time scale for a set of active galaxies where people have done the detailed variability monitoring to measure the break versus the black hole mass. And you find that objects with relatively low mass black holes have breaks on rather short time scales, and black holes with very high masses have breaks on longer time scales. kind of what you would expect. You know, if the black hole mass sets the system size and sets the characteristic timescale for variability, you might expect behavior like that. And in fact, if you do a detailed modeling of the variability, you find that the break timescale scales as the mass to almost linearly with the mass and scales almost inversely with the Eddington fraction. Okay? And that simple formula that's been found there actually describes, well, both galactic black holes and active galaxies. Here's a plot here that sort of shows that over a very impressive range of sort of orders of magnitude. Here, this plot you can see goes down to break timescales here of sort of like 10 to the minus 6 days down here, and then extends up to timescales of sort of hundreds of days at the extreme end over here. Okay? And it combines together measurements of active galaxies up here and measurements of galactic black holes down here. And you can see that this very simple equation actually links together the variability behavior of galactic black holes and of active galaxies quite effectively. And it indicates that the active galaxies are really behaving like scaled-up galactic black holes, okay? Which is quite nice. It actually sort of unifies very nicely stellar mass black hole phenomena and supermassive black hole phenomena in terms of how they vary. We see a number of other additional remarkable types of variability as well. This is sort of measurements of the general variability that we see from these active galaxies, but there are extreme cases as well. I'm just going to show you a couple of those. Here's one example of an extreme variability event. This is a luminous quasar that we were studying and what this plot is showing is it's showing its flux history over the years, running from back to 1980 with observations from the Einstein Observatory through more modern observations with ROSAT and XMM here. And this source, during the XMM era, showed a really remarkable drop in luminosity, where it was going along being quite bright over the years. But then one time we observed it with XMM, and we barely detected it down there. Okay? And we found out, and note this is a logarithmic plot here, we found in this case that the luminosity of this quasar had dropped by a factor of like 260. Okay, you know, an incredible amount without any strong X-ray spectral changes. In fact, here what you're seeing is X-ray spectra measured when the thing was bright, and then as it got fainter. And the source remained quite soft, indicating this probably wasn't an absorption event or anything like that. This was a true change in the luminosity, okay, by a very remarkable amount. And so sometimes, remember I told you before how the corona is really remarkably stable, but it's not perfectly stable? Well, here's an example where perhaps the accretion disk corona somehow shorted out for a while, and the X-ray emission temporarily turned off. We've continued to monitor the source, and it's largely recovered now back to its nominal level. But sometimes things may happen to the accretion disk corona that shut it off or something like that. That's one thing that can happen in terms of extreme variability. Another thing is that we often see variability in X-ray absorption. Here's a nice example. This is a nearby bright Seyfert galaxy studied with the XMM Newton. And you can see how, in this case, the spectra taken over a period of a few months are very dramatically different in this energy range, where the flux drops off to lower levels in this intermediate X-ray band. I will just tell you, without going into details, much of this variability in spectral shape can be modeled by changes in X-ray absorption. And so people have proposed that in this case there's some kind of cloud of obscuring material that for whatever reason moved in front of the X-ray source for a while and obscured a lot of the X-rays and caused this very strong X-ray spectral variability. So sometimes absorption events are seen. And then the final thing I'll say before the break is that we often also see variability of the lines. If that iron line is indeed made in the immediate vicinity of the black hole, and if it's made by irradiation of the surface of the accretion disk by the coronal emission, then the iron line should vary. And we see that also. Here are some plots showing a couple of examples of that. Here's a nearby Seyfert galaxy, NGC 3516. And what this is showing is it's showing a plot of the iron line region. You see here's the 6.4 keV energy where the iron line should be, versus time. And so this is showing a bunch of little spectra lined up versus time. And you can actually see here what they claim. I don't know if I fully believe it. You clearly see variability of the shape of the iron line, where the iron line over here is showing a much stronger red wing than it was previously showing over here. And people have proposed in this case that they actually may see a periodic variation of the iron line. I don't know if I believe it's truly periodic from only 2 cycles, but nevertheless, the iron line is clearly varying in an interesting way. And here's another example. What people have done is they've computed a lag spectrum, in this case, and focus on this plot over here on the right, between the continuum and the iron line. And what they see is that the iron line variability appears to be lagging the continuum, in this case by about 2,000 seconds. So in other words, you see the continuum vary, and then the iron line varies, but it follows the variability of the continuum, but with a lag, and the lag's of about 2,000 second time scale. And so that's an indication that indeed there's some kind of reflection process going on. And this is, and the time scale is about right, okay, to, for the expected physical size of this particular system, to have the line lagging the continuum. And that's exactly what you would expect. If the line is formed via a reflection process, it should lag the continuum. And it indeed appears to be doing that. So anyway, I think that's a good place to have our break. And we'll then pick up afterward and start talking about the broadline region. But are there any questions, any final questions about the black hole region? Or if not, feel free to come up during the break, and I'm happy to answer any questions. Yeah, go ahead.
So, what's the physical origin of the break in AGN power spectrum?
Yeah, what is the origin of the break? Well, okay, again, an even more basic question to ask before that is what is the origin of the variability? And the problem is we don't really know all that well. What I can say is that, there has to be a break. There has to be a break at some level. We measure a power law up here, and then there is some characteristic time scale where there has to be a break. Otherwise, the power spectrum would diverge.
When we go to lower frequency, we expect another break, right?
Yeah, there should be even further breaks. And indeed, what is the physical reason for it? Well, for the case of AGNs, I don't think we've measured it well enough to really know. Although, if you really wanted to get your best understanding of that, what I might suggest you do is go study the stellar mass black holes, where you can get very high quality power spectra and see what they're saying about the origin of that break. I don't think it's been clearly established what the origin of the break is physically. It isn't like a rotation time scale or anything like that. What could it be? It could be some characteristic viscous time scale in the disk, or some time scale over which irregularities in the disk develop and go away. But what exactly it is, I don't know. But empirically, it's quite remarkable that it correlates so well with properties and appears to unify stellar mass black holes and supermassive black holes. Yeah. Yeah?
I can understand why the breaking frequency is correlated with mass, but I don't know why it is correlated with the accretion rate.
Well, yeah, that equation that's given there is not a theoretical equation. That's just measured. So what people have done is they go out and they have this sample of active galaxies. They believe they can measure the black hole masses for these active galaxies, and I'll tell you how they do that when I talk about the broadline region next. Okay? And they can then also measure the total power they see coming out, the total luminosity they see coming out of the active galaxy. And with that in the black hole mass, they can work out the Eddington fraction. And they empirically find that relation to fit. So that's an empirically derived thing. It was not derived from first physical principles or anything like that. I can't give you a simple why. I can just tell you when you go get the data, that's what you find. Yeah. And if you want to see speculation as to why it might follow that particular form, I'd suggest you look at these papers by McHardy. He may have some discussion of that, but I don't remember the specific details on it. Yep. Yes? The double peaked iron line? Yeah. Like this one? Yeah. Okay, yes.
And relative to the Newton profile.
The Newtonian profile, yes.
Special relativity and the general relativity predicted the spectrum redshifting relative to the
Yes. Okay. Well, a couple of things happen. A couple of things will happen. First of all, so the predicted line energy in the way this plot has been normalized should be at 1, right? And so, it should be. And so, first of all, from Newtonian, you know, here's 6.4 keV right in the center. You should have some emission blueward and some emission redward. And then the blueward emission is stronger than the redward because of the beaming effect. And so that emission should actually be above 6.4 keV. But then the gravitational redshift takes it and pulls it back down closer to 6.4 keV. And that's why the thing ends up being pretty close to 6.4 keV there, is the Doppler effect and the gravitational redshift compensate each other out to some degree. Yeah, that's the idea. Yep. Anything else? Okay, well, let's have the break then, and I'm happy to answer any more questions during the break. Okay. So I think we should get started again. Any questions that came up during the discussion or the break that you want to talk about? Okay, well then let's continue on. We've just finished talking about the region very close to the supermassive black hole and what we can measure about that. I now want to move on and talk about the Broadline region, a region a little bit further away that now we're going to shift from measurements primarily in the X-ray band to measurements in the optical and in the ultraviolet. And we'll talk about what we can learn about the Broadline region. Okay, so we commonly observe strong and broad optical and UV emission lines from active galaxies. I talked about these yesterday a little bit. Here are examples. Here's the Lyman alpha line, here's the carbon 4 line, and here are several additional lines. And we want to understand how these lines are made in detail. And we also want to figure out if we can use these lines to learn anything useful about active galaxies. And it turns out we can. It turns out these lines can be used to get at the black hole's mass as one example of something quite useful. And so we're going to talk about the Broadline region, again, from an observational point of view, and how we use it to deduce things about active galaxies. So first of all, what can we say about the Broadline region? Well, if you look at the relative strengths of those emission lines that we see, they indicate that we're observing gas that's photoionized. So this is not thermally ionized gas. It's gas that's being irradiated by the brilliant radiation of the central source, being photoionized and thereby producing line emission. So it's nebular gas that's photoionized. And you can even estimate the temperature of that gas. And you find the temperature is about 10 to the 4 Kelvin in round numbers. Okay? Furthermore, you can look at the strengths of those emission lines, particularly their equivalent widths. How strong are they relative to the continuum emission? And the observed equivalent widths of these emission lines indicate that the gas that's producing those lines covers something like 10 to 20% of the total solid angle, okay, around the AGN. So this gas is not fully covering the central source, but it's covering a decent fraction of the central source, up to like 20% or so. You can also infer something about the abundances of the gas. And this is difficult to do, but you can make approximations. And what we find, even for active galaxies out at quite high redshifts, interestingly, is that the abundances are roughly solar or perhaps even somewhat supersolar. Okay, so that's what we can infer just at a very basic level. So let's now talk more about these lines. Okay? When we observe these lines from active galaxies, we find out, and we study them carefully, we find that they're kinematically composite. And this is going to be important when we talk about the Broadline region versus the narrow line region. We find that these lines have a broad component and a narrow component. Okay, and we're going to talk about these in some detail. The broad component of the lines has a broad width with Doppler widths between about 1,000 up to about 25,000 kilometers per second. Okay? Whereas the narrow line components have much narrower widths, typically less than about 900 kilometers a second. So in other words, what I'm saying is that when you observe a line like, let's see, where's a nice example here, like the H beta line here, is that this, when you study it in detail, is not a single line. There's actually a broad component to this line and a narrow component to this line. How do we actually know that? Well, you can study, for example, how this line varies over time. And you find that there's a broad component of the line that's variable, and then a narrow core of the line that's not varying. Okay, that's one example of how you could infer the lines are kinematically composite. Okay, and what can we say about the broad component? Well, when we study it, we find that the broad component, from studying which lines are broad, for example, you find that the broad lines arise in gas with a density between about 10 to the 9 and 10 to the 11 particles per cubic centimeter. How do we know that? Well, it's because we look at what lines are broad. For example, we generally don't see the forbidden O3 line as being broad. You can go back here and actually see that directly. Here is the forbidden O3 line there, and you can see how the forbidden O3 line is much narrower than this broad H beta line there, right? You can see that, how the O3 line is narrower. Well, O3, of course, being a forbidden line, okay, is something that can give you a density constraint, okay, in the sense that if the density, what it's saying is the fact that we don't see broad O3 tells you that the density has to be fairly high, and the density via collisional interactions prevents the forbidden O3 line, which is a slow-forming transition, from being formed at all. So that gives you a density constraint. Similarly, the fact that we do see broad carbon-3 tells you the density can't be more than about 10 to the 11. And so by looking at which lines you see being broad, you can get an estimate of the density, and the density is between about 10 to the 9 and 10 to the 11 particles per cubic centimeter. Okay? And we have a name for the region that makes these broad line components, and it's the broadline region. Okay? Similarly, the narrow lines, again, they have smaller Doppler widths. They have to arise in relatively low density gas, and we know that from the fact that you do see something like oxygen-3 coming from the narrow line region. That gas has to be fairly low density to allow this forbidden lines to form. And our best estimates from looking at the various lines you see from the narrow line region indicates that its density is something like, very roughly, something like perhaps 10 to the 3 particles per cubic centimeter. And that's the narrow line region. This actually could be up to like 10 to the 5, but it's in very round numbers. It's a much lower density than the broad line region. So this kinematic separation of lines into a broad component and a narrow component leads to us discussing a broad line region and a narrow line region as being two distinct entities in an active galaxy. Okay, so let's now talk about the broad line region. First of all, these strong and broad lines from active galaxies are common. This is a nice plot that shows that. In this case, this is a plot that shows the spectra from 46,000 quasars, in this case observed by the Sloan Digital Sky Survey. Okay, and so Xiaohui Fan, the person who made this diagram originally, what he did is he went and took a huge number of quasars from the Sloan Digital Sky Survey, ordered them by redshift, and then plotted all their spectra, such that, here, the color here running along this way is showing one spectrum. Here's the next one. Here's the next one, going upward and upward and upward in redshift. And here you can see the various lines. Here's the nice magnesium-2 line. Here's oxygen-3. There's H-alpha. Here's carbon-3. Here's carbon-4. There's Lyman alpha. And you can see that in these 46,000 quasars, those lines are almost always there. So these lines indeed are common. The strong and broad lines are common among active galaxies. Again, things like carbon-4 and Lyman alpha and magnesium-2 and H-alpha, those are examples of the broad lines. Okay. So the first question to ask is, why are these broad lines broad? What's making them broad? Okay. Well, first of all, the motions that make these lines broad are not thermal motions. Okay. From the temperature that I just told you we've inferred for the broad line region, something like 10 to the 4 Kelvin, the expected thermal broadening is only like 10 kilometers per second. So it's not thermal broadening, okay? It's not that this gas is super hot and that's making it broad because of thermal motions. That's not what it is. Rather, this gas has to be exhibiting some kind of highly supersonic bulk motions, and those bulk motions of the gas are what leads to the broadening of the lines, okay? And of course, the fact that you see the larger Doppler shifts of the broad lines indicates that the broad lines are likely arising deeper in the gravitational potential, closer to the black hole. okay, where the expected bulk motions of gas are expected to be higher. So that's why people think the broadline region is formed in closer to the black hole than the narrow line region. Okay? So let's talk about the basic variability properties. It turns out variability has been extremely important for understanding the broadline region and pulling it apart. And we've learned a number of important things by studying that. First of all, we find that the broad lines from the broadline region vary on short time scales. And they do it in a very specific way. They do it in the sense that they follow the variability of the continuum, but with a lag. Okay? And I'll show you an example. Here's one nice example, study of that. So what this is showing here is it's showing the 5100 angstrom continuum light curve here, running along over time, varying over, you see, and this runs over a period of, what is this, 100 days or something there, right? Okay. Here is the helium-2 line varying. And you can see the continuum goes up and the helium-2 line goes up. And here's the H-beta line, and here the H-beta line goes up. But which one goes up first? If you look at that plot, which one goes up first? I mean, the continuum, look at that peak. What Kate Greer, who made this plot, has done is she's drawn the peak of the continuum. She drew a vertical line there to show where the continuum is peaking. This is where helium-2 is peaking. This is where H-beta is peaking. And you can see the continuum rises first, and the lines then follow, right? The idea there is a very simple one. The idea there is that these lines are being formed by ionization by the continuum. And so it takes some time for light to travel out to the emission line region and then travel off to the observer. There's a time delay associated with that light travel time out to the broadline region, and that's why the broad lines lag the continuum emission. Does that make sense? Okay, that's what's the origin of that lag, is that it takes time on average, okay, for the light from the continuum, which is ultimately responsible for producing the lines, to reach the line emitting region, and that's why the lines lag the continuum. Okay. So again, it's thought to be the light travel time across the broadline region, and this leads to this whole idea of reverberation mapping of the broadline region that we're going to talk about in considerably more detail shortly. Okay? For now, I'm just going to say that those lags give you an ability to measure the broadline region size. If the broadline region size, say it's a roughly spherical broadline region, is, if those time lags simply reflect the light travel time out to the broadline region, and there's pretty good evidence that indeed is the case, then it gives you a way to measure the broadline region size. You just take the time lag and divide by the speed of light, and that's the size. Okay? That's how you do it. And what people find is that depending upon an AGN's luminosity, the broadline region ranges from as small as 5 light days in the lowest luminosity active galaxies up to something like 500 light days in the most luminous quasars where people have seen these lags so far. Okay, so that's the physical size. This thing is light days in size, the broadline region. And we find also that, at the same time, you can look at the variability of the narrow lines. And at least on short time scales, the narrow lines do not vary. They actually may vary some on longer time scales. I'll talk about that in a future presentation. But the fact that the narrow lines do not vary nearly as fast as the broad lines indicates they're from a much larger region than the broadline region. Okay? So that's the idea there. You have this broadline region. You have light travel time across it. That leads to these lags, and that gives you the ability to measure the broadline region size. And people have, in fact, done exactly that. And here's a plot that shows, here are 2 plots, in fact, that show the estimated size of the broadline region in light days versus the luminosity of the active galaxy. Okay? And you can see here that for low luminosity active galaxies, the broadline region size is pretty small. As I said, it's down to something like 5 light days or so. And for more and more luminous objects, it gets bigger and bigger and bigger. To up here, you're up at a couple hundred light days. Okay? Here's another estimate where people have done a little more careful job subtracting out any light from the AGN, subtracting out any light from the host galaxy to get a more reliable estimate of the 5100 angstrom luminosity. And here's another measurement of the same phenomenon of the broadline region size getting bigger and bigger as you go to higher and higher luminosities. Okay? And this should make sense, as I'll talk about. And what people find is they find that the broadline region's radius scales roughly as the luminosity of the AGN to between the 0.5 to 0.7 power. Okay? And there's an argument among the various workers in the field whether the slope is exactly 0.5 or 0.7. Okay? But it's in round numbers, it's around there. And that slope is actually expected if all AGNs have similar ionization parameters and densities in their broadline regions. And so let's sort of just consider that. Okay, so you all probably have all heard, okay, thanks. You probably have all heard of the ionization parameter of gas, which is basically just the luminosity divided by the density over the radius squared. Okay? So let's say that you have gas where the ionization parameter is pretty much constant, right? Well then, how should the size, okay, there and the luminosity be related? Well, you can just work it out. The size, so if this is a constant, we can just also write this as r squared equals L over n squiggle, okay? And so r equals L over n squiggle to the 1/2, okay? And so the radius should go as the luminosity to the 1/2 power. And that's about what people actually find, okay, from making these detailed measurements. And so it appears that the broadline region from one active galaxy to the next appears to have a pretty similar density and a pretty similar ionization parameter, such that it appears to follow this simple relation between radius and luminosity. Okay, a pretty good approximation. Okay, so that's what people find about the sort of size of the broadline region. And then let's talk a little bit about the profiles of the broad lines. So people have looked in detail at measurements of these broad lines, measuring exactly what the line profile is like. And the profiles can't just be fit by a simple Gaussian. Generally, the profiles can be fit with something like 2 or 3 Gaussian components, or a Gaussian plus a Lorentzian component, or a logarithmic profile, as I've described there. And in fact, even in a single source, the profiles of different lines show diversity among them. The line profile that you measure for, say, carbon-4 may be very different than the line profile that you measure for the H-beta in a single object. So not all the lines show the same profile, even in a single object. So there's diversity from one object to the next, and there's diversity among lines in a single object. Okay? Some of the lines, it's worth noting, particularly things, high ionization lines like carbon-4, can show significant blue shifts. That is, if you define the AGN's rest frame by, say, the O3 line, which we believe is a pretty good tool to measure the rest frame of the AGN, you find that something like the carbon-4 line is significantly blue shifted, suggesting that some of the gas producing the carbon-4 line may actually be flowing outward, and you're seeing a blue shift owing to that outward flow. I'll say more about that in a little bit. And in many cases, the line profiles have additional structure that can be quite complex. You can see bumps or humps or asymmetric wings, okay, on the lines. And in fact, double peak lines are one rare extreme example. I'll just show you an example of these. These have been studied by a number of people. Here's some work by Mike Heraclius that have studied the broad line profiles, in this case in H alpha, for 2 objects called double peaker AGNs, okay? And you can see here, in this case, this thing has this broad sort of peak here, and then it has another peak over here, and this is the narrow line component in there in the middle of it, which makes the thing a little bit messy. But the broad component of this thing appears to have perhaps a double peaked type profile, sort of reminiscent of what we were just talking about for the broad iron line, how you might expect it to have a double peaked line coming from an accretion disk. And of course, here we're measuring optical emission that's made substantially further out than the X-rays. And so you might actually have truly double peaked lines out there. And Mike and others have suggested that some of this broadline emission may be from an accretion disk, at least in the cases of these double peaked emission lines. Okay. So these line profiles can be very complex. Okay, that's the point to take away from that. Unfortunately, owing to that complexity, the modeling of the profiles usually does not strongly constrain the detailed geometry and nature of the broadline region gas because there's degeneracies in the modeling. You can't really tell, is the gas in the form of an infall, an outflow, or is it in the form of orbital motions? It's very hard to tell. But there are a few important things we can learn from measuring these line profiles. One thing people have done, which is very clever, is they can go and get extremely high signal-to-noise measurements, okay, of these broad lines. What people do is they take a very bright local Seyfert galaxy and they go to a huge telescope like Keck, and they observe it all night with Keck to get this extremely high signal-to-noise measurement of the line, the broad line. And you can then look for what's called microstructure in the line profiles. Why is that useful? So let me first of all just show you an example. So here's an example where people have gone to a bright active galaxy, in this case Markarian 335, and they've gotten an extremely high signal-to-noise measurement of the line profiles. Here's the H-alpha line profile. That's the H-beta line profile. And they can cross-correlate these line profiles with each other, and they can look for microstructure. Why is that interesting? Well, let's say that the broadline region. Let's consider a very simplified case. Let's say that the broadline region was made up of clouds of some form, and let's say there were only 10 clouds in the broadline region. Well, then you would see distinct lines from each of those 10 clouds added up, to produce the total line profile, and you would see this graininess to the line profile, this microstructure to the line profile, because of the fact that you have a small number of clouds that are producing the line. We don't see such graininess. And in fact, if you look quantitatively for that type of microstructure, that kind of graininess associated with discrete clouds, you find out it's not there at a very sensitive level. And you can force the number of any sort of discrete clouds that are responsible for forming the line to be enormous, something like more than 1 million, or in the most extreme cases, more than 100 million such emitting clouds. Okay? So this has led people to suspect that there may not even be clouds at all, but rather the broadline region may represent line emission from some kind of continuous flow that doesn't decompose itself into a bunch of discrete clouds. Does that make sense? So this is one very useful thing that's come from studying the line profiles, the fact that there's a very strong limit on the number of any such clouds that can be there, and it has to be enormous, okay, ruling out many early models people had for the broadline region. Okay. Another important thing to note about the broadline properties is that there are object-to-object differences, as I already mentioned, in the broadline properties of active galaxies. And there are a couple of very notable ones that I want to just show you. One notable thing is known as the Baldwin effect, named after a man named Baldwin who found it in the first place. And Baldwin noted that some emission lines, carbon-4 being the most prominent example, show smaller equivalent widths on average as the luminosity increases. So in other words, luminous quasars have smaller equivalent width lines in carbon-4 than do low luminosity Seyfert galaxies. Okay? And that's known as the Baldwin effect. Okay? And it's been studied extensively by many people. And there's a lot of scatter in this correlation with luminosity, but there's a clear correlation there. And some emission lines, particularly I believe the high ionization lines, tend to show the Baldwin effect more prominently, whereas other lines really don't show a clear Baldwin effect. But that's one example. That's a luminosity dependence of the equivalent width of the lines. Okay? That's one thing that's known. Furthermore, another thing that's very remarkable among the broad emission lines is there's a set of emission line properties, including broad line properties and narrow line properties, but I'm going to focus on the broad line properties for now, that vary together in a correlated manner. And these have come under the name eigenvector 1, owing to the original methodology that we used to find these correlations, where people performed what's known as a principal component analysis, and as I'll show you momentarily, to find these correlations, okay? And I'll just show you what I mean by this. So what people did, in particular, there's this classic paper by Borison and Green that's worth reading. It's a very influential and important paper, where they got high-quality spectra, and here are some examples, for a large number of active galaxies in the Palomar green sample of quasars, in particular in this case. And they went out and measured systematically the emission line properties, things like the equivalent widths of the lines and the luminosities of the lines and the widths of the lines and the blue shifts of the lines. They measured all reasonable properties of these lines. And they found out that quasars are not random. There's, in other words, these lines have diversity from one to the next. And you can see that. I mean, you can see that very directly here. You can see this spectrum here has this very jaggedy-looking continuum and has very weak O3 line emission, where this one has a nice smooth continuum and very strong O3 emission. That's an example of what I mean by this variation from object to object. And moreover, these variations are not random, okay? There's a pattern to how the emission lines vary, and here it is. This is showing that pattern. So this is a large sample of quasars. Each one of these data points represents a quasar. And it shows a line property, in this case, the strength of iron 2 emission relative to the H beta line. In this case, the full width half maximum of the H beta line. In this case, the luminosity of the O3 line. In this case, the asymmetry of the H beta line, okay, versus this parameter eigenvector 1, which is a parameter that was found in a principal component analysis that was done on this set of spectra. And basically what they found is that there's a set of objects that live at one end of this eigenvector that tend to have strong iron 2 emission and weak O3 emission and generally narrow H beta lines and generally asymmetric, I don't remember if it's red word or blue word, probably blue word, but I'm not sure, H beta lines. And at the opposite end, there are quasars that have weak iron 2 emission and strong O3 emission and broad H beta lines and asymmetric H beta lines the other way. See what I'm saying there? And these things aren't random. That's the point, is that while there's a lot of diversity from one object to the next, it's not just random diversity. There's correlated variations of the emission line properties, where if you find an object, for example, that has very strong iron 2 emission, it's almost certainly going to have weak O3 emission. And it very likely is going to have a narrow H beta line. These things all go together. And so while there's diversity, there's method to the madness. There's an underlying structure here, okay, that you can find systematically in a statistical sense. And it also, I'll say, links in with X-ray properties as well that's been found, where it links in with the X-ray spectral shape and other properties as well. Okay, so this is an important correlation that's found among these emission lines. So that's what I mean when I talk about object-to-object differences. You see luminosity effects, and you see systematic variations of emission line properties known as this eigenvector 1. And I will tell you that further study of this indicates that the eigenvector 1 is likely related to the fraction of the Eddington luminosity that the quasar is emitting at. Okay, and there's many studies on such things which you can go read about. But that's one example of how there's interesting correlated variability of emission line properties. So yeah, go ahead. Yeah, sure.
What's the origin of Baldwin effect?
Of the Baldwin effect? I don't know. Yeah, it's not really. It's established observationally to be the case. I believe that there are suggestions that maybe the covering factor of the line-emitting gas drops with luminosity. If you go back, you'll remember that the equivalent width of the lines is largely set by the covering factor of the line-emitting clouds. And there's been suggestions that covering factor drops with luminosity.
Actually, that's another question I would like to ask. Can you explain in more detail about how to relate the equivalent width and the covering factor?
Yeah, it deals it deals with photoionization calculation. So what people do is they consider a given quasar, and they then put gas around that quasar in a simulation with a given covering factor. And because they've set how luminous the quasar is, they can work out how bright the continuum should be, and they can work out how bright the emission lines are. And you do a photoionization calculation with a given selected choice of covering factor. And then you can increase that covering factor and increase it more and increase it more. And by doing that sort of a photoionization calculation for different covering factors, you can work out how much line emission you should get for a given covering factor. And then quantitatively, you look at the equivalent widths of the lines, what they're actually seen to be, and you then compare that with what you get from your predictions, and you find that 10 to 20% that I was talking about. That's where it comes from. Yeah. Other questions at this point? Questions at this point? Okay, well, let's continue on then. So I now want to get to say a few more words about this reverberation mapping, because it turns out this has been a key way that people have pulled apart the broadline region. Okay, so as we talked about already, people have measured these lags between the variation of the continuum and the variation of the emission lines. Again, associated, thought, probably with the light travel time between the continuum source and the line emitting region. Okay? And they've measured this for something like 50 AGNs. Okay? And the current sample of AGNs that they've measured this for is somewhat biased. They've tended to prefer to reverberation map the objects with relatively strong lines. And they've mostly made measurements of, for example, the H-beta line, which happens to be very easily accessible in optical spectroscopy. But in some cases, they've done this reverberation mapping for multiple lines. And when they can do it in multiple lines, they see something very important. They find that the highest ionization emission lines generally respond most rapidly to the continuum changes, indicating stratification of the broadline region, in the sense that the higher ionization lines have smaller lags and appear to be formed on smaller physical scales than the low ionization lines, which are formed on larger physical scales. And in fact, here's a plot that shows that. No, I'll come back to that plot in just a moment. But they find this stratification in ionization level, again, such that the highest ionization lines are formed on the smallest scales. Furthermore, what they can do is they can look at different lines, and they can look at the widths of those lines, and they can look at the lag time scales, which are two independently measured properties for those lines, and they find that the line width, the velocity, scales roughly as the time lag to the minus 0.5 power, as expected for virialized gas dominated by the gravitational potential of the central source. And here's a plot showing that. This shows the lag time scale of a given broad emission line. These are a set of lines here, shown with the solid symbols. And here are multiple independent measurements of the H-beta line for a single object. This is all measured in one galaxy, NGC 5548, which has been very extensively studied with these types of measurements. Okay? And what they find is they find that the width of the line scales inversely with the time delay. And moreover, what this plot is showing is that shows the virial expectation, where the width scales as the time delay to the minus 0.5 power. Now, how do you get that relation? Well, we can just do that quickly. You know, it's pretty much just doing something like 1/2 mv squared, okay, for a virialized system goes like gmm over r, and then you cancel those, right? And so then you can work out how should the velocity and the radius, the size, be related. And of course, what is r? Well, r is just equal to the speed of light times the time delay. So we can also write this as v squared going like gm over c tau, v squared going gm over c tau. And so you can see then that, going back to that relation I said there, that the velocity should go as tau to the minus 0.5 power, right? That's the prediction just for virialized motion. And that's what's shown on the plot there. And it agrees pretty well. Okay? It really appears that the gas may be virialized. Okay? You look at different lines representing different ionization levels, and you find that the ones that are broader seem to be formed closer in, exactly as you would expect for virialized motions. And that's a very useful thing to know, because now, once you've established that the gas is virialized, that means that it really follows simple laws like the ones we've written here. And you can actually hope to work out genuinely useful physical quantities. Okay? Because it's not guaranteed that this gas has to be virialized. It could be in the form of some outflow that's completely non-virial. But that doesn't appear to be the case. It really appears to be simple, at least in this sense. Okay. That being said, you have to be quite careful when playing these games. You have to worry about other effects like radiation pressure and so on. But to first order, it appears that virialized motion works pretty well for these lines. So that's one quite interesting thing you can do. Another thing you can do is you can observe the phenomenon known as broadline region breathing. So in a few well-studied objects, the broadline region has been observed to breathe over year time scales. So what does that mean? That means that the broadline region appears to get bigger as the source varies to high luminosity. So in other words, for some galaxies, like NGC 5548 that I just showed you, Brad Peterson in particular, has been monitoring this object for like 20 years now. And he can measure the lag when the source is in a very high luminosity state, and he can measure the lag when the source is in a low luminosity state. And what he finds is that the lag is longer when the source is in a high luminosity state versus when it's in a low luminosity state. Okay? The broadline region gets bigger and smaller, or appears to get bigger and smaller as the luminosity of the source goes up and down. Now, that does not mean that the broadline region gas itself physically expands and contracts. The broadline region gas is moving much too slowly to have that occurring on the observed timescales. Rather, the idea is that there's gas out there everywhere, that there's a large amount of gas out in the line emitting region, and that what's changing as the luminosity goes up and down is the distance from the continuum source where conditions are optimal for line emission. When the luminosity of the source goes up, the gas close in becomes too ionized to optically produce, say, the H-beta line, but the gas further out moves into an optimal state where it emits H-beta line very effectively. And then the source goes down to a low luminosity, and then conditions move inward. You see that? And the name for that idea that's been studied extensively is the local optimally emitting cloud model, okay? Whereby the region where line emission is optimally emitted, okay, depends upon the luminosity. It can move inward and outward as the luminosity of the source goes up and down. And this is important. It tells you that the total reservoir of gas that's producing that's associated with this region is large. It's something like 1,000 to 10,000 solar masses, even though at a given time only a tiny fraction of this gas, less than 1%, is radiating lines efficiently. In other words, the total amount of mass needed to produce the broadline region is tiny. It's like 10 solar masses, something like that. Okay, maybe a little more, but it's tiny, 10, 20 solar masses, somewhere around there. Whereas the total reservoir of gas filling this entire region has to be quite large, because you see this breathing effect going on, which tells you there's gas spread throughout the entire region. Okay, so that's another interesting phenomenon. Here, in fact, is a nice plot of this phenomenon of broadline region breathing. So this is showing the flux of NGC 5548 as measured by Brad Peterson over, again, something like, well, he has 14 independent reverberation experiments that were used here. And you can see here that as the flux of the source becomes bright, the broadline region appears to become larger. The lag becomes longer. And as the source goes down to low luminosities, it appears to become smaller. So the thing gets bigger and smaller as the source goes up and down in luminosity. Okay. So that's very interesting. So now we've seen that, okay, the broadline region's nifty. You can show that the gas is probably virialized. You can show that it breathes. That's all good. But what good is it? I mean, what good is all this? Well, the reason why people have gone to all this effort to try to measure all those things is it gives you a way of getting at black hole masses. Okay? And this is one of them. I believe this is arguably the main way that we actually get reliable masses. And I say reliably there with a little bit of caution, but fairly reliable masses for actively accreting supermassive black holes. Okay? You can estimate black hole masses. If you believe the gas is really virialized, like I wrote here, you can estimate the mass. Okay? You can see that the mass is just going to go as c tau times v squared divided by g. Right? There it is, c tau v squared divided by g, with some geometrical fudge factor, f, which accounts for the precise geometry of the broadline region, which affects exactly how the time delay relates to the physical size. Does that make sense? The gas is truly virialized. You can just, if you can measure the width of the line, you can measure the time delay, you can get the black hole's mass. Okay? And that's why people are so excited about reverberation mapping, is it gives you a way of getting at the black hole's mass. Okay. So, first of all, how do we deal with this F? Well, people have compared the black hole masses derived from reverberation mapping with other mass estimation techniques. For example, we've now established, and we'll talk about this a little bit later, and you'll hear much more about this from Luis Ho next week, how the mass of a galaxy's bulge is related to the mass of the black hole in the center. And that gives you another way of estimating black hole masses. And comparisons with such methods indicates an average value of this factor, F, that's between like 4 and 5. So if you put in sort of 4.5 or so for that F factor, you can estimate masses. If you can measure the width of the line and you can measure the time delay, you can get the mass. And masses measured that way appear to be accurate roughly to within a factor of about 3 when you use the H beta line. Okay. You can also use other lines. Magnesium-2 is commonly used. It appears to work pretty well. Carbon-4 is also sometimes used, particularly out at high redshift where you only have carbon-4 available. There, things are a little more difficult. And I'll say more about that in a little bit. And note that this method, this reverberation method, can be used if you're patient, even out at very high redshifts. Okay? If we wanted to get the mass of a black hole out at a redshift of 2, well, you have to monitor it likely for a long time because it's likely going to be a luminous object, so the time delay is going to be long between the relation between the time lag and the luminosity. And furthermore, of course, there's going to be cosmological time dilation. It's going to make it even longer. But if you're patient, and in fact, I've been trying to do this for about the past 14 years, and I'm still getting data. Maybe by the time I'll retire, I'll actually have an answer. But we've been trying to actually get masses this way. And so if you can get the time lag, and if you can get the width of the line, you can actually get this even for a black hole at a redshift of 2. Whereas I can tell you there's really no other way in the foreseeable future we're going to get such masses for high redshift black holes aside from this approach. So this is what people find when you look at the relation between mass and luminosity derived for black holes that have reverberation mapped masses. Here's the black hole's mass. Here's the optical luminosity. And with those two things, you can then plot on this diagram Eddington fractions. Here's 1/10 the Eddington limit. This is 1/100th the Eddington limit. And there is the Eddington limit there. And you can see that many of the black holes appear to have Eddington fractions about 1/10 the Eddington limit. So that's a nice direct estimate of the fraction of the Eddington rate that black holes are accreting at, about 1/10 of Eddington. And some of them, the open symbols here, you probably wonder, what are the open symbols? These are the so-called narrow line Seyfert-1 galaxies. And they often appear to be accreting at higher fractions of the Eddington limit than do more typical Seyfert galaxies, which is quite interesting. Okay, so that's good. What else can we do? Well, you can use the reverberation technique to calibrate mass estimates based on single epoch observations as well. In other words, if you combine the relation we've already seen between the radius of the broadline region, this thing I was talking about over here, and the virial theorem, this thing I was writing down here, you can estimate single epoch masses. In other words, you don't have to fully reverberation map an object. If you believe all this stuff, and if you're willing to make some extrapolations, you can actually, just from a single epoch spectrum, you can say, well, since I know the luminosity, I know what the radius is, and so here's my relation that puts in the radius as a function of luminosity. Here's the width, okay, again, going as the width squared, okay? And so I can work out a relation between black hole mass and line width and luminosity. And people do this all the time, okay? They try to get black hole masses this way. And these allow quick estimates of black hole masses for large AGN samples, but I would say their accuracy is no better than a factor of several, okay? And I would say the factor of several applies when you're using things like H-beta or magnesium-2, where we actually think we understand things fairly well. For something like carbon-4, I'm very scared about using carbon-4 with such a technique. People do it all the time, but the masses may not be so reliable because carbon-4 has a number of complications in its line properties that make it very hard. One of the real challenges here, in fact, is characterizing the line widths. When people do reverberation mapping, to get the width of the line, back in this equation like this, there's a natural question: is what do you put in for the line width? Do you put in the full width half maximum, or sigma, or something else? Well, people have to work that out very carefully. And what they typically, in fact, do is they don't use direct measurement of the line. They look at the line's variability, and they make an RMS spectrum and look at just the variable part of the line. And they use the width of the variable part of the line to get the width. And that's what seems to work the best for getting you a reliable mass. And so that's what you use when you put in the velocity width here, okay, to get the line width. If you're not careful, or if you just have a single epoch spectrum, you don't have the ability to look at just a variable part of the line because you don't know how the line's varying. And so you just put in the full width of the line and you hope for the best. And that's what leads to some of the significant uncertainty associated with this type of approach. But statistical use of such masses is probably okay, even though individual mass estimates may be unreliable. And this has proved to be a very useful method for getting basic estimates of black hole masses for large samples of AGNs. Then I'm just going to wrap up by saying a few more words about reverberation mapping. Now, the reverberation mapping I've been talking about so far has just been the simplest kind of reverberation mapping, where you take a whole line and you look at how does that whole line lag the continuum. But people dream, and they're actually making some progress, as I'll show you now. They're actually making some progress. They're actually trying to do a more sophisticated version of reverberation mapping. What you would ideally like to do is not to look at how the integrated flux of the entire line varies versus the continuum. Rather, you'd like to look at how the detailed line profile varies versus the continuum. You'd like to look at, for example, how the blue side of the line varies compared to the continuum, or how the red side of the line varies versus the continuum, how the center of the line varies versus the continuum. And the reason why is because people can make, for various broadline region geometries, predictions as to how the line profile should vary in relation to the continuum. Here's a case here, for example, where you have an infall of material. Here's another case where you have infall of a more extended broadline region. And what you predict in cases like this is that, let's see, how does this go? That one of the sides of the line should have a substantially larger lag than the other side. And that's associated with the fact that the material on the near side, close to you, if it's infalling, you'll see a blue shift there, and there'll be a much shorter lag. Whereas the stuff on the other side that's infalling will be red shifted relative. You see what I'm saying? This will be red shifted, this will be blue shifted, and you get different lags geometrically depending upon the geometry. Alternatively, if you have a Keplerian disk, you can work out the response there, and you get a different response. And so people have tried to do this already with limited data. They've tried to work out how does the detailed line profile change, okay? How does the lag change going across the detailed line profile? And what they find are a variety of results. Here's a nice case here where you actually see something that looks kind of like the predictions for infall, suggesting there may be some infall in this broadline region. But then you look at a different object, and you see something that looks like it might be an inclined Keplerian disk. And you see another object here that may show some infall. This one may be a disk. And the results right now are not crystal clear, because these types of measurements are extremely challenging to do. But people have put in a tremendous amount of work, and they're making real progress here. And in fact, there's a very large campaign right now that's either just completed or is just about to be completed on NGC 5548, where they're doing extensive monitoring with the Hubble Space Telescope and with ground-based observatories, trying to get very high quality data that will allow this kind of velocity resolved reverberation mapping, which can give you the detailed geometry of the broadline region. So this will be an exciting thing for the future, for me to do this. Anyway, so that's one thing that people are attempting for the future. And then the final thing, just I want to say a few more words about what is the nature of the broadline region. Well, these types of measurements have the possibility of quite directly giving us the nature of the broadline region. Is it a disk? Is it an infalling material? Is it a wind? We don't know. These may tell us directly, but for now, the current thinking, when I talk to people who work on this a lot, is they believe that the broadline region very likely itself has a composite nature. That is, the broadline region itself is probably made up of at least two regions. There probably is a region of moderate ionization and high optical depth that's responsible for the emission of the sort of lower ionization lines, things like the Balmer lines or the magnesium-2 lines. This may be the accretion disk itself. Remember, we talked back here when we talked about double-peaked line emitters. We saw that there are some objects that show lines that that have a kinematic signature of may well being from an accretion disk. And in fact, Mike Heraklius and others have argued that you can explain even single-peaked lines with an accretion disk in cases where the line emission is originating fairly far away from the, with a large line emitting region. You can actually get single-peak lines from an accretion disk as well. And so people are arguing that that may be the origin of many of the low ionization lines. You may have some line emission occurring in the accretion disk itself. However, that almost certainly cannot explain the high ionization lines. The high ionization lines are likely formed in a different region of moderate optical depth. And this may be an accretion disk wind. This could help to explain the blue shifts. Remember how I told you how many of the high ionization lines, things like carbon-4, often show very substantial blue shifts, indicating they're likely formed in some kind of a wind-like structure. And so people have proposed that the high ionization lines come from some kind of a wind, and that can explain the blueward line asymmetries and the blue shifts and so on. And there's still tremendous work going on trying to sort out the exact nature of the broadline region. Anyway, I think I'll wrap up there for today. And in the next lecture, we'll pick up and talk about outflowing winds, and then we'll move on to the more distant regions of the active galactic nucleus. I'm happy to answer any questions. Yeah, go ahead.
The info process means the blue side is the red side is more close.
Yeah, that's right. Yeah. So if you had infall, let's say you had infall, I'll just sort of I have an eraser this time. Okay. So let's say you had infall. Now I'll just sketch this very roughly. And if I'm recalling this correctly, let's say you had some kind of quasi-spherical broadline region where you had infall. And let's say we're observing it from over here. Okay, so if you had infall like this, what you'll see is you'll see over here, you'll see redshifted. This will be the redshifted part of the line, and there'll be a rather short lag there because you don't have much of a time delay due to the light crossing time. Whereas over here, on the the infalling side on this side, you'll have a long time delay, all the time to go there, and then all the way to time to go all the way back across there. So you'll have a long time delay, and so that the blue shifted side of the line will have a long time delay.
This is the red shift.
Which? Remember the red shifted side, this is moving away from us. We're over here. This is moving away from us, so that'll be the red shifted. This is moving toward us, so that'll be the blue shifted side. Is that good?
This process is come out with the potato algae.
Comes out of what?
This process this info process is come out with the rotate or they info themselves.
It comes. I didn't understand a word there. I'm sorry.
This info process come out with the rotate process or they info themselves.
Yeah. So what people do is they compute line response profiles for different assumed choices of broadline region geometry. You can work it out for a case where you have simple infall. You can work it out for a case where you have simple outflow. You can work it out for a case where you have broadline region clouds going around in orbits. Or you can work it out for a Keplerian disk. And you work out what the line response profile should be for all those different choices of geometry. And then you then try to make measurements that can discriminate between those possibilities. And that's what people are trying to do now. But people have, I mean, again, you saw some of the results here. And the results so far, I mean, there's some cases where you seem to see something like infall. But then there's other cases where things are not so obviously like infall. And whether this is just, I have not dealt with the data, so I can't say for sure. But, you know, there may be some wondering in the community whether this is truly whether the difference between this and this are truly statistically significant, in which case that's very interesting. It suggests that in some cases you have an infall, in some cases you have a disk. Or whether this is just due to the fact that the data are very hard to obtain and work with. You need very high Searles noise data to do this type of an experiment. And so people are trying to get much higher quality data now. Yep. Yes?
So that the total mass of the Broadline region is from 10,000.
Yeah. Mm-hmm.
How do you estimate?
Right. Again, this comes to photoionization calculations. And so you can work out, you can do photoionization calculations putting in a certain amount of gas, and you can ask how much gas do I need to produce the line strings? And it's not much. The gas instantaneously emitting at any given time is small. It only has to be, again, it only has to be like 10 solar masses or so. The gas is instantaneously emitting at any given time. But then the fact that you have gas that follows this basic type of relation, okay, spread throughout the entire region in order to allow this breathing phenomenon to occur at a wide range of radii implies there has to be quite a bit of mass there. That's the reasoning for how you do it. And again, it's not something where I can just write a simple equation on the board and there it is. You have to run a photoionization code to predict line strengths, and from that you can make the comparison with the data. Yeah. Any other questions? Yeah, go ahead. What is the Baldwin effect? Okay, so the Baldwin effect, I'll just go back. So people have noted a number of object-to-object differences in broadline properties. And one of the first ones that was noted was noted by a man named Jack Baldwin, who's still alive today. He works in Michigan, I believe. And he noted that some emission lines, particularly the high ionization emission lines, things like carbon-4, have smaller equivalent widths on average as you go to high luminosity. So in other words, if you take a large sample of active galaxies, okay, and you plot the equivalent width of carbon-4 versus luminosity over a very broad range of luminosity, you find that the low luminosity objects tend to have larger equivalent widths, although there's quite a bit of scatter. And as you go to higher and higher luminosities, in a very broad sense, the luminosities on average go down, like I'm showing there, and with a lot of scatter from one object to the next. And that phenomenon of the carbon-4 equivalent width dropping as you go to high luminosities is known as the Baldwin effect. Why does it happen? Yeah, again, as I mentioned to Professor Jouet, we don't have a totally clear answer to that. It may be that the covering factor of the broadline region drops as you go to high luminosity. And I'll show you later on a similar phenomenon where we actually believe that the covering factor of the torus likely also drop as you go to high luminosity. So it may be something like the covering factor tends to become smaller of all kinds of gas as you go to higher luminosity systems. They may be able to clear out their central regions better than low luminosity objects. That's one possibility. But I don't think that, I don't think there is a single universally accepted clear answer as to why. Right. Yes, go ahead.
More detail about how to convert the broadline winds to velocity.
How you convert the broadline width to velocity. Yes, it's not an easy thing to do to start with, okay? Yeah, so that's what I had mentioned here. You know, so when you have a broadline profile, there's many things you can measure about it. I mean, what do you care about? Is it the full width half maximum, or sigma, or the width at a quarter intensity? What is the most relevant quantity to measure? Well, the first thing that people do is they have learned from looking at measurements, from analyzing these reverberation data sets with many different approaches. They have found that in general, the clearest results appear to come when they don't use the direct line profile, not like the average line profile, but rather they look at the variable line profile. They look at, instead of making like an average spectrum, they make an RMS spectrum. I showed you an example of one in the lecture yesterday, an RMS spectrum of a line profile. And that shows you just the part of the line that's varying. And then you tend to measure the width of that. And by width, they generally work with something like the full width half maximum. And they measure that part of the line profile. And they use that in equations like these to derive black hole masses. But it's a good question. I mean, the question is to what is the most relevant thing to measure to get a black hole mass? That's not an easy thing to, it's not an easy thing to know. And so people are making the best possible choices they can. Is that the nature of your question, or are you asking something else?
For example, how wide to velocity?
How what?
Wavelengths to velocity.
How do you do it? You use the Doppler formula. It's like V over C is like delta lambda over lambda. That's what you use. Okay. Okay. Right. Okay. Yes.
Is there how you totally a boundary between the continuum lines and the broad line region?
Continuum?
Continuum. Where does this continuum line?
Where does the continuum come from?
Come from is from the base.
Yeah, right. Okay. Her question is where is this continuum coming from that drives the broad line? So in other words, if I go back to this plot, you know, I have mentioned how, you know, you see the continuum varying, and then you see the lines varying. Okay. And so the question is, where does this continuum come from? And the answer is, yeah, we believe it comes from the disk. We believe that this is the optical and UV emission from the accretion disk that's driving this. Now, this is actually an important question because, you know, one inherent assumption built in, and there are many, but one inherent assumption built into reverberation mapping is that the continuum source is essentially point-like compared to the size of the line emitting regions. Because if it isn't, if the continuum source had a non-negligible physical size compared to the size of the line emitting region, then you have to worry about all sorts of geometrical effects, not just of the line emitting region, but also of the continuum source. Fortunately, our best estimates of the size of the continuum source and our sizes of the line emitting regions indicate the continuum source is indeed much smaller than the line emitting regions, validating that assumption of reverberation mapping. So yeah, the idea is from the accretion disk, from the optical UV emitting region of the accretion disk. And remember also that the lines, the continuum that is driving things like H beta and helium-2 is not at 5100 angstroms. It's actually much shorter. It's out in the ultraviolet and the extreme ultraviolet. You remember the ionizing continuum that leads to the creation of these lines is at much shorter wavelengths, and so it should be even smaller. Now, you might ask then, well, why is it that you measure 5,100 angstroms? Why don't you measure the true continuum that's driving the creation of these lines? That would be a better continuum to measure. But the problem is it's much harder to measure because it's hard to make observations out of the ultraviolet and extreme ultraviolet, where it's easy to make them at 5,100 angstroms. And so people typically use 5,100 angstroms because it's convenient and because it appears to work. But really, the more relevant continuum is the ultraviolet and extreme ultraviolet continuum that drives the line production. Yeah.
This plot, the helium-2 and hydrogen.
Yes. Yes.
Lines have different R, like the.
They have different. Yeah, exactly. They have different lags. They have different lags, and that goes to this idea of stratification that I mentioned, if I can find it here, of stratification. The idea there is that. The idea there is that, where did I have it here? Here, the higher ionization, helium-2 is a higher ionization emission line than H-beta. And so it's responding more rapidly to the continuum changes than H-beta is, and that's the ionization stratification. So the reason why helium-2 has a shorter lag than H-beta is because helium-2 is higher ionization and is thought to be made closer to the black hole. Yeah, that's what's going on there. That's right.
So we can scale the.
Exactly. That's what people have done. That's what this plot is all about. That's what this plot is all about. People have measured lags for multiple independent lines in this single object, and they find that the lines that are of higher ionization have shorter lags and also have generally broader widths.
So it's closer.
Closer. So you can see this true stratification of the structure, and because this quantitatively matches the expectation from the simple virial relation. Well, I've erased it. I had it over here. Matches the simple prediction from the virial relation, leads you to believe that indeed this is just simple black hole's gravity is driving the motions of these lines, which lets you use the virial theorem and all those types of arguments to deduce black hole masses.
But there are less like points or data near inside.
Well, they only have so many lines to work with. Yeah, I mean, clearly, if you could measure, if you had access to an even higher ionization line, like could be over there, you'd like to have one, but they don't have. All they have is what they can measure. Yeah, but I mean, they've measured a good number of them, and it seems to be somewhat virial there, which is reassuring. Yep. Good. Other question? Any other final questions? Oh, yeah. Go ahead.
When estimating the black masses by the RM method, so they often to the beta MG2 carbon 4 lines.
Yes.
So my question is that when all of these emission lines are available,
yes.
So the best one is beta, right?
The one that is best understood right now is H-beta. And the reason for that, remember, is that H-beta is a relatively low ionization line, and as is magnesium-2. And so because they understand H-beta, they think they probably understand magnesium-2 pretty well also. And magnesium-2 often has a similar line profile to H-beta, whereas something like carbon-4, which is a much higher ionization line, often has a very different profile, may have very different dynamics, may not even be virialized. And so you have to be very nervous. The further away you get from H-beta, the more nervous you should get. To get black hole masses at high redshift. Now there you won't necessarily be able to use H-beta. You'll have to go use other lines, magnesium-2 or carbon. Hold your breath and use carbon-4, okay? Because carbon-4 is going to be available at a high redshift. And I think there may be hope for carbon-4 in the sense that if we really go out and study a bunch of quasars and get really good measurements of carbon-4 out at high redshift, maybe we can calibrate carbon-4 and understand it well enough that we actually can use it and not feel very nervous about it. However, we're going to have to be very patient to do that, because you typically at high redshift, if you want to be studying a bright object at least, you have to be studying a very luminous quasar. It's going to have a long lag time scale, plus cosmological time dilation makes it even longer. And so these types of reverberation mapping experiments out at high redshift may take decades to do. But, yeah. What? You don't get immediate results. Hopefully they'll be very satisfying when they're done. I've actually been, I've been doing such measurements, in fact, since the late 90s. on a few high redshift quasars with the telescope, the Hobby Beverly telescope at Penn State, and we hope to actually get measurements for high redshift quasars. But it takes a very long time to do it. You have to be very patient. Yeah, so don't do it if you don't do it while you're a graduate student. Wait till you have tenure, and then try to do it. Yes. Okay. Yes.
Since the mass of BLR is very large, but only a fraction of it is emitting light.
What's that? Since the mass of the broad is
It's pretty large. It's 1,000.
yeah. That's the mass emitting at any given time is much smaller. But yeah, the total mass is pretty big.
Does it mean that BLR region is optically thick?
No. It's still optically thin. You take that much mass and you spread it out over that size scale. It's not enough to make it beyond optically thick. It's still optically thin.
What about the rest of the map? About the rest of the...
The rest of, what do you mean the rest? I mean, you mean like from the narrow line region and so on? Or what?
No.
I mean, you're talking about all of this gas? Yet you take all that gas and you spread it around over that physical volume, and it does not make the thing optically thick.
This includes the narrow line.
No, the narrow line region's in addition to that, but that still doesn't make it optically thick. We know these things are pretty optically thin. Just from the fact that you can see rapid X-ray variability, for example, tells you you're dealing with a pretty optically thin region. Yeah. So you're not hitting the region of you aren't hitting optical thickness yet. Now there are. I mean, I'll say much more about the narrow line region later on, and there can be parts of the narrow line region that can be optically thick, owing to dust being present in the narrow line region. And I'll say more about that later on. And I mean, another question, which I'm sure you're all wondering about, is I told you right at the start back here that, there is this, I've told you how the lines appear to separate out into these two distinct regions, the broadline region and the narrow. But you might say, why is that? Why is there a broadline region and a narrow line region, and why are they distinct from each other? Why isn't it just a continuous region of some kind? And I'll talk about why that's the case when I talk about the narrow line region. Yeah.
Can you also tell exactly which part is the disk and which part is broadline region?
Can you tell which part is the disk? Well, yeah, right now, not entirely. That goes back to what I was saying here on this last slide here about the nature of the broadline region. I mean, one of the favored suggestions out there, and it's not proved, but one of the favored suggestions out there, in fact, is that much of the broadline emission may actually be coming from a disk. So maybe it partially is maybe some of the outer parts of the disk are responsible for some of the line emission, some of the low ionization line emission. We don't know that for sure. That's one of the reasons why measurements like these velocity resolved reverberation mapping experiments are very important, is to try to settle that very clearly. Yep. Yep. Okay. Oh, yeah, go ahead.
For those low luminosity AGNs,
Yes.
do they have
Low luminosity, yes, some of them do. I believe there are some, if you go down to quite low luminosities, here NGC 4051 is fairly low luminosity. It has one. There's another object, NGC 4395, which is one of the lowest luminosity AGNs known. It has a broadline region, but I don't remember all the subtleties here. There may be some complications with, down at very low luminosity, some objects not having broadline regions. But I don't remember all the technical details there. I could show you relevant places where you can read about that. But there certainly are some very low luminosity objects, like that one and like NGC 4395, that do have broadline regions. But there may be other objects that don't. And I've read some things about that. I can show you the literature on that if you're interested in learning more. Yep. Yes, go ahead.
When you calculate the black hole mass,
Yes.
you assume that
When we did, let's see, you're talking about with this. Here? What, you mean this equation is what you mean? Right.
But even for one photosource, you also mentioned that there is an addition spectrum.
There's ionization stratification. Yes, yeah, that's right. Of what I mean by that is that lines of different ionization levels are formed in physically different regions.
Yeah. So, my question is how this assumption a constant ionization current is reliable?
Okay, I see what you're asking. Okay, so what I meant when I said that. You know, and I believe that was back when I talked about, let's see here. I believe that was here when I was talking about how the line versus the lag shows that relation. I'm trying to find what I was referring to there. Where was that? Is that back here? Back more. It was at L to the 1/2. Here it is. There. This is what you were interested in, right? The R going as L to the 1/2. Right. So what I was saying there, what I was trying to say there is that this is showing for a single line, not for multiple different lines. For a single line, in these cases, I believe it's always for H. It's for H beta for both cases. Here you can even see these are all for the H beta line. So for a single line, okay. For a single line in different sources, yes, you know, this is the relation that you get. But for that, the evidence is that H beta is formed at a similar ionization level with a similar ionization parameter across many sources, just from the fact that, again, if you just do this simple prediction where you just write down the equation for ionization parameter, if that is a constant, you can then you expect that the radius will go as the luminosity to the 1/2, or the lag will go as the luminosity to the 1/2 power. And the fact that we see that pretty closely for a single line seems to indicate that it's okay. Now, that's always for a single line. Now, when you start looking at multiple different lines, which is what I was talking about when I was showing plots like this, well then, of course, you're going to see stratification. You know. You see the difference there? The difference there is you're looking at multiple different lines here, whereas the other case you're looking at a single line across multiple objects. That's the difference. Yep. Good. Any final questions, or is that good? Okay, great. Well, thanks a lot. Thanks. Okay, I think we should get started. So today we're going to continue with the observational overview of active galactic nuclei. And we're going to continue talking about, for the first part of today, observations on small scales. So we're in our second chapter right now. You'll remember that yesterday we talked about observations of the black hole region, often made with X-ray astronomy observatories. And we also talked about the Broadline region. And we're going to finish up this chapter, probably before the break, talking about outflowing winds. And then we're going to move on to observations on large scales. And we'll start talking about the narrow line region, and we may get into talking about the Torus some as well. So that's where we're aiming to go for today. And then tomorrow we'll continue talking about the Torus and jets. And then ultimately we'll move on to this more focused lecture on AGNs and what we can learn about them in X-ray surveys. So that's an overall view of where we are and where we're going. Any questions about that? Does that seem sensible to everyone? Okay, so I'm just going to have to skip ahead because we've already covered all this stuff on the black hole region. You'll remember all this from yesterday. And we've covered the Broadline region. We talked about that in detail yesterday, and we finished that up. And I'm moving ahead to talking now about outflowing winds and why they're interesting and what we know about them. Okay, so that's where we're going to be focusing on now. So we've known for a long time that many quasars as well as many lower luminosity active galaxies as well, show blue-shifted ultraviolet absorption lines from outflowing winds, and we're going to talk about these. Here's an example I showed you previously of broad absorption lines, and by that I mean these are the absorption lines that we're focusing on here, and you can see that these troughs have these absorption lines, or absorption troughs as they're often called, have a significant breadth to them, okay? Thousands of kilometers per second broad in this particular case here. And these objects are, with the very broad absorption feature, are known as broad absorption line quasars, or BAL quasars. And we see bona fide broad absorption lines in about 10 to 15% of optically selected quasars. So this is a pretty common feature in quasars. It's not like we only see this 1% of the time or something like that. We see this a good fraction of the time. And due to various selection effects, we actually believe that the true fraction of quasars that contains these broad absorption lines is even higher, is perhaps 20 to 30%. Okay, so this is a significantly common feature in quasar spectra. And we know of many examples of these broad absorption lines. Here's a selection of a few more, focusing in here on the absorption in the very strong and well-studied carbon-4 transition. And you can see that these broad absorption line profiles are complex and diverse. There's certainly, here are 4 different examples, and each one you can see is significantly different from the next. And you'll often have multiple absorption features that almost appear like distinct ones present. Okay? And so these are examples of broad absorption profiles. And you might wonder, well, is this term broad absorption lines rigorously defined? What do you exactly mean when you talk about a broad absorption line? Well, we do have a definition. It's one that was set up long ago by the people who were first studying these features. And specifically, the broad absorption features are ones that are broader than about 2,000 kilometers per second in width. Okay, so their widths are more than 2,000 kilometers per second. That's the definition of a broad absorption line. Okay? Then people realized that there's also intrinsic associated absorption with quasars that can be narrower as well. And so they made up the terminology of mini-BALs, okay, which are somewhat narrower than the BALs. They have widths between about 500 and 2,000 kilometers per second. And then there's even narrower ones still, which are referred to as narrow absorption lines, which have widths less than 500 kilometers per second. But we think all these absorption features are actually significantly related to one another. Okay? And we have now been able to identify very large samples of broad absorption line quasars, for example, from the Sloan Digital Sky Survey. In fact, here is a plot showing luminosity versus redshift for about 5,000 broad absorption line quasars that were found in the Sloan Digital Sky Survey. And this was actually, as you can see, back in 2009. We actually have a much larger sample still now, because the samples have only gotten larger over time as Sloan gets more and more spectra. So we have large examples of these quasars showing wind features. And there's a lot of interesting things you learn when you look at a sample like this. Here's one very interesting thing that was found, is that, so this plot illustrates a couple of things. It illustrates that we find these ultraviolet absorbing outflows, these ultraviolet absorbing winds, over a wide range of luminosity. You can see down here, this is the luminosity at 3,000 angstroms, and you can see that every point in here is a quasar that shows a wind absorption feature of some kind. And you can see that we see these wind absorption features over 1, 2, 3, 4, almost 5 orders of magnitude in AGN luminosity. Okay? Furthermore, along this axis is plotted the maximum observed velocity of the outflow. And you can see that doing this sample work shows something quite interesting. It appears that more luminous quasars are able to launch winds that have higher maximum outflow velocities than lower luminosity AGNs. Okay? There's this sort of envelope here where luminous quasars can launch both low velocity winds and high velocity winds, but low luminosity objects are only launching winds of relatively low velocities. See that there? So that's a quite striking result right there, the fact that luminosity really seems to have something significant to do in the driving of these winds, because it appears to have a role in setting the maximum velocity that an outflow can achieve. Okay? And I just want to show you, so what I've been showing you back here then are examples of these absorption features in quasars, in highly luminous AGNs. If you go down to lower luminosities, down to the safer galaxies, we also see these wind absorption features there. Here's an example of a nearby, much lower luminosity safer galaxy, NGC 4051, one of the original safer galaxies studied by Carl Seyfert back in 1943. And you can see here these absorption troughs here in carbon-4, nitrogen-5, and silicon-4. And here you can see they're sort of doubled, and that's because it's a doublet transition there, so you get the repetition of them. And then here are many additional absorption features in carbon-2 and silicon-3 and so on. Okay? So we see these absorption features in safer galaxies as well, but as you would expect from this plot here, the safer galaxies would be down here at the lower luminosities. They're generally lower velocity outflows and narrower outflows than the broad absorption lines that we see in luminous quasars. Yeah? The absorption features, okay, the absorption features almost always appear to be blue shifted. I will tell you, in fact, I've done some work on this. About 0.1% of the time, you will also see red-shifted absorption features, but they're very rare. So 99.9% of the time, yeah, they're blue-shifted. 0.1% of the time, very roughly, they can be red-shifted as well. And if you're interested in the red-shifted ones, I can tell you about them, although I'm not going to focus on them today because they're such a tiny group. Yeah, so it's almost always blue-shifted. Okay, that's a big clue as to what's going on, and I'll talk about exactly what's going on in a minute. Here I'm just describing what we can observe. And so all these observations here that I've covered so far, there, and even those measurements, that's all measurements in the ultraviolet. Okay? But I also want to stress that we can see these outflows as well in the X-ray band. Okay? Here's an example of these ultraviolet, these outflowing absorption signatures seen in the X-ray band. And so this is a broadband X-ray spectrum now. You can see here that's 1 keV, 2 keV, going up to like almost 10 keV over there. Okay? This is a broadband X-ray spectrum, okay, of a local safer galaxy. And you can see that there's this whole forest of jaggedy things here, right? And that's not noise. None of that's noise. That's all signal. Those are literally hundreds of absorption lines being imprinted upon the spectrum of this safer galaxy from an outflowing wind. Okay? And we call these, in the X-ray band, these are referred to as X-ray ionized absorbers, or sometimes they're called warm absorbers. Okay? And they're seen in about half of safer galaxies. And so these things are commonly seen in safer galaxies. They have typical column densities studied in the X-ray band between about 10 to the 21 and 10 to the 23 particles per square centimeter. And the gas that's imprinting this absorption is likely in multiple phases of ionization. And I'll say more about that in a minute. And we believe that the material causing much of this X-ray absorption has a significant relation to the material that causes ultraviolet absorption in safer galaxies. We don't think these are two totally unrelated things. We think that the gas that makes much of the X-ray absorption has a significant relation to the gas also creating the ultraviolet absorption. In particular, the ultraviolet absorption that has high ionization levels, it shows high ionization levels, is likely that also causes the X-ray absorption. Okay. Now, so that's one thing you can see. You can see this whole forest of absorption lines. And I want to show you those in more detail. If you actually zoom in on this part of the spectrum where you see all these absorption lines, this is what you see here. Okay? So this is a broadband spectrum. And you can see here it's It's running in wavelength here from, well, 13.5 down to 10.5 angstroms. Here's 10.5 to 7.5, 7.5 to 4.5. And so there's so much wavelength being covered in the X-ray band that you have to actually stretch this out over multiple plots. And you can see all these little absorption features. All of these are real absorption lines imprinted upon the X-ray spectrum in this case. And there's about 150 of them in total that we've identified. Okay? And so you see lots of absorbing features here. Okay? And unfortunately, this plot doesn't come through very well here. But this is the dots here are showing the X-ray data as a function here of radial outflow velocity for this particular object, which happens to be NGC 3783, if any of you care about exactly what object it is. And the red here is showing the ultraviolet absorption, which matches very nicely in kinematic properties the X-ray absorber, strongly suggesting that they're related, that they share the same kinematics, okay, which suggests that they really are quite closely related. Okay, so that's one thing that we see in terms of X-ray absorption signatures. We see absorption lines, okay, from bound-bound transitions in atoms that are absorbing X-rays. But we also see other absorption features as well. We see edges as well. And are you all familiar with the phenomenon of edges as opposed to lines? You know that lines are made from bound-bound transitions in atoms, and edges are made from bound-free transitions in atoms. When you take an electron bound to an atom and you knock it entirely out of the atom, then you get a different absorption feature called an edge, which gives you a broader absorption signature. And this overall drop here and rise upward is due to an edge setting in about there and then recovering as you move away from the transition energy, from the resident energy of the edge. Okay, that's an edge absorption feature. So you have both the absorption lines and the edges being made in the X-ray band. Okay, right. So that's an example of, those are examples of what we see in terms of absorption features. And again, the X-ray absorption lines are blue shifted essentially always. I'm not aware of any clear case of a demonstrated red-shifted X-ray absorption line because the samples are much smaller than in the UV. And so it appears that here we also have some kind of outflowing material. So now what's going on? What do we think is going on to make these red-shifted, blue-shifted absorption lines in the ultraviolet and the X-ray band? Well, here's a model that is commonly discussed, okay, to explain this. The idea is that we're looking through a line-driven wind that's often envisioned to be equatorial, although it probably isn't always equatorial, okay? And it's thought to be driven off the accretion disk or perhaps off the torus with high velocities of sort of 100 up to 30,000 kilometers per second. And those are very impressive velocities. I should have mentioned that. If you go back here and look at this plot, I mean, look at the velocities up here. I mean, that's 30,000 kilometers per second. That's a tenth the speed of light. Okay, so some of these winds can be launched at terrific velocities outward. I mean, far faster than any winds on the Earth. These are million miles per hour or many millions of miles per hour winds. You wouldn't want to get caught in one of these. Okay, and so these are very fast winds. And the idea then is so in this picture, this is showing the accretion disk here. And this stripy stuff here is representing wind material that's being launched up off the accretion disk, being driven by line pressure, okay? And we're looking through this material, and when we look through it, okay, with our line, you know, you're looking through outflowing material, so you get a net blue shift, okay? And that material is what is imprinting these absorption features on the ultraviolet spectrum. In this case, in the ultraviolet, that's the carbon-4 absorption features. Does that make sense? So I want to say a little bit more about this line driving of the winds. How does this work? So the idea here is that this wind material, you know, lying slightly up above the disk, starts to absorb photons from the brilliant central source. And when it absorbs those photons, it not only absorbs their energy, it also absorbs their momentum. And so that pushes the material outward. And that's what allows the material to be pushed outward to these terrific speeds that you see. is its line driving, its absorption line driving. And this plot here shows the effect of this sort of line driving. And it compares the strength of outward pressure that you can get from line driving compared to that just for standard Thomson scattering, for electron scattering. The electron scattering pressure is what, of course, sets up the Eddington limit. Okay? And so that would sort of correspond to a value of 1. And this shows the force multiplier over and above what you get just from pure electron scattering as a function here of the ionization level of the gas. And you can see for moderate ionization levels, you can get pressures on the outflowing material that are 100 or 1,000 times stronger than just from pure Thomson scattering. And so this line driving is really a very effective way to push out material. And of course, this is the same way that massive stars launch winds. You probably all know that things like O stars and B stars also launch high velocity winds, right? And those come from this same basic type of phenomenon, line driving of the winds pushing the material out. Okay. And so the common transitions that we see in the ultraviolet are, you know, just the strong resonant lines of things like carbon-4, silicon-4, magnesium-2, and aluminum-3. And in the X-ray band, the transitions that we commonly see here in the X-ray band, making all of these lines, are things like the hydrogen and helium-like transitions from the abundant elements. Things like carbon, nitrogen, oxygen, magnesium, silicon, sulfur, okay, iron. All those abundant elements you see in their hydrogen and helium-like absorption transitions. The lines that we're observing, all these lines that we're seeing here are predominantly from those types of transitions. Furthermore, another thing is that you'll often see multiple lines from the same transition. Here's an example of that. Here's carbon-4, and you can see here's one absorption trough, here's another one, and here's another one. You have 3 distinct absorption troughs, all from carbon-4. Okay? And so it appears that oftentimes you'll actually have not just a single wind component along the line of sight, you know, at a single velocity, but you'll have multiple components along the line of sight. Okay? And a couple of other things then is that, well, what about the widths of the lines? How are the lines so broad? Again, it's not thermal broadening that makes them broad. The idea here is you're actually seeing a wind that's accelerating. Okay? And so you're looking through accelerating material that has a range of velocities, and that's what leads to the broadening of the lines. Okay? So you're seeing a wind accelerating out, and you're looking at its acceleration region. And we believe that, in fact, most active galaxies, at least of moderately high to high luminosities, drive these winds. Okay? And the fact that you only see them 10 or 20% of the time, as I mentioned earlier, is an orientation effect. Okay? In that the lines are only thought to cover, you know, some fraction of the sky. And so in this case, you know, if your orientation, if you indeed have an equatorial type wind, you're only going to see it when you're looking at the system when it's fairly inclined. If you were looking instead at the system straight down like this, you might not see much wind absorption in that case. That makes sense. So it's an orientation effect. So it's not like we think these winds are only there 20 or 30% of the time. We think most AGNs are driving these winds, and orientation determines whether or not you see them in a particular system. Okay? And furthermore, we believe then, so the question then is, where is this wind material lying? Well, we believe that in different systems, it likely exists over a wide range of radii, starting down at very small scales, down at 0.01 parsecs in some cases. I'll tell you about variability evidence that some winds lie on such small scales. And some material is likely out on much larger scales, is perhaps out on kiloparsec scales. In fact, we have evidence that the wind material often lies outside the broadline region. You can see that pretty directly here. And that here is the carbon-4 emission line, right? And you can see the carbon-4 emission line is being strongly absorbed on this side from the wind material, right? And so that's telling you pretty clearly that the wind material has to lie outside the broadline region, and at least in this particular case, because it's able to absorb the broad emission line. Otherwise, if it was inside, then the broad emission line wouldn't be affected by the wind material. You see that? Okay, so you get a clue as to where it is just by looking at simple spectral signatures like that. Okay, so again, then to put it into context, going back to our sort of powers of 10 diagram for AGN. So here is the broadline region that we've talked about substantially yesterday, likely having some kind of disk-like component and some kind of wind-like component. Okay, and the outflowing wind, in many cases, likely lies just outside that. Okay, here are the absorption clouds, is what they're referred to as here, although it may actually be a continuous flow, okay, lying just somewhat outside the broad emission line region. Okay, so that's where this is located in the overall scheme of things. So that's nice. There are winds in AGN, but why does that matter? Why do you care that there's winds in AGN? Okay, well, there's several reasons why. Here they are. First of all, these winds significantly affect the observed properties of AGNs. Okay, and they do this in many ways. They do this via the ultraviolet line absorption we've just talked about. Furthermore, you'll remember yesterday we talked about how some of the high ionization line emission from the broadline region likely is associated with the wind. So they also make line emission in many cases. They can also imprint reddening. Many times you will see preferential amounts of reddening in quasars that show these wind features. So there may be dust sometimes in some way associated with the wind, or at least along the line of sight where the wind is present. Okay? Furthermore, many times you will see enhanced polarization among quasars that have strong absorbing winds along the line of sight, likely associated with scattering or radiation of some kind. And furthermore, you have the X-ray absorption that we've been talking about. So you affect many of just the basic properties of AGNs with winds. And then secondly, we know these winds are a substantial part of typical AGN nuclear regions. They're seen in absorption in roughly 30% or more of AGNs, if you include the broad absorption lines and the mini BALs and the NALs all together. You see it in more than 30% of AGNs. And then, of course, as I've just said back here, we believe that, in fact, most AGNs likely are driving these winds. Okay, so it's not just 30% of them. We think all of them do, and it's just orientations. That's whether you see it or not. These winds may be important for helping black hole accretion to proceed. As you've learned about from the theoretical lectures, it's not easy to get material out here and move it into there. Okay, the material has to lose a tremendous amount of specific angular momentum, okay, to get from out there to in there. You have to expel that angular momentum ultimately in some way to allow material to accrete. One way that may occur is via a rotating wind. If you're flinging off material from the disk that carries away some of the angular momentum, that can help some of the material work its way inward so it can actually accrete. And so these winds may be essential in allowing accretion disks to work. Okay? And then finally, and I'll talk about this more later on, we believe that these winds can evacuate substantial amounts of gas from certainly the central parts of the host galaxy, and thereby perhaps affect the further growth of the black hole as well as galaxy evolution. If these winds, for example, interact with the interstellar medium of a galaxy and can cause a significant part of the galaxy's interstellar medium to be ejected, that may halt star formation in a galaxy, for example, and thereby may prevent further growth of a galaxy's, at least its stellar content. And so those are the reasons why I think winds are worth studying and worth discussing in some detail. And I'll just sort of show you that there are many people, it's not just me who cares about AGN winds. Here's an entire conference, okay, on AGN winds that was held a few years ago. And this is part of a series of conferences. Here's the conference photograph from this particular conference. And so there are entire conferences that are held every few years just on AGN winds and trying to understand them in some detail. So there's many people who are working on AGN winds and trying to understand all their properties. And you may recognize some of these people. Okay, so a few more things about the winds. This is another sort of interesting aspect of winds. It appears that the fraction of luminous AGNs, of quasars, showing the very strong broad absorption line type winds, actually appears to depend upon radio power. Okay, and here's one example of many studies on the topic, where generally the fraction of quasars showing broad absorption lines tends to go downward by a significant amount, from like 30 or 40% down to something like 20 or 10%, okay, as you turn up the radioluminosity of the AGN. And of course, this is related ultimately, the radioluminosity of the AGN is mostly related to the jets, okay, that AGNs launch. And so it appears there may be some link between the launching of winds and the launching of jets in AGNs, okay? The reason for this relation is still not entirely clear, even though it's been very well established. Some people have proposed that there may be some kind of connection between winds and jets in AGN, and AGNs may tend, this isn't a strict rule, but may tend to launch either a highly relativistic collimated outflow in the form of a jet, or sort of a poorly collimated subrelativistic outflow in the form of a wind, but usually not both. Okay, there may, so in other words, winds may have some connection into the formation of jets. Other people propose that there may be orientation effects coming into play that lead to either the preferential detection of jets or not. You can read this paper by Shankar et al., for example, if you're interested in such things further. Okay. And so that's another remarkable aspect of these. I want to say a few more things now about the sort of connection between X-ray absorption and ultraviolet absorption in these winds. But this is a good place to pause to ask, are there any questions about what I've been covering so far? Yeah. How is it related to the fraction of type 1 AGN versus type 2 AGN? Is this what you're saying? Yeah. Okay, well, so generally, we only see these winds clearly in type 1 AGNs. Usually you don't see wind signatures so clearly in type 2 AGN. Now they're probably there in type 2 AGN, but it's just because there's so much other material, the Torus, which we're going to talk about shortly, providing obscuration on larger scales, you generally don't see the wind. But they're probably there in both type 1 and type 2 AGNs. And in fact, some people have proposed, and this is not proven, but some people have proposed, going back to sort of a diagram like this, in fact, that the Torus, the thing that we call the Torus, may actually be a wind. You may actually have a very thick, dusty wind that actually is the thing that we call the Torus. Now, that may be true. It may not be true. We don't know. But winds may have an important role in the unification of AGNs, if indeed the Torus is in fact just another component of a multi-structured wind. Yeah. And if you're interested in that, I can give you some references of people who discuss such things. Yeah. Any other questions at this point? Yeah, go ahead.
The geometry of why the slope is not so more different.
You mean in this, why is it not?
If you see from the top of the why can't you see the outflow?
If you look down this way, you mean?
Yeah.
Okay, so I mean it's just a geometrical effect mostly, in that people often propose that the wind has some kind of basic equatorial nature. This is not rigorously proven, and I suspect there's exceptions to this in some objects, but broadly speaking, they propose that the wind has some kind of an equatorial nature, as being shown here. And so if you're looking along a line of sight that's fairly equatorial, you're going to be looking through a lot of wind-absorbing material, and so you'll pick up quite strong absorption lines. Whereas if you're looking in a highly pull-on manner, looking directly down like this, you may pick up just a little bit of wind material or no wind material, and so you won't see the wind absorption features. Is that answering your question?
I want to know why. Why is that?
Why is the wind equatorial? Why is the wind equatorial? Okay, we don't fully know. Okay, it deals with subtleties of how the winds are formed. I'll show you some simulations later on that will have some relevance to that. But the idea generally is that you have some wind material that starts to lift up off the disk a little bit. It suddenly gets hit by the radiation pressure from the central source and gets pushed out at very high speed via this line driving process. And so there's a lot of momentum pushing it outward. And of course, that's going to push it outward. It's going to try to push it outward in a radial direction. Okay? And so you may, and so the idea is that you then tend to get wind streamlines, clumping close to the disk and not launching preferentially outward this way so well. But the details are not totally clear here. We're still, one of the things people are trying to do is they're still trying to work out the geometry of these winds. Yeah. Okay. Yeah, go ahead.
Is there a typical temperature of the wind? I mean, if it's likely to practice some countries on temperature?
Yes. Yeah, certainly. Well, the constraints are most importantly relevant to the ionization level of the wind, or the ionization parameter. That's what this is here. So this is the ionization parameter of the wind here. But certainly, the fact that you see transitions from things like carbon-4 and nitrogen-5 tell you something about, about the ionization level. And for a photoionized plasma, that tells you something about the temperature. And the temperature is typically of order 5,000 to 20,000 Kelvin in round numbers. That's the sort of range, similar to the temperatures of the Broadline region. Yeah, that's right. Yeah.
I wonder whether there are something like optical broad absorption.
Do you ever see optical broad absorption lines? Generally not. You typically see these things. You typically see these transitions in the ultraviolet most strongly. Where you have strong resonant lines. But it's for the same reason that we see a Lyman alpha forest, but you don't see an H alpha forest. Okay, it's because the wind material is generally too highly ionized to get strong resonant absorption down in the optical. But there are a couple of cases. If you're interested, one example is NGC 4051, where people do appear to see some intrinsic absorption in optical lines as well. But it's quite rare. And it's for the same reason why there's a Lyman alpha forest, but not an H alpha forest. It's because the material is generally too highly ionized. Yeah, that's right. Yeah. People have, yes, there have been some estimates of that. I'm going to show you one at the end. There are computations by Andrew King, for example. I'll show you some papers, as well as by, King has done a lot. There's also some computations by Hopkins that suggest that indeed, yes, you can drive out a lot of material. But there are significant uncertainties still in establishing the total kinetic power of these winds. And until that is nailed down much better by measurements, the theoretical predictions are going to have large uncertainties to them. But it certainly appears plausible that, yes, you could drive out a lot of material with winds. Yeah. And I can, again, I'm happy to give references on that. Yeah. So there was, yeah, go ahead.
I wonder if any particular reason the possible X-ray in safer, not just quasars.
Ah, yes. Okay, good question. I'm going to show you X-rays from quasars in a little bit. The challenge there, okay, I'll give you the basic answer. Yes, so she's asking a good question. She's asking the question, why did you talk about the X-ray absorption in only Seyfert galaxies, whereas you showed all this stuff about absorption here in quasars, as well as in Seyfert galaxies in the ultraviolet? So this is actually predominantly a technical issue, in that to do this kind of work, to see these absorption lines, you need high spectral resolution, okay, to do it. That's true both in the ultraviolet and the X-ray. And for a long time, we've had, since the 60s, we've actually had the capability to do very high throughput, high resolution spectroscopy in the optical UV. In the X-ray band, that's much harder. Typically, in the X-ray band, the detectors you're using are CCD-based detectors that give you much poorer spectral resolution. The typical resolution of a ultraviolet or an optical spectrograph is going to be a few thousand, where the typical resolving power of an X-ray CCD spectrometer is like 50. So it's 20 times worse. Okay, so that's been the problem generally. So the way that we've managed to make measurements like these, in fact, these measurements I was heavily involved in making, is you actually have to put a grating spectrometer along the line of sight to your X-ray detector. And this is possible, but for example, both Chandra and XMM have grating spectrometers on them, but it takes very long exposures to get high quality measurements in the X-ray band, because the count rate is low, and because you're dispersing the X-rays, and because you actually get a lot of loss of X-rays in the grating mechanism itself. And so for all those reasons, in fact, this observation here, that was 1 million seconds of Chandra time to get those data. These data we had to expose for 1 million seconds with Chandra to get those data. These are very expensive observations in the X-ray band. And that's just for a nearby Seyfert galaxy. So talking about a quasar, which is generally much fainter in terms of its flux, there is going to be even more expensive. And few people have tried, almost no one has tried to do such measurements for a quasar because they'll be extraordinarily expensive. So it's a technical limitation of what we're able to do. There is a great desire among people in the X-ray astronomy community to build better spectrometers to do this type of stuff. You may have heard that recently in Europe the Athena mission was approved. The Athena mission is a much larger aperture X-ray telescope that will give you grading. And it won't let it grade. It'll have another type of device, a microcalorimeter. It will give you a very high spectral resolution, high throughput measurements, in the X-ray band for the first time. They'll let you go do such things in quasars. But trust me, if I could go do this in quasars, I'd go do it. I'd love to do it. But it's not an easy thing to do. Yeah, that's right. Any other questions? Yeah, go ahead. Why do we think? Yeah, okay. May I defer that for a moment? I'm going to show you some evidence for that shortly. Variability is one example. We often see these wind absorption features changing on fairly rapid time scales. And on the time scales you would expect, you can translate that into a physical size scale that suggests you're probably dealing with something in the accretion disk type region. That's the evidence. But you'll probably note that, in fact, I sort of hedged it back here, and that I sort of said, if you see here somewhere, I said something about how it comes from the accretion disk or torus. I sort of hedged it there a little bit, and that's because there is still real uncertainty in some cases as to where it's coming from. And down here, you'll probably recall, I mentioned how the wind material probably exists over a wide range of radii, down to sub-parsec scales, and out quite likely in some cases out to kiloparsec scales. Some of that large-scale absorption likely does come from something more like a torus than a disk. But the standard model that we think applies for most cases of these ultraviolet absorption features is likely a disk-related model. Because most of them, as I'll show, seem to vary pretty rapidly as one example for why we think they're on the right scale. Yeah. Okay. Any final questions? It's good. Yeah, great. Go ahead. You didn't hear how hot it was? How it's created. How was it made? Okay, so I'll go through that again. So her question is, how is the wind made again? So the idea is that this is a line-driven wind. Okay, so you have you have this brilliant radiation source down here close to the black hole that's producing large amounts of radiation in the ultraviolet, well, in the extreme ultraviolet mainly, and in the ultraviolet, and so on. Okay, and you then have some material from the disk that starts to get struck by some of this radiation. It starts to feel a strong pressure force upon it, because when it absorbs the radiation that strikes it, it picks up not only the energy of that radiation, the ionizing energy of it, it also picks up the momentum of that radiation. So that pushes it outward. And that's what I meant when I was talking about these force multipliers. It pushes the material outward with a force that's 100 or 1,000 times stronger, at least at fairly low ionization levels, 100 or 1,000 times stronger than you would get just from pure electron scattering. The same thing, and the same phenomena drives the winds of O stars and B stars. Okay, and then that material gets pushed outward via the momentum, and it starts to accelerate outward. And then more radiation strikes it, and it gets pushed outward even more. And you see it, and the material accelerates and accelerates and accelerates outward to form this high-velocity wind. So that's how it's being made. That's the idea. It's a line-driving, it's radiation pressure-driven, and specifically radiation pressure acting upon those I mean, these lines here, those absorption lines, are what makes the wind go. Is that when it gobbles up the photons to make those lines, those photons push upon the wind material and makes it fly outward. That's what drives it. Yep. Okay. Yeah. Well, yeah. I mean, we see carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron.
So I wonder
Whether I see. You're saying that does the hydrogen get carried along for the ride with the carbon? Yes, we believe it does. We believe that the plasma is exchanging via scattering, is exchanging momentum sufficiently rapidly that, yeah, the hydrogen gets carried along for the ride. It's not just pure carbon coming out or something like that. Yeah, that's the belief. Yeah, we see absorption in Lyman alpha. You often see Lyman alpha BALs. And so that tells you there's hydrogen in there. Yeah. Yeah, so Lyman alpha transition is one example. Yeah. Yeah, okay. So any final questions? It's good that we're going through this. Okay, so I'm just going to say a few more words about these winds now. I want to say a few more technical things, okay, about how these winds work. Okay. And there are some challenges here. Here's one of them. And so I'm going to say a few more words now about, and this goes back to your question about what should the X-ray absorption be doing in the quasars. Okay. Well, we've thought about this quite a bit. Many people have thought about this quite a bit. In fact, there was a highly influential paper by Murray et al. That's worth reading if you're interested in this topic, as well as further simulation work by Proga that it sort of backs up the original analytic work. Considering in some detail how you could actually launch one of these winds. And so here's a schematic that shows down here the supermassive black hole, the X-ray emitting region, the ultraviolet emitting region out here further in the disk, and then here's the wind coming out. And there are some real challenges, in fact, in launching these winds. One of them is that the X-ray emission that we see from these quasars from small scales, which we know is very commonly there, is so strong that it has a tendency, in the absence of something to help the situation, it has a tendency to, in fact, over-ionize the wind, and to ionize the wind to such a level that transitions like carbon-4, the ones we were just talking about back here, carbon-4, silicon-4, magnesium-2, aluminum-3, the ones that are so essential for driving the wind, they tend to get over-ionized, so that those transitions tend not to, they're predicted really not to exist very well in the wind material, given our understanding of it. And so people have invoked, Murray et al. Proposed this first, proposed that there has to be some kind of additional material on small scales, which they call the shielding gas, that plays a critical role in the driving of these broad absorption line winds. And so there's some kind of shielding material down here on small scales. We don't know its exact geometry, so here it's just drawn as a little cloud, although it probably isn't just a little cloud like that, okay? That shields the wind from the harsh glare of the X-rays coming out on small scales, and thereby prevents the wind from being over-ionized. And so that was predicted to necessarily be there just on theoretical grounds of allowing these winds to be driven at all. And in fact, notably, further observations have shown very nicely that Murray et al. And Proga were actually almost exactly right, in that you actually, and this goes back to your question about X-ray absorption, while we can't get extremely high-quality grading measurements of X-ray absorption, you can get basic CCD measurements to get basic estimates of absorption. And we actually commonly see some kind of heavy X-ray absorption with properties very consistent with the shielding gas in X-ray when we study X-ray absorption. Here, and I'll show you an example of that, where we actually see nice relations found between the level of X-ray absorption and the ultraviolet absorption strength and its velocity. Here's a plot. Oh, I see this didn't come through very well. I'm sorry. But this is a plot that shows the relative strength of the X-ray emission compared to the optical emission, defined according to this formula, if you're interested in the exact detail, okay, versus the strength of carbon-4 absorption in the ultraviolet, okay? And this is set up such that X-ray weak quasars live over here, presumably corresponding to objects that are heavily absorbed by some kind of shielding material, and X-ray strong objects live over here, okay? And you can see that quasars show a range from having rather weak or no absorption in the X-ray, but also showing essentially no significant strong carbon-4 absorption, to being sort of moderately X-ray absorbed and having much stronger carbon-4 absorption, to having over here strong X-ray absorption and also strong carbon-4 absorption. So the fact that you see a relation between the level of X-ray weakness, which presumably reflects the level of X-ray absorption that's present, and the strength of the ultraviolet absorption suggest that, yeah, the X-rays really have an important role in the launching of these winds. And this is very impressive in that this plot spans, it shows this correlation between the level of X-ray absorption and the level of ultraviolet absorption over very broad ranges. This is a logarithmic quantity here. And so the X-rays along this axis span about a factor of 400 or so in the level of X-ray strength. And the level of carbon-4 absorption here spans 3 orders of magnitude. And you can see over these tremendous ranges, there's a broad relation there, suggesting that, yeah, indeed, the X-rays have something critical to do. Some kind of shielding material has a critical role in allowing the wind to launch at all. Now, then, what is this shielding material? That's a natural question to wonder. What is it? I mean, it's nice that they said it should be there. Well, the best idea that people have, in fact, is that this is some kind of a wind also that tries to launch on even smaller scales, but gets over-ionized and stalls and perhaps falls back toward the black hole. That's what these little arrows are sort of showing as some kind of schematic as to perhaps how it moves. So in other words, the idea is that a wind tries to launch at all radii, small radii, moderate radii, large radii, but the material that launches on too small of a scale gets blasted by the X-rays, gets ionized, and fails to launch, but sort of sacrifices itself. It's actually called the sacrificial wind. Sacrifices itself so as to allow a wind on larger scales to actually successfully launch. That's the idea. And this whole model seems to hold together pretty well. I want to show you some further evidence for this idea. Here are a couple of more plots. And again, this shows the relative X-ray strength, with X-ray weak objects being over here and X-ray strong objects being over here, versus, again, the carbon-4 absorption strength. So this is very similar to the plot I just showed you here. And you can see that while there's a lot of scatter, there's a general trend here such that objects with strong carbon-4 absorption tend to be more X-ray absorbed. Over here is another plot that's quite interesting. It shows, this plot showing, again, the maximum velocity of the outflow versus luminosity, both for objects shown in black here that are fairly X-ray strong, and for objects in red that are fairly X-ray weak. And look where all the red ones lie. They lie preferentially at the high velocities. And so it appears that if you have X-ray absorption present in your quasar, you're actually able to launch a wind along the line of sight, at least, that achieves a higher velocity than you are when there's not that X-ray absorption there. So it appears that this whole idea of shielding material on small scales has an important role in allowing the winds to launch. So that's a few more things about the X-ray absorption in quasars. That's what we can do. These are much more basic measurements, again, than one would like to be able to do. I mean, what one would like to be able to do, to go back to your question, you'd like to be able to go and get a really high-quality X-ray spectrum of the X-ray absorption, which presumably would show material that might even be redshifted. It might be infalling, or it might have much lower velocity than the ultraviolet material if it indeed is in this sort of form that we think it's in. Yeah, so that's something quite interesting that we'd like to investigate in the future. And then, actually, yeah, this is relevant to another question. Someone asked, why do you think that this wind material is launched from the disk? Well, we think this for one reason is because we actually see that this wind often shows a quite dynamical nature. And to sort of illustrate that, here, in fact, I show simulations. This is a numerical simulation done by Proga et al., showing a simulation of the formation of a wind at 3 different times. 0 years in the rest frame. Here's 1.3 years after the rest frame. There's 3.2 years after the rest frame of the wind, here, here, and there. And you can see it's changing significantly over time. The wind structure changes significantly over time owing to changes in the filamentary structure of the wind. And so you expect that these broad absorption line features, if indeed they're formed on these small scales, to be changing. And you can work out the typical time scale of which they can change. And you can see here it's a couple of years in the rest frame. Now, of course, you then also have to take the cosmological time dilation into account, which makes it even longer. Okay? But when you actually look at broad absorption lines on multi-year time scales, you commonly see strong absorption line variability. Here's an example. Here's a broad absorption line quasar, just one example of hundreds that we've studied, where you see that this quasar had, in the original data from the first iteration of Sloan, had very strong ultraviolet absorption there and also had ultraviolet absorption there. And then several years later, in fact, this is the time in the rest frame. It was 1,223 days later in the rest frame. This feature had gotten much weaker. This feature had completely disappeared, okay? And so you actually see significant changes in the strength of the absorption features over time. And because the time scale that you expect from accretion disk launched winds and the time scale you observe in the data match pretty well, that supports the idea that this indeed is probably, much of this material is on an accretion disk type scale. Okay. Okay, so that's another thing that's quite interesting. And then to say a few more words about what we have tried to do in the X-ray band on luminous quasars. Here's one example of what we can do currently in the X-ray band. We can't get data of nearly the same quality as we can in the ultraviolet. But there are a few cases where you actually can get somewhat decent X-ray spectra. You often have to utilize a trick to do this. In this case, the trick that we used is here we had a luminous, very luminous quasar, the redshift of about 4, that we observed with Chandra. And this quasar happens to be very bright, not, first of all, because it's intrinsically a very luminous system, but furthermore, because it's gravitationally lensed. Okay, this system is gravitationally lensed. Here's the Chandra image, which you can see is split into 2, okay, due to the gravitational lensing. And that gravitational lensing boosts up the flux of the quasar compared to what it truly should be by about a factor of 100. So it makes things 100 times brighter than you otherwise would have. And so it gives you a much brighter source to work with. Of course, this is very rare, but so you have to be very lucky to have it. And not only that, this quasar also shows broad absorption lines. And so when you go study this quasar then in the X-ray band, you see hints of what seem to be absorption features. This is a model here of the X-ray data showing the power law spectrum. And you see a deficit of X-ray emission down here, indicating there's absorption present in the spectrum. And you also see an absorption feature that seems to be there, and another one that seems to be there in the X-ray data, corresponding to the features there and there in the residuals. Okay. These are also seen in XMM Newton, but it doesn't come through so well in that plot. And so you see absorption features that appear to be from iron K, which normally would be at about 6.4 kV or up to 6.9 kV for ionized iron in the rest frame. But you see it at like 8 to 12 kV. And so if you work out the implied X-ray velocity, you actually see that some of the X-ray absorbed material actually appears to be flying out very fast with speeds of 20 to 40% the speed of light or higher. And so it appears that at least some of the X-ray absorbing material, contrary to some of the expectations, appears perhaps to be in a state of outflow. And if you work out the implied mass outflow rate associated with that material, it's large. It's like 10 to 30 solar masses per year, with a very large associated kinetic luminosity, certainly carrying sufficient power, if the interpretation is correct, to drive a lot of material out of the host galaxy and thereby affect star formation and so on. And we know that in the work that we did on this particular object, which again is unique in that it has this gravitational lensing boost that makes it very bright, that such behavior could be present but currently undetectable in many other Bal quasars. It's only the lensing boost in this case that lets you see it. And there are a few other local objects that people have studied in considerable detail where they see similar features. Here's another example, this quasar PD-S456, where you see these strong absorption troughs up here. Okay, here's a zoom in of them, where people appear to see, again, iron K absorbing broad absorption lines in the X-ray band. Here's another case, another nearby quasar, where people appear to see almost what seems to be almost like a P Cygni type profile, where you have the emission line here and the absorption line there, again associated with an outflowing wind. Now, the interpretation of all these data, I will tell you, because I've had my hands in it, is very difficult in many cases. Okay, modeling data of this quality, which is not the best quality one might hope for, is difficult. And so there is real significant debate remaining about the overall interpretation here. And so caution is required, and we hope to get better measurements in the future to clarify these things. And then just to end, I was asked earlier about, how could this actually affect a galaxy? Well, the idea is this wind material, if it's launched outward at these high speeds, just doesn't stop, at the nucleus. It keeps going outward into the host galaxy. And people have done modeling of momentum-driven outflows or energy-driven outflows and how they can interact with the host galaxy's interstellar medium, shown there and there. And they work out lots of details of the various layers of interaction that occur in this sort of region of a shock front where the wind strikes the interstellar medium. And the details are complex, but the bottom line is that people estimate that yes, that if the basic interpretation of the data is correct, there's plenty of energy and momentum there to actually have a significant effect upon the host galaxy's interstellar medium. And again, that could have an effect upon further star formation in the host galaxy. It could affect the further formation of the host galaxy. And it could also affect the further fueling of the supermassive black hole itself, in the sense that if you push all the cold gas out, the black hole may have a tendency to shut itself off after a while under the action of these winds. So that's another interesting possibility. And I think this is a good natural place to have our break. But before we go into that, are there any more questions about this material so far? Yeah, go ahead. Yeah, sure. This one? Yep.
So the XML observations are not consistent with Chandra?
Well, no, no, you do. It's there. It's there. This absorption there is what we saw with Chandra. But the stuff below, yeah, that's been modeled. This model, the modeling that's been done there, they've put in an absorption component that takes that out of the residuals, where here we just didn't take it out. So that's just how the data were modeled. That's not an inherent difference. And the details of what happens down here is not the exciting thing. The exciting thing to us are these absorption features you see there. Now, I'm convinced personally that there's something very remarkable going on in these data. Am I totally convinced that indeed we're seeing X-ray absorbing BALs and iron K flowing outward at a large fraction of the speed of light? Not as convinced about that. It's a very interesting possibility. The data are certainly very suggestive of such a thing, and we've made multiple observations of this quasar with Chandra, with XMM, and with Suzaku, trying to test it. And it appears that these features indeed are there. We've seen them with Chandra and XMM and Suzaku. They appear to change somewhat over time, but they're always there. And so something remarkable is going on here, and this is our best interpretation. Yeah. Yeah. How do we know? Well, we don't. We don't know that. We don't have a direct observational way of measuring the X-ray absorbing material's kinematics or something like that to learn about its location. We don't know. So we can't prove it. What I can say is that Murray et al. Worked out theoretically, and Proga backed it up with simulations of the types I showed slightly later in the talk, made predictions before the measurements were done that, that there should be a heavy amount of X-ray absorption there from some kind of shielding material that plays a critical role in allowing the UV wind to survive. And lo and behold, you go make the X-ray measurements and it's there. So that's not proof. You haven't proved it. But a couple of things I can say. I mean, the whole idea of this model is that the X-ray material has a critical role in shielding the ultraviolet material and keeping it from getting over-ionized. If the X-ray absorbing material were somehow out there, then it wouldn't be a very effective shield. That's one point. And then secondly, again, the fact that you see relations like this between the level of X-ray absorption, between the red points and the black points, okay, and the kinematics of the UV wind, tells you that somehow the X-ray absorption, it suggests that the X-ray absorption is really playing a role in shaping the launching of the UV wind. So again, it's not proof, but it suggests to me that somehow Murray et al. Were on the right track. What?
It's just a formula consistency.
Yeah, that's right. It's an eternal consistency type argument. But a much better thing to be able to do would be to be able to go in and directly measure the kinematics of the X-ray absorber down in here, or measure the ionization properties of the X-ray absorber, and thereby learn something about its location in a much more direct manner. That can't be done with the current observatories. We just don't have the throughput and photon collection ability to do it. But that's one reason why people have proposed, I mean, first the International X-ray Observatory, which now is Athena, to hopefully go do this in the future. Yeah. Yeah. How do we know? How do we know? Yeah, that's right. Okay, that is an interesting subject, and it's a complicated subject. And what I can tell you is that in some cases, while we can't get high resolution spectra, like with the grading quality spectra, in some cases with CCD-based measurements, we can get a basic X-ray spectroscopy, enough to show that in some cases you see a photoelectric X-ray absorption cutoff, very consistent with what you would expect from absorption. You see a hard X-ray spectral signature, you see a photoelectric cutoff that suggests that there's absorption. However, and if you're interested, I can give you a reference on something. There is now a subset of broad absorption line quasars where the data suggests that, in fact, some of them may actually be intrinsically X-ray weak. And so sorting that out is a complex and difficult thing that people are working on right now. But yeah, I mean, that would be another thing, another possibility, and this is something that we've considered, is that let's say that there was a group of quasars that didn't make X-rays very well. I mean, the X-rays, going back to this discussion, the X-rays are just an enormous nuisance for the launching of the wind. If you wanted to build a quasar to launch a wind in the best possible way, the thing you would want to do, first of all, is just shut off the X-rays. Just have them never be made in the first place. And that such a quasar would very effectively launch a wind. And perhaps the quasars that are, if there are quasars that are intrinsically X-ray weak, if you believe some of the recent work on the subject, then perhaps such quasars preferentially launch strong winds with large covering factors. That is, perhaps intrinsically X-ray weak quasars preferentially appear as broad absorption line quasars. That's an interesting possibility to think about. Yeah. Any other questions?
Can such feature be seen in black hole band?
Can such phenomena be seen in black? Yeah, certainly, yes. People have, I mean, the scaling is somewhat different because remember the accretion disks in black hole binaries are much hotter. So you tend not to get ultraviolet absorption so much. But what people have done, and this is something you can do very well with X-ray grading spectrometers because the black hole binaries in the galaxy are so much brighter, is people have gone for a number of galactic black hole binaries and done high-resolution X-ray spectroscopy, and they see outflowing material at high speeds in X-ray absorption transitions, not entirely dissimilar to the ones I was showing here. And they see high-velocity winds coming out from galactic black hole binaries. If you're interested in the details there, you can look up, there are two systems, a GRO J1655 studied by Miller et al. And GRS 1915 plus 105 studied by Joey, what's his last name? I can look it up for you. There's another useful study by, Joey Nielsen et al. Yeah. So look for papers by Nielsen et al. And Miller et al. Yep, on the top. Yep. Okay, very good. Well, let's have the break now then. Thanks. Okay, I think we should probably start up again. Are there any further questions that you came up with during the break on winds or on anything else? Everyone's good for now? Okay, so we've now finished the second chapter. Okay, we've talked about the black hole region, we've talked about the broadline region, and we talked about outflowing winds. So now we're going to start talking about phenomena on larger scales. We'll talk about the narrow line region, which I've alluded to already, but really haven't discussed properly. And we're going to focus on that probably for most of the rest of today. And we may get to the torus some today, or that may be in the next lecture, depending on how things go. And we'll then move on and start talking about jets. Okay, and this will give us an overview of the bigger picture, the large-scale picture of what goes on in these active galactic nuclei. So again, we're going to talk about narrow line region, the torus, and jets in this chapter. So again, here's our powers of 10 diagram, okay? Starting at very small scales, moving out to even larger scales. Here's the jet that we'll be focusing on a little bit later. And the jet, of course, while it's created originally on quite small scales, can extend out to very large scales indeed, outside the galaxy itself. And then out here's the broadline region, here's the torus, okay? And here's the inner part of the narrow line region that we'll be focusing on. So we're now moving to another line-emitting region in AGNs that's outside the broadline region. And in fact, this is where Pat Hall stopped making his diagram zooming out and out. I wish he would have given me a few more orders of magnitude going out. So I had to switch to a different set of pictures that were made by Roger Blandford. This shows scaling out on even larger scales now. Okay, so here's a 10 parsec scale, 100 parsecs, 1 kiloparsec, 10 kiloparsecs, 100 kiloparsecs, and a megaparsec. Okay, and going out onto those scales, you can see that you can have out here the narrow line region here, and then the jet, which again forms on very small scales, extends outward through essentially all these scales, even out to a megaparsec scale. You will sometimes see jets extending out to such scales, as well as the lobes that are formed. And then, of course, you also have the host galaxy, which we'll be talking about more in the next chapter. Okay, so we're moving out to these types of larger scales now and thinking about what goes on for them. So let's talk about the narrow line region in some more detail. This is the same slide that I showed yesterday when we just talked about the broadline region, where I mentioned how the lines we see from AGNs are kinematically composite, how they separate out into a broad component and a narrow component. And these are thought to, again, be from the broadline region and the narrow line region. And we're going to focus on this one now. And what can you do with the narrow line region, and why is it interesting and important? Okay. And again, here is an example of the optical UV emission lines that we see from active galaxies, okay? And an example of a line that we think comes mostly from the narrow line region is the oxygen 3 line here. You can see these lines are quite narrow, much narrower than, say, the H alpha line here, or the magnesium 2 line here, or these lines from carbon 4 and so on. So this is a forbidden line, which can only be formed in low-density gas further away from the active galaxy, and thus it predominantly comes from the narrow line region. Okay. Here's this plot, which I showed previously, which we can refer to if we need it. And so let's just go through some basic points about the narrow line region. First of all, the narrow line region is the largest spatial scale in an active galactic nucleus where the ionizing radiation from the central source dominates. Okay? Beyond this, stellar processes, stellar ionizing processes take over the level of ionization. So this is the biggest scale where the AGN's radiation still dominates. And in fact, the NLR is oftentimes thought to be big. In fact, it's so big that you can spatially resolve it. I'm going to show you an image in just a minute where you can actually spatially resolve the narrow line region, at least in the optical, where at least some of the narrow line region emission has scales of 100 parsecs, okay, in local Seyfert galaxies, and likely is even larger in quasars. And because you can go and spatially resolve the narrow line region, this gives you the ability to map out its physical and kinematic properties, at least to some extent. You can go and directly resolve the thing and see it. Okay, here's a nice example. This is the nearby Seyfert galaxy, NGC 1068. Do you remember NGC 1068? We talked about it. It was one of the first objects we talked about. where the man Edward Fath, long ago, back in, what was it 1908 or something like that, saw that the strong emission lines of NGC 1068. Well, when you look at NGC 1068 with the Hubble Space Telescope, this is what you see, okay, on one side of it. So the nucleus of NGC 1068, where the black hole is thought to be down in here, and you see this big plume of emission extending outward, okay, from the nuclear region. And it's big. In this case, it's like 200 parsecs in size. And what you're seeing here is a combined image in the U-band and in the forbidden 03 line that emphasizes the emission from the narrow line region. And that's the emission from the narrow line region shown there. There's a couple things to note about this. You can see that this emission, this narrow line region emission, is clumpy and complex. You can see how it has this sort of clumpy morphology to it. Okay? Yeah, go ahead. Where is it on the other side? Yeah, it's getting extincted, I believe, by dust in the plane of the galaxy. So we're seeing the side of it that's sticking up above the plane of the galaxy, and the other side's getting wiped out by dust. I believe that's what's going on in this case. And I'll show you examples later on where you actually can map the DNLR in the near infrared, which is much less sensitive to dust, and there you can see both sides. So I'll show you that in a minute. Yeah, okay. So the narrow line region is also clearly not spherically symmetric. But when we study with imaging like this, the narrow line regions of various active galaxies, it does appear to be roughly sort of axisymmetric in a sense. In that, if you have an axis of symmetry running along like that, well, clearly the thing has this sort of random clumpy behavior, but it has a general axisymmetric behavior. And in particular, you find that the axis of the narrow line region along this direction generally coincides with the radio axis. As I mentioned, even radio-quiet active galaxies often emit weak jets, okay? And in the cases where you can actually trace those weak jets in the radio, as well as the narrow line region emission, you find that the jet usually runs along the axis of the narrow line region, okay? Where you see the extended linear radio emission. And I will tell you now and elaborate more on this a little bit, you actually in some sources may see, you sometimes see strong line emission from regions where the radio jet appears to be colliding with the interstellar medium of the host galaxy and thereby causing shocks. And so in addition to having the ionizing radiation from the AGN predominantly produce the narrow line region gas via the ionization here, you may have an additional source of ionization from shocks, okay, when the radioplasma in the jet interacts with the gas in the galaxy. Okay, so that's another way you can have narrow line region emission. So when you model the narrow line region, you have to be quite careful because you can see it's complex. It has this complex morphology. It's clumpy. You may not only have pure photoionization, but also shock ionization from jets playing a role. Okay. So what are some basic properties of the narrow line region? Well, first of all, if you look at the lines from the narrow line region, well, they're narrow, okay? In terms of a typical range to think about, it ranges between about 200 up to about 900 kilometers per second, with the line profiles varying spatially across the narrow line region. And we see a wide range of ionization states from the narrow line region. You see low ionization lines, things like oxygen 1. You see high ionization lines, things like oxygen 3. And sometimes you even see very highly ionized species, such as iron coronal lines. There's a wide range of ionization parameter present throughout the narrow line region. Okay? And again, from studying the ratios of the line strengths from the narrow line region and comparing that with the results of photoionization codes, we do infer that the narrow line region is mostly photoionized. Okay? That is, the jet and shocks from the jet may provide some additional ionization, but the photoionization dominates. Okay? And that's inferred from the relative strengths of the lines that are observed. And you can see these lines that I'm talking about the best in systems that are obscured. Okay? In obscured systems, the so-called type 2 AGNs that I've alluded to earlier, where you have obscuring material blocking the small-scale emission, that's actually where you can see the narrow line emission the best, because all the broadline emission is blocked and goes away. And here's a nice example of that. This is an obscured active galaxy. Here it is. It's NGC 5252. And you can see here a spectrum running from, I believe, yeah, from the optical out to the ultraviolet of this particular object. And these spiky lines sticking up here, those are the narrow lines that I'm referring to coming from the narrow line region, all those lines there. Okay. And so you can see the narrow line region, the emission from the narrow line region the best when nature has given you a blocking filter that blocks out all of the small scale emission. Okay, and we'll talk about that blocking material, that torus, in much more detail shortly. But that's what I mean. Okay, so this is a prototypical example showing you all the beautiful lines present from the narrow line region. Okay, so what can we infer about the narrow line region? Well, first of all, the fact that you see forbidden transitions, things like oxygen 3 and oxygen 1, tells you the density has to be low. Okay? Because if the density were high, those forbidden transitions would be collisionally de-excited before they could ever occur. Okay? Because they're slow. So it's got to be low. And in fact, from looking at that matter in a more quantitative sense, people infer that there's a range of density across the narrow line region, ranging as low as about 10 to the 2 particles per square centimeter up to about 10 to the 5 particles per square centimeter. Okay? And from the line ratio, you can also infer temperatures. And here's the sort of range of temperatures, again, that likely vary across the narrow line region. Now, at these temperatures and at those densities, dust can survive in the narrow line region. Okay? And so this is a way that the narrow line region is significantly different from the broad line region. In fact, we'll see that this dust may have a role in actually separating out the broad line region from the narrow line region. Okay? But dust can survive in the narrow line region at those densities and temperatures and can cause self-extinction. And so there's a real problem in studying the narrow line region, in that what you see is there, what you see coming out, is not necessarily reflective of everything that's being made. Okay? Because dust may be having a significant role in extincting some of the emission. Okay? So you have to remember that. This can be overcome to a large extent by studying the narrow line region when possible using near-infrared lines. Okay? And this is becoming increasingly possible now as near-infrared observational technology gets better and better, and I'll say some more about that in a minute. When people make an estimate of the total amount of mass in the narrow line region, it's a lot. It's like 1 million solar masses of gas is present throughout all this stuff to make that line emission. Okay. And so you might say, well, if there's that much gas emitting, why aren't the narrow lines much stronger than the broad lines? Okay. Well, it's because of the density's lower. Okay. Remember, the density is much lower than in the broad line region. And remember, the emissivity from plasma scales as the density squared. And so while the total mass is bigger, the emissivity is much lower. And those two things largely balance out and make the narrow line strings comparable to the broad line strings. Okay. Now, all that being said, and I've shown you, I mean, it's pretty hard to argue with a picture like that the narrow line region is extended. Okay? But to counterbalance that, there have been some recent observations which have surprised a lot of people, okay, of spectral observations of the narrow lines. You can look at this paper by Peterson et al. In 2013. Recently, people have found slow variability of the narrow lines in a few safer galaxies. Okay? And this is only possible when you get observations over a very long time span. I mean, here you can see this is running over, I mean, what is this? This is 2,000, 4,000, 6,000, it's something like 8,000 days of observations there of 5548. And by doing very careful spectral calibration of the data for 5548, again, over many thousands of days, people have found that the O3 strength in 5548 is slowly declining. Okay? Not extremely strongly. You can see it's a weak effect, but it's changing a little bit. And so some of the narrow line region emission is likely compact. Okay? Some of it probably is formed on small scales. okay, it doesn't have to be a huge fraction because you can see the variability is only going from like 5.5 down to like 4.5. Okay, all the rest of the base level it's sitting on could still be formed on the large scales. Okay, but have a look at this paper if you're interested, because this has actually stirred things up a little bit, so suggesting that there may be a significant amount of narrow line region emission formed on small scales as well. I also just want to mention that the narrow line region shows a significant luminosity dependence, kind of like what's seen for some of the broad lines when I talked about the Baldwin effect. The equivalent widths of the lines from the NLR generally drop with increasing continuum luminosity. And up in very high luminosity quasars, they're often undetectable. Now, what's going on there? Well, people don't know, but there are suggestions. Hagai Netzer, for example, is particularly fond of arguing that the narrow line region in luminous quasars may grow to become so large that it becomes larger than the host galaxy that the thing's living in. And so you may run out of gas to ionize. And so you see what I'm saying there? In other words, you know, if in terms of a scaling, again, if you just have that if the narrow line region is taken to have, on average, a typical ionization parameter, xi, which is L over nr squared, right? Well, if you take that to be a constant, then the radius is going to grow as the luminosity to the 1/2 power, right? And if you crank up the luminosity sufficiently high, this is the same scaling, remember, we talked about for the broadline region. If you crank up the luminosity sufficiently high in the very powerful quasars, well, if you just scale up what is seen here for Seyfert galaxies, where again, in NGC 1068, a Seyfert galaxy, it's 200 parsecs. If you scale that up by L to the 1/2 up to a powerful quasar, which could be, you know, 500 times or 1,000 times as luminous as that, you actually end up with a narrow line region that's as big or bigger than a galaxy. And so you may run out of gas to ionize, and that may be why the narrow line region gets weak in the very luminous quasars. Okay. So that's the narrow line region. That's its basic properties. I mean, what good is it? I mean, why should you care about the narrow line region? Okay. Well, there's a couple of reasons, I think, why. First of all, the narrow line region is practically a very useful thing, just in terms of understanding AGNs and calibrating spectra and so on. First of all, the narrow line region lines are nice and sharp, okay, and they're formed from physically a large region, so they're thought to be a good indicator of the systemic redshift of an AGN. There's always this challenge when you measure an AGN spectrum of knowing what is the exact redshift. Because as I've told you, some of the broadline region lines have blue shifts to them, right? And so what should you use for the exact redshift of the AGN? Well, when possible, you're usually best off using the narrow line region line to get the systemic redshift. 0.3 is commonly used to get the redshifts for AGNs. Furthermore, the narrow line region emission is a useful spectral calibrator because the narrow line region lines should not vary on short time scales. Okay? And so if you're trying to, for example, do a reverberation mapping experiment, and you're trying to look at the variability of the broad lines, or if you're trying to do a measurement of variability of absorption of some kind or another, how do you calibrate your spectra? Well, one good way is to use the narrow line region lines, because while it's recently been shown that they do vary a little bit, it's not very much. And it's only over time scales of decades that they change significantly. So they don't vary rapidly, and so they're a useful spectral calibrator. Okay, so those are a few very basic things. Furthermore, the narrow line region can be a very useful bolometer for inferring the total AGN's power. Okay, and I'll show a plot of that here. So another thing you often want to be able to work out is the total power of an AGN. You go and observe an AGN up there, and you want to know, how powerful is this thing that I'm looking at? Well, one good way to estimate it is to use the strength of the narrow lines. Why is that? Well, it's because the narrow lines are formed from a large region that, while it may suffer from some intrinsic obscuration of its own, it's on a larger scale than any small-scale obscuration associated with the nucleus. And so if you want to get a good estimate of the total power of an AGN, whether it's a type 1 or a type 2, that shouldn't matter much because that obscuration is occurring on small scales. You can use the emission of the narrow line region to get a pretty good guess as to how powerful it is. And it seems to work quite well. Here's a plot that compares, in this case, the hard X-ray power of an AGN. Again, the hard X-rays being a very penetrating form of radiation that should not be very affected by obscuration, versus the O3 luminosity here. This is supposed to say log there, but Heckman had a typo in his paper, so he wrote loaf. But it's log LO3, okay? And you can see that these correlate pretty well, indicating that, yes, the O3 power is a pretty good indicator of the total AGN power, okay? And here's a plot that shows here the dispersion in the ratio of the hard X-ray power to the O3 power, and it peaks up pretty decently. Okay. So the AGN, so the point is that the NLR is a useful barometer. If you want to know how powerful is this AGN I'm studying, one good way to do it is to measure the strength of some narrow line, okay, because that's made from a big region that shouldn't be too badly obscured on average. Okay. Furthermore, you'll recall yesterday I talked about eigenvector 1, this set of AGN properties that correlate with each other. Well, the narrow line region lines correlate with that too. Okay, here's the same plot I showed you yesterday. You'll recall this plot. And remember I told you how the lines of, for example, iron 2 and H beta and O3, a narrow line region line there, correlate with each other. And so this is a remarkable thing. It tells you that there's some intrinsic property of an AGN that affects its observed properties running all the way from the biggest possible scales down through the intermediate scales probed by the broadline region, and even down to very tiny scales as probed by the X-rays. So the narrow line region connects in an interesting way with overall AGN properties. And moreover, the fact that the O3 correlates with this eigenvector suggests this eigenvector is probably not just an orientation effect. You might think, well, maybe this orientation is just, maybe the H beta lines are narrow when you're viewing a source pole on or something, and maybe they're broad when you view it edge on or something. The fact that O3 correlates so clearly with the eigenvector tells you that's not the case. And so things like O3 measurements from the narrow line region are very physically useful for sorting out physical effects, because when they correlate with other interesting properties, it tells you that orientation is probably not having a big role here. Okay, so they're a useful sort of way to separate out orientation effects. Furthermore, then, the dynamics of the narrow line region tells you about AGN fueling and about outflows, and I'll show you that in just a minute. And furthermore, you sometimes see anisotropic illumination patterns of the narrow line region, okay, that provide clues about AGN geometry and about orientation of AGNs. And I want to talk about those things now. So here's some interesting results that have been obtained about the dynamics of the narrow line region, okay? I've told you already how the ionization, okay, of the narrow line region is dominated, okay, by the AGN's radiation field. But what about the kinematics of the narrow line region? What dominates that? Well, this plot here, which is of some famous work on the narrow line region by Whittle, compares, in this case, the luminosity of the bulge of a galaxy versus the O3 luminosity, okay? And what people find, excuse me, this is the width. This is the full width half maximum in kilometers per second of the O3 line. And what people find, what Whittle finds, is that the narrow line region width, shown there, correlates pretty well with the host galaxy bulge luminosity. That's the correlation that's found, okay? And that suggests, okay, that, well, it also correlates with the bulge gravitational potential, suggesting that the narrow line region widths are primarily virial in origin, reflecting the gravitational field of the stars in the AGN, rather than the gravitational field of the supermassive black hole. So we're now moving out to gas that's on a physically large enough scale that the kinematics of stars actually matter significantly. And in fact, I want to step back to these orders of magnitude diagrams to sort of point that out a little bit further about stars. One thing which, yeah, I'm sorry, you probably can't see it super clearly, but in a diagram like this, you see that little speck there? That's a star. So what Pat has done here is he's worked out the typical expected separation for stars in the nuclear region of a galaxy, where, of course, stars are very tightly packed. They're packed in the center of our galaxy. They're packed nearly as tight or about as tight as a globular cluster. So they're packed very tightly in the center of a galaxy. So that should be the first star you encounter on that sort of a scale. These little dots here, which Pat just drew in a grid pattern, well, clearly they're not going to be actually in a little grid like that, shows typical star separations. Okay? And if you go out to the size of the narrow line region, there are stars there as well, although I don't think they're not coming. Can you see them there? Yeah, you can see them there. You can see some specks there, I believe. Those are representing the stars. Okay, so the point is that you have this stellar cusp, okay, down in here, which provides a significant amount of mass. And by the time you get out to the size of the narrow line region, the mass of all those stars is outweighing the mass of the black hole in general. And so those stars are determining the kinematics of the narrow line region rather than the black hole. That makes sense? So these kinematics don't tell you about the black hole. So you can't use the narrow line region to work out the black hole's mass, because the velocities of the narrow line region are telling you about the stars, not about the black hole. Okay. So that's the kinematics there. Another interesting thing that came out of this work by Whittle is that he's also here coded by symbol type AGNs with different radio power. And in particular, I want you to focus on the plus signs here, which have linear radio features and high radio luminosity. So those are sources that have fairly powerful radio jets. And look where the pluses lie. They preferentially lie at a given bulge luminosity. They preferentially lie at higher velocities. See that? And that indicates that when you have a fairly powerful jet in there, it actually is stirring up the gas and pushing it towards somewhat higher velocities than it would have otherwise had in the absence of a jet. And that indicates that jets are actually having some role, some significant non-virial role in stirring up the gas in the narrow line region. Okay? And so this is furthermore supportive of the idea that shock interactions between the radio jets and the NLR gas have some significant role in shaping the properties of the narrow line region. Okay, so let's now talk about the profiles of the narrow line region and see what they can tell us about the motions of the gas. Here you'd like to be able to know, how does the gas move in the narrow line region? Is it in the form of an inflow? Is it in the form of an outflow? Is it just moving around randomly? That relates back to this big question here. The dynamics of the narrow line region, which we're able to spatially resolve, this is the first time we can spatially resolve a gas component around an AGN, okay, might tell us something about fueling. I mean, if you see this stuff inflowing, that might say, well, okay, I'm seeing some sort of inflow that may ultimately fuel the AGN. Or if you see it in the form of an outflow, you may think, well, then maybe this is some kind of an extension of the outflows that are seen on smaller scales. That's why this is interesting. Okay, so let's talk about that. Well, people have tried to learn about the kinematics of the narrow line region by studying the profiles of the narrow lines. And here's an example. This is work by Velu, where he's gone and looked at the narrow line profiles of this particular active galaxy. And in his paper, he has many other examples like this, which you can look at. For the H-beta narrow component, for oxygen 3, here's the other oxygen 3 line, here's the H-alpha component, here's another nitrogen 2, and so on. You can see those are the profiles. And first of all, you can see that the narrow line region profiles are not Gaussian. Okay, the narrow line region lines are not Gaussians. They have stronger bases than you would typically expect for a Gaussian. And furthermore, they're often blueward symmetric. I mean, look here at this 03 5007 line. You can see this blueward asymmetry there, right? Okay, the thing's stronger on the blue side than it is on the red side. And that's telling you something about the kinematics. And that there was a long debate, which has now been resolved, and I'm going to show you why momentarily, about the nature of this interpretation. Just like for the broadline region, you might think, well, okay, that's interesting, but you know, just like for the broadline region, that could arise many different ways. So how is this actually made? Well, for the narrow line region, because we can resolve it spatially, we can actually sort it out. And what's going on here in general, the cause of this blue-word asymmetry, okay, is you have some kind of an outflow motion plus dust extinction. And so the basic idea here, and I'm going to draw just a very crude picture, is that you have some kind of gas that's in the form of an outflow. Okay? There's some outflow motion to the gas, and we're, say, observing it from over here. Okay? And what you have is you have outflow plus extinction. So you have the redshifted side of the outflow, which would be the side over here, is extincted. Because remember, the narrow line region parameters, the density and the temperature of the narrow line region, allow dust to survive. And so there can be intrinsic extinction of the narrow line region by itself. And so the idea here is that this side of the narrow line regions get preferentially absorbed down some, whereas this side, which is closer to us, is not as badly absorbed. And that's what leads to this blue-word asymmetry of the lines. Okay? And this is also seen in direct narrow line region mapping, which I want to show now. Okay. But before I do, I want to also note that people have also, in some objects, noted that the narrow line widths are larger for the higher ionization species. So in other words, you look at the ionization level of the different lines, you look at the widths. The higher ionization lines have broader widths. Okay? And that's indicated that you have radial stratification of the narrow line region, just like for the broadline region. The thing is stratified, with higher ionization things in closer and lower ionization things further out. Okay? So it's stratified just like the BLR is. Now, this is what I meant where now people can do direct mapping of the narrow line region. This is some really beautiful work that's recently come out of observations with the VLT. Okay? And what they've done here is they are now able to study the narrow line region in near-infrared lines, like the bracket gamma line. The bracket gamma line has a wavelength of 2.165 microns, okay? And therefore, it's largely immune to extinction effects. And so this studying the narrow line region in lines like this lets you see the whole body of the narrow line region without having to worry about, well, maybe this half is extincted and that half isn't, and stuff like that. You can see the whole thing, okay? And they've done this here for a set of active galaxies. And if you look in their paper, they show many more. But basically, here's a set of each one of these. You can see these are the names of the active galaxies where they've done the narrow line region mapping. And this is basically the direct image here. And then over here is a kinematic map, okay, where I don't remember the exact scaling, but I believe it's such that the blue colors are the blue shifted side and the reds are the red shifted side. And in a number of cases, you see evidence for some kind of biconical outflow type signature of the narrow line region. The thing is outflowing in an axisymmetric biconical way, such that over here you can see this side's blue shifted, right? And that side's red shifted. So it's like a bicone. You're looking at this side coming out and this side going away. Okay? And similarly, I mean, in some cases like this one, you can broadly see, you know, blue shifts over here and red shifts over there, but it's more messy. Okay? And this case is also somewhat messy, although you can see a general trend there. Here's another very nice case here where you can see a biconical outflow signature. And so in cases where you can see any useful kinematic signature at all, you see evidence that there's some kind of a biconical outflow going on in the narrow line region. Okay. And again, this is work that's only become possible very recently with the ability to do very high angular resolution imaging of the narrow line region, okay, in near infrared. And I mean, note the scale here. I mean, from there to there is 0.2 arc seconds in this case. Okay, so that's very impressive. They're going in and doing very high angular resolution imaging with adaptive optics to get rid of the atmospheric blurring. And you can actually start pulling apart directly the kinematics of the narrow line region. Okay, so that's what you can see on the sort of moderate scales of the narrow line region. But the narrow line region, it turns out, extends out to very large scales indeed. Okay? And I want to show you now an example of what you can see when you look at the extended narrow line region, which extends out to very large sizes throughout the host galaxy's interstellar medium. Oftentimes, when you study the largest extent of the narrow line region, you see what are called ionization cones. And I guess the best way to explain Isaac is just to show you one. Okay, here's an ionization cone. Okay, this is a nearby Seyfert galaxy. This is the Circinus galaxy. Okay, and what you see here, what you're seeing here is this is an image here made directly in the O3 line. Okay, and you can see, and here's the contours showing the sort of body of the galaxy of the Circinus galaxy, and you see this cone sticking up out of the Circinus galaxy. Okay, that's an ionization cone. It's a big cone of ionized gas sticking up out of the galaxy. And presumably there's one on the other side too, but it's sticking down underneath the plane of the Circinus galaxy, and so it's getting extincted. Okay, and here is another plot showing, I believe this is some kind of a ratio or something between O3 and H alpha that they put together. There it is. It's O3 divided by something else plus nitrogen 2. And it shows a ratio. It gives you the ionization level of the cone, showing you how the ionization level of the cone changes throughout the thing. Here's another nice example. Okay, here's NGC 5252. I showed you the spectrum of this one just a few minutes ago. And here is the host galaxy of NGC 5252. And that's the ionization cone, okay, of 5252. And you can see there the nucleus is there. And there's this big giant cone when you look at it in ionized oxygen sticking up, you know, from the nuclear region. And you can see this thing is, it's big. I mean, it's really big compared to the galaxy, okay? And so these the narrow line region can, you know, in total, if you go out to its full extent, can extend out a good fraction of the size of a galaxy, okay? And one thing that's worth noting here is, you know, the narrow line region and the jet, which typically runs along the axis of it, gives you an indicator of the inclination. And it's pretty clear that the inclination of the AGN, which is pointing this way presumably, need have little to do with the inclination of the galaxy, which has an axis like that. And so the AGN's axis and the host galaxy's axis often have little to do with each other. They can be highly inclined from one another, as we see from observations of jets and as we see from observations of ionization cones. And so here's a few words I wrote about ionization cones. You see these cones, these wedge-shaped structures of gas that have been ionized by the AGN continuum. These often sort of begin in this sort of classical NLR and can extend outward to kiloparsec scales, forming this sort of extended narrow line region. And then the natural question is, why are they there? I mean, why is there an ionization cone? Okay, well, we don't fully know, but it can be understood quite naturally in the context of AGN unified models, as I'll talk about more shortly, in that the fairly sharp edges of the ionization cone may be defined by the collimation of the ionizing radiation from the AGN. In other words, if you have an AGN here, and it's surrounded by a toroidal structure that subtends some large solid angle, then radiation that goes this way can't get out. The radiation that goes this way can get out, and you get a cone. So the idea there is that the ionizing radiation that makes the cone is being collimated on tiny scales by some kind of a torus, and it has exactly the right geometry you would expect according to the unified model. And so ionization cones, in fact, are thought to be one good piece of evidence that supports the unified model for AGNs. So this could be due to shadowing by the torus. That's the sort of favored idea. But alternatively, there could be other things going on. It could be some inherently anisotropic ionizing continuum that also could be causing this. And so people are still trying to learn exactly what causes the collimation that makes the ionization cones. And again, these cones come in single-sided types and biconical types. Here's a single-sided one. Here's a double-sided one. Okay? And the idea there is that the single-sided ones presumably have a counterpart on the other side, but it's just being obscured. So that's the idea for them. Okay. And so yes. And so I'm going to then wrap up the discussion of the narrow line region by addressing one final point, and that is, I've told you now that the lines from AGNs are kinematically composite, that you have broad lines and narrow lines. But you might say, why is there a broad line region and why isn't there like a region in the middle? Why isn't there an intermediate line region? Why isn't it a continuous range of line emission? You know, there really appears to be this separation into broad lines and narrow lines. But why are they distinct? Why are there two distinct things? Well, the best idea we have for that, which was put forward in a paper by Netzer and Leor, it has been further examined by many people. This is a recent paper by Baskin et al. That considers this issue and many others. Okay, goes back to this issue of dust. Okay, and so the idea that people have is that as soon as dust can start to form within clouds around the AGN, the emissivity of the gas is greatly suppressed. And in fact, that's what's shown here. This is showing the line equivalent width here as a function essentially of radius going outward compared to the radius of the broadline region. And we believe that the broadline region is largely dust-free. But then as soon as you move outward to a radius where the density and temperature conditions are right to allow the formation of dust, suddenly, and that's right here, suddenly the line emissivities drop off greatly. See, it just drops like a stone there. And here it just goes boom. See, they're just dropping off there. As soon as dust can start to form in the gas clouds, the emissivity drops off tremendously because the radiation has a hard time getting out through all that dust. Okay? And in fact, beyond the so-called dust sublimation radius, so the dust sublimation radius is beyond that radius, dust is able to survive, which again are these vertical dashed lines. Beyond that radius, about 80% of the incident radiation gets absorbed and is re-radiated by dust in the infrared. And that's what causes these strong drops, is dust extincting the radiation. And so the line emissivity drops off sharply right as you get to the region where dust can form. And so then you have to go out much further to accumulate a sufficient mass of gas to overcome that much lower emissivity. Remember how I told you that the narrow line region has 1 million solar masses of gas? Well, it's because you need all that gas because you have a very low emissivity. While you have a lot of gas, the efficiency is low because the dust is extincting a lot of the radiation. And so you have to go much further out before you accumulate sufficient further emission to get any measurable emission from the narrow line region gas. And that formation of dust in the narrow line region, but not in the broad line region, is likely the cause of the distinct composite nature of line profiles in AGNs. That's why you have a broad line region and a narrow line region, but not like a middle region in between. Does that make sense? OK, so that's what I wanted to say about the narrow line region. So I think this is a good time to pause and see if there's any questions. And then we can figure out what to do next. Any questions about the narrow line region and all the stuff I was showing? Yeah, go ahead. Right. OK, so his question basically is, when people think about the Baldwin effect or think about the dropping of equivalent width with luminosity in the narrow line region, why do they use the equivalent width? Why don't they use the line luminosity? Okay, and the basic idea there is that if an AGN was perfectly the same and just scaled its size as you went up in luminosity, then yes, as you turned up the continuum luminosity, the idea is that you would also scale up the line luminosity by a comparable amount. So both the line luminosity and the continuum luminosity, in the case of a perfect scaling, would both go up by the same amount. And the fact that the equivalent width drops tells you that that perfect scaling is not true, that something changes about AGNs as you go up to high. While you turn up the continuum, say the amount of gas is not dialing up at a comparable rate to match. So that's why people use the equivalent width to look for physical differences. Yeah, that's the thing. Any other questions about the narrow line region? For an AGN. No. OK, exactly. OK, right. So I need to be clear about that. It's a good question. So the question is, if as I was saying, if I can find it here, somewhere here, where is it? There. If indeed it's just if the kinematics, OK, are being driven by the stars, then why don't you get this in all galaxies? Why don't all galaxies have narrow line regions? Well, again, the kinematics are driven by the stars, but the ionization, if I can find it, going back to here, wherever it is, the ionizing radiation that does most of the ionization of the narrow line region comes from the AGN. So the ionization comes from the AGN, and the kinematics comes from the stars. So it's a mix of AGN plus stars. Yeah, that's why you don't get a. That's why the Milky Way doesn't have a narrow line region. Yeah.
How do we know AGN rather than stars dominate their narrow line region?
Because you can put in a stellar ionizing, a couple of reasons. You can put in the amount of radiation we expect to be coming from all the stars, and it's not sufficient to drive the luminosity of the narrow line region. That's one thing. And furthermore, we see high ionization lines, things like oxygen 3, from the narrow line region. And we even see very highly ionized species like iron coronal lines. Those require a high energy ionizing continuum out in the extreme ultraviolet that you don't get from stars. So that's what tells you that it's an AGN that's driving that ionization, both the specific lines that you see and the total power of all the lines. Yep. Correct. That's right, exactly. So yeah, that's what I meant here. Yes, there is a radius that can be computed where you basically look at the various processes that allow dust to be formed and to be destroyed. Okay, and for example, down in the Broadline region, dust is very efficiently destroyed by both sputtering. The densities are high, so there are physical collisions of dust grains with particles that chip off pieces of a dust grain that tries to form before it can form. And also there's an effect, the sublimation effect, where at high temperatures, a dust grain will spontaneously lose particles via evaporation. And so down at these small radii, dust grains just can't survive because they're either sputtered or they're sublimated away. But as you go out to larger and larger radii where the temperature is dropping and the density is dropping, eventually you get to a point where dust formation can turn on very efficiently. And that occurs in a narrow range of radii right around here. That's what these vertical dashed lines are showing the dust sublimation radius. And as soon as you can form that dust, which occurs over a small range of radii, the emissivity comes crashing down from the lines. And that's what gives you this separation.
But the depth not changed so sharply.
No, there's not a sharp change in the density or temperature, but the turn-on of the dust formation is a fairly sharp thing. That's the idea. Yep. Yes. Okay. This paper, which you should go read, does a number of computations of the Broadline region, and you can ask then exactly what is meant by the Broadline region and so on. But I believe what's being shown here is the size, if I recall. I have to go back. I believe they're showing the size of something like the peak of the H beta line or something like that, the weighted average of the H beta line. That's what they speak of the broad. I mean, again, it's very difficult to speak of a highly specific radius of there is this radius of the Broadline region, because as I've showed you, the Broadline region has ionization stratification running throughout it. And so, it's a characteristic number here that's used, and I believe people typically use the H beta line to work it out. Yep. Yes. Yes.
Whether it's possible to form stars in the narrow line region, in the outer part of the narrow line region.
Can you actually form stars there?
Do you have dust and it might?
Yeah, maybe. I don't know. I don't have much expertise in star formation. And I'm not aware of anyone. I'm sure someone has thought about such things, but I'm not sure of the details. I mean, I think it might be a little rough, just owing to the ionization field of the AGN. But yeah, if you had a sufficiently dense region there that somehow was able to shield itself from the AGN's ionizing radiation, maybe you could form stars. I don't know. It's certainly. I mean, at some point. I mean, at some level, these things. If you consider the full extent of the narrow line region, I mean, this is the full extent of the narrow line region in this thing. I mean, presumably there's some star formation out there, yeah. Can you observe stars? Well, there is, I mean, in what way? I mean, people have talked about seeing obscuration events from a star moving through an AGN's radiation field. The star develops a big cometary tail behind it. and you might see obscuration from that gas. People have talked about such things. And you remember yesterday I showed you an example of strong X-ray spectral variability of an active galaxy. It was NGC 1365. Some people have proposed that may be a cometary tail running behind a star. But whether that's true or not, we don't know. But there are ideas, yeah, about seeing stars in there. Now, about seeing star formation, I'm not aware of any detailed work on that, but there may be something I don't know about. Yep. Okay. So how are we doing on time? Is this a good natural place to stop, or do we have lots of extra time? Because I can. Okay. Okay. So maybe I'll just spend a little bit of time then introducing the torus and the unified model, but I won't say too much, and then we'll break for lunch. Is that good? Okay, fine. So I'll say a few words about the torus then. Okay, so now we're going to move on to the next part of the large-scale environment. And I've alluded to type 1 and type 2 AGNs and the torus and all this stuff many times already. And I now want to talk about the torus in a proper way and talk about AGN unification in a proper way. Okay, so first of all, this whole idea started when people noted that there was a distinction between AGNs. And they, in fact, being astronomers, they split it up into two types, okay? The type 1 and the type 2. And so to first approximation, people found that the optical and ultraviolet spectra of AGN separated into two broad spectral types. You have type 1s. These show broad permitted emission lines, particularly the Balmer lines are very broad. And the formal definition relies upon the Balmer lines. And it's such that the permitted lines that are present are clearly broader than the forbidden lines that are present. So things like H alpha and H beta are clearly much broader than O3. Okay? And you also do have forbidden lines present, and they have moderate equivalent widths. That's what you see among the type 1 AGNs. The type 2 AGNs, okay, have narrow permitted emission lines. So things like the Balmer lines are now narrow, having similar profiles to things like O3, okay? And so the permitted lines have similar widths to the forbidden lines. And furthermore, the lines generally, the forbidden lines, have high equivalent widths. They're very strong, okay? And I'll show you an example momentarily. So that's the formal definition of type 1 and type 2 AGNs. It's a definition based upon optical spectroscopic criteria using the Balmer lines. Okay? And this scheme was put forward long ago by two researchers, Kachikian, who was an Armenian researcher, I believe. I've met him once, and Weidman, who was a professor at Penn State, in fact, for many years. They put forward this definition of type 1 versus type 2 AGNs, just as an empirical thing. They didn't have any physical explanation for it. They just noted empirically AGN types seem to separate out into these two broad classes. Okay. Now, of course, this was a simplification. Further study of the optical emission line spectra of many AGNs showed that there were additional complications. And this led to people introducing intermediate AGN types. You may hear sometimes of a type 1.5 Seyfert galaxy and so on. And there are so-called narrow line type 1 AGNs and further on. So this is a first order scheme of classification, but it's not the full story. Okay? And furthermore, people, unfortunately, in the literature sometimes use the type 1 versus type 2 labels in very inconsistent ways. In my opinion, and maybe someone else disagrees with me, in my opinion, the only proper way to speak of a type 1 versus a type 2 AGN is when you have good coverage of the Balmer lines and good coverage of the forbidden lines in the vicinity of the Balmer lines, things like O3, and you use this classification scheme, because that's what was originally defined. People sometimes now find objects that are X-ray obscured, and they call them type 2. And then later on, they actually go and get proper spectra in covering the Balmer lines, and they actually see they have broad lines. Okay? And so you can make a real mess of things if you're not careful about doing your type classifications. But this is the formal definition. And it's really quite apparent when you look at their spectra. Here are examples of a type 1 AGN and a type 2 AGN. Okay? And there's a couple of things that are worth noting here. I'll give you a minute just to stare at it. Okay, first let's look at the type 1 AGN and look, for example, at those O3 lines. See those narrow, spiky O3 lines sticking up there? And then you see here how the H beta line is much broader. And similarly here, the H alpha line is much broader. Okay, that's an example of a type 1 AGN. Okay? And here it is, by the way, here it is zoomed in. So here basically Peterson expanded the y-axis scale, and you can see here the broad H beta being much broader than the O3. Okay, that's a type 1 AGN, and that's what's meant by all these words. That's the difference. Okay? Type 2 AGNs, and here's the example I showed previously, all the lines are narrow. Okay? And things like H alpha and H beta don't have distinctly different profiles from things like O3. And furthermore, as I mentioned back here, the equivalent widths of the forbidden lines are very large. I mean, the continuum is weak. And so the equivalent widths of these lines are large. They stand way up above the continuum level. Okay? That's the official definition. That's the formal definition of type 1 versus type 2 AGNs. Okay. Now, what does that mean physically? Well, people didn't know for a long time. It was more than a decade between when Kachikian and Wiedemann put forward that original definition and when people came to a physical understanding of what was going on. Okay? And here's the story. These optical spectral differences between the type 1 and the type 2 AGNs have come to be understood as due to orientation-dependent obscuration of the central regions by a so-called torus. Okay? The torus is presumed to be a roughly axisymmetric structure of large height, so that at least at low AGN luminosities, the majority of AGNs are obscured by it. Okay? So in other words, the idea here is that most AGNs are actually type 2 AGNs. Most AGNs are obscured. And it's only the minority that are not obscured. And this is backed up by X-ray surveys and so on that show that most AGNs are obscured. The torus, what is it made of? Well, it's thought to be made of a combination of dusty atomic gas and molecular gas. And that gas and the dust in particular causes large extinction in the optical UV and sometimes even out in the near infrared. Okay, so the torus is responsible for extincting a lot of the radiation, and it doesn't let it get out. The torus then lies between the broadline region and the narrowline region. That's where it's located. And so the narrowline region is large enough that it's largely unaffected by the torus, where the broadline region is very strongly affected by the obscuration of the torus. Okay? And such that type 2 AGNs are those obscured by the torus, where emission on the scale of the broadline region and smaller is obscured by it. And models explaining the differences between type 1 and type 2 AGNs this way are referred to as unification models. And here's a picture that I've shown a couple of times already of this model. And for now, let's just focus on the bottom part of this diagram, on the radio-quiet AGNs. We'll talk about the radio-loud AGNs more later. Okay? So for the radio-quiet AGNs, the idea is a type 2 object, for example, a Safer 2 galaxy or a type 2 quasar, is one where this dusty molecular torus, shown there, is obscuring the line of sight. And you can't see down into the central regions, okay, in a direct sense at least. And thus, it's hard to see the broad lines, for example, whereas you can see the narrow lines formed on a physically larger scale because they're not obscured by the torus. Yeah, that's the idea. Type 1 objects, on the other hand, give you a clear view down into the nuclear region. Okay? And you can actually see both the broad lines and the narrow lines. So that's how that relates to all the words that I was saying back here. Okay? You know, you have this orientation-dependent central obscuration. In other words, if you're oriented this way, you're obscured. If you're oriented that way for the exact same object, you're not. Okay? It's an axisymmetric structure of large height. There you go. You see, it's axisymmetric. This is a cut-through picture. Axisymmetric. It has a large height compared to its radius, such that most AGNs will be oriented such that you actually strike the torus. Okay? It's a dusty atomic gas, a molecular gas. That's what's causing the extinction. And then the type 2 objects are the ones that are obscured. So that's exactly what you see in this diagram. Is that clear to everybody? The basic idea here? That's the idea of the unified model. Okay. These unified models have had great success overall. They really have cleared things up a lot, and they've shown that a lot of this distinction between type 1 and type 2 AGNs is artificial in the sense that you're studying the same type of object, and it's just obscuration differences that are making the observed differences. Okay? And that being said, the most simple unified model, which proposes that the torus is the same in objects of all type, cannot be true. We now have clear evidence that there are substantial object-to-object variations in, for example, the covering factor of the torus and likely the geometry of the torus. As one example, which I'll talk about more later on, we now have quite good evidence that the torus is less important in terms of the fraction of objects it obscures in highly luminous AGNs than in low luminosity AGNs. There's a luminosity dependence to the obscuration by the torus. Okay? And so the simple unification model, which proposes that everything is exactly the same, can't be true. But nevertheless, the basic idea is an extremely powerful one that's cleared up a lot of otherwise confusing measurements. Okay. Now, I think having introduced that, I would think this is a natural place to stop. And so I think I'll stop there, and then I'll pick up next time introducing the evidence for the unified model. I mean, why do we think this model is right? We have very good evidence for it. And I'll explain things like the scattered radiation, the transmitted radiation, and polarimetry, and X-ray observations, and so on, and what they all have to say about the torus. But I think, given the time, and this is a good natural place to stop. So are there any questions about the basic? I mean, I haven't proved it yet by observations. I've just sort of told you this is what we think. And I'm going to show you all the why we think it's this way soon in the next lecture. But for now, are there any questions just about the basic definition of the torus in the unified model? Or is that all very clear to people? Seems good for everybody? I mean, one piece of evidence, again, that we think we're on the right track, as I mentioned, comes just from these ionization cones. I mean, the fact that you see things like that is a pretty darn good hint that you have some kind of toroidal obscurer down on small scales that preferentially lets radiation out in the axial direction. You see that, right? So anyway, I think then we'll stop there for today. I'm happy to take any questions. Feel free to come up, and there we are. Thanks.